Hello friends, hope you're having a fantastic day today. This is going to be part 4 of our 50-hour long DSA mega course that contains every single thing related to technical interviews, data structures and algorithms. Now you can find part 1, 2 and 3 right over here. I have also provided their links in the descriptions. Now due to YouTube's restrictions, I can't upload full 50 hours in just one video. That's why I have to break them down in bunch of different segments. But needless to say, the content is once again as useful as it can be. So without any delay, let's get started with part 4. Dynamic programming is the toughest and most important part of any DSA interview question, and I have decided to make a full course on that. By the end of this course, I can guarantee you that you will become master in all dynamic programming questions. And in this course, we are going to discuss what is dynamic programming, brief history, what are the different ways to use dynamic programming, recursion, tabulation, memoization, all the characteristics, when to use dynamic programming, what are the most effective ways. Trust me, these questions have been asked by hundreds of companies thousands of times. So without any delay, let's get started. The term dynamic programming has the reputation of being a scary term, but it's not that complicated. Actually, this dynamic programming approach is nothing but a problem solving technique. And this technique involves you of taking a bigger problem and then start breaking into bunch of different smaller sub problems. Now for each of the sub problems that you are already calculating the results, you are also going to store this result, and this is going to be the important procedure in this whole dynamic programming scenario, that because you are storing the results, whenever you need to recalculate or refine the same value, you can simply quickly look up in the stored values, and then you would be able to find the answer for that, and eventually you would be able to find the correct solution for the item that you are looking for using dynamic programming. Now in order to achieve that, we are going to use bunch of things like recursion or memoization or tabulation, but let's try to understand dynamic programming with a very simple example of a Fibonacci series. This is the simple equation of for any Fibonacci series, and we are given the first two values of the Fibonacci sequence, where Fibonacci of 0 is going to be 0 and Fibonacci of 1 is going to be 1. Based on these two values and this function, we can calculate any particular Fibonacci number. We can calculate number for even Fibonacci of 100, and that is going to be sum of Fibonacci of 99 plus Fibonacci of 98. Now let's try to understand that if we have to calculate or find the value for Fibonacci of 5, how we are going to be able to do it without using dynamic programming. And for simplicity, we are going to be using recursion to solve this problem. Logically, Fibonacci of 5 we know is going to be sum of Fibonacci of 4 plus Fibonacci of 3. Now same way, subsequently, now notice that in order to calculate Fibonacci of 4, we will have to do all of these calculations, and same way in order to calculate Fibonacci of 3, we will have to do bunch of different more calculations. But notice over here we are calculating the value for Fibonacci of 3, over here we are calculating the value of Fibonacci of 3, over here we are calculating the value of Fibonacci of 2, once again Fibonacci of 2, and once again Fibonacci of 2. So we are doing lot of repeated work, and for problems like these, dynamic programming would be the correct and most efficient approach. Because now notice the scenario that what if we just simply create an array where we are going to store the result of every single Fibonacci value starting from value 0 all the way up to 5, and all we need to do is store those results, and whenever we need to calculate the new value, we can always look up in the previously stored results. So let's try to understand this with an example. We know the base case Fibonacci of 0 and Fibonacci of 1 is going to be value 0 and 1. For value Fibonacci of 2, the value is going to be sum of previous two elements, so this is going to be 1. Same way Fibonacci of 3 is going to be sum of previous two elements, so on and so forth. We can keep on repeating for every single value, and we would be able to generate Fibonacci of all the way up to million values in very quick fashion. Now notice the difference between two approaches. Without dynamic programming, we are doing bunch of repeated work for our recursion call, and the time complexity in this case is actually going to be big O of 2 to the power n, which is very expensive. Like, trust me, this is very expensive, and most of the computers cannot even compute more than 100 numbers. For this approach, dynamic programming approach, time complexity is actually going to be big O of n simply. So you can compute billion values and still computer would be able to run very efficiently. And this is the true power of dynamic programming. Dynamic programming was originally invented in actually 1950s as part of the way to calculate some complex problems where we are already storing the results and we would be able to recalculate that in bunch of other places. Now, computers were not popular in 1950s, but the underlying concept allowed computers to quickly look up the previously computed values and come up with the answers. This was actually developed by a very popular mathematician called Robert Bellman. And yes, this Robert Bellman is the same Robert Bellman from our very popular Bellman and Ford algorithm. And if you know, Bellman and Ford is a great algorithm if you want to find the shortest path amongst any graph where you have negative values as well. So which is like a much better approach compared to Dijkstra's, which only works with non-negative values. So now coming back to our problem of understanding what dynamic programming is. Now we know that we'll have to deal with three distinct terms while speaking about dynamic programming. First one is a recursion. Well, it is nothing but a simple way for you to take a bigger input, start breaking this bigger input into smaller input and smaller input and again smaller input until you reach to a case where it is very easy to calculate. And once you have this result, you would be able to build the next result, then you would be able to build next result, and so on and so forth. You would be able to solve this problem completely, and this is the simple recursive approach. Next category is memoization. So memoization is actually very closely related with recursion, where for recursive call, whenever you are making and whenever you are doing any sort of computation, whenever you find some result, you start to store that result in some fashion and you are actually memoizing these values. So say in future, if you have to make another recursive call for any particular item and then you need to make that calculation, you already have those values stored in the result, and this is called memoization. So recursion and memoization would always go hand in hand in any dynamic programming approach, and combination of these two is actually going to be called top down approach. Now, why it is called top down? Remember how recursion works. For recursion, you are going to start with the topmost or most largest or extreme value, and then you are going to be taking on smaller and smaller sub problems, and once you reach at a base case, then based on that you would be able to start making calculations. So there would be a recursive call stack that you are going to take care of and which will store all the results. Now the third term associated with dynamic programming is going to be called tabulation. So tabulation is slightly different compared to our recursion plus memoization approach. Now even in tabulation, we are storing the result of items that we are calculating. But the different part is that let's say that we are currently given a problem size of this, and where we need to store the value for something associated with term 50 or value 50. As part of dynamic programming tabulation, we are actually going to start calculating results starting from value 0 all the way up to value 50, and this is going to give us the result all the way up to all of these values which we would have stored. So notice that instead of starting at the biggest value, we are actually starting at the smallest value, and then we are building our solution with bigger and bigger values, and eventually we would calculate the results for all 50 values. So logically, this is also a dynamic programming technique that is going to be opposite of the top down approach, and that is called bottom up approach, where you are starting at the bottom and then you reach at the very top. And both of these ways can be used in different scenarios. Many times you can also use them interchangeably depending on the problem statement, but there are some scenarios where it makes sense to use either top down approach or bottom up approach. So let's understand those scenarios as well. Logically, let's say that if you are already given that the problem can be easily solved recursively, it makes sense to use a top down approach, because the recursion goes hand in hand with memoization and dynamic programming. It is going to be a less coding approach, and you can also simplify your implementation and understanding of it. Next thing is, you will also have to keep track of the recursive call stack, so that is something that you need to be aware of, and also understand that how the time complexity is going to affect. The other thing with recursive approach or top down approaches, that many times you don't have to do all the calculations. So if you only need to do selective calculations in order to generate the result, then it would make sense to use top down approach. And there can be many examples of this, but one common example is a problem called unique paths, which you are going to solve in this subsequent lead code problems that we will do. Same way, let's understand some of the benefits of bottom up approach. If the problem can be easily completed in a bunch of different sub problems, then it becomes a good candidate. If you have a good base case, and based on the base case you can build on top of that base case for all the other subsequent value, then it makes sense to use bottom up approach. If you need to do all the calculations for all the sub problems and store all of those results, which means you are not doing selective calculations and you are not doing sparse calculation, but you are doing dense calculations, then it makes sense to use bottom up approach. And remember that this is going to be an iterative approach, so you don't have to worry about keeping track of any different type of call stack, so it works perfectly fine. And these are the two common differences. Now I know we are at the very beginning of our dynamic programming journey, so it's tough to understand all of these statements, but I can guarantee you that after completing our 20 lead code problems, you would be able to very easily identify the difference between bottom up approach and top down approach, and when to use which one, and how to use memoization, recursion, and tabulation. So I guess I gave you like good introduction of what dynamic programming is, what to expect. Basically take a bigger problem and make bunch of different smaller problems, or do like a recursive approach and try to come up with like a smaller and smaller sub problem, and eventually store those results, and after storing these results, come up with the solution. So that would reduce your time complexity significantly.
So, understanding what dynamic programming is will allow you to understand more complex dynamic programming topics such as two-dimensional dynamic programming. So, we will understand the concept of that as well, and then we will dive deeper into dynamic programming questions.
So 2D dynamic programming is actually nothing but an extension of the original dynamic programming that we all know. Now, in typical dynamic programming, we are basically given a set of problem that we are trying to solve, and in order to solve that problem, we store the information of all the sub step of that problem in an array or a string like format. So basically, if we have to take the classic example of the climbing stairs problem, basically we are being told that we are given a bunch of stairs, and at any given position we can climb one step or we can climb two steps, and we need to find that how many distinct ways we can reach at the top. This is a classic dynamic programming example, and as part of the solution what we do is we take that if there is only one step, how many distinct ways we can climb at the top. Same way, if there are two steps, how many distinct ways we can climb at the top, and so on and so forth. And we would keep on pertaining that information in an array like format and store it, and then based on that we would be able to very easily calculate the final result only by looking at the previous two values rather than going and redoing the whole exercise. That is the core concept and power of dynamic programming. In two-dimensional dynamic programming, basically we take that up a notch. We typically break the problem down into a pieces of set of permutations and combinations. And let's say that we are given a problem where we are given a particular word, and we are given another word. So let's say that is like a substring of the original word 1, and we need to find out that how many distinct substrings that we can make out of this second word 2 that we are given based on this first word. Now in that case, the problem becomes exponentially difficult if we just have to use single dynamic programming. We won't be able to solve it. So what we are going to take it, let's say that for word 1 we are given the values a b a b a b a c, something like this, and word 2 we are given as the value of a b and c. So in this case, what we can do is we can take every single possible combination of word 1 against word 2 in a grid like format. So where we are going to have a scenario that what if we have word 2 present over here, and what if we have word 1 present over here, and for all of the permutations and combinations we would treat that if, let's say for some reason, if word 1 only had values a b and word 2 only had the value a, what would be the total number of substrings that we can generate, and that would be calculated based on a cell value that represents over here, where we can notice that we are currently taking care of a and b from this word 2, and from word 1 we are taking that as if it only has value a. So on and so forth. You can understand all sorts of different questions and examples where we can use 2D dynamic programming, but the core underlying concept is that now instead of just taking care of a single parameter, we are actually worried about two distinct properties, and based on that we are actually going to create a grid like format, and for this grid we are going to iterate over every single combination to solve the problem. Now let's visually represent. For a typical dynamic programming, we saw the classic example of climbing stairs where we had the values being stored within an array. And for any particular value x, the answer of x was directly reliant on the previous two values that we have already calculated, and that was the sum of the previous two values. So let's say that this value was a and this value of b. We could have said that the x is equal to a plus b. This is not going to be as straightforward in a 2D dynamic programming, because now we are dealing with a grid like structure and we already have calculated values beforehand. So let's say that there is any particular cell x that we are trying to work upon. It could be possible that we only care about the direct diagonal value. It could be possible that we care about the top value and the side value, or it could be possible that we care about all of these three values, and some form of addition, multiplication, subtraction, whatever that case might be, would be the recurrence relation in this case to solve this problem. So it is really important in the 2D dynamic programming to first of all understand that number one, what is going to be the base case and what is going to be the recurrence relation. And based on these two information, we need to start populating our matrix to solve the problem that we are currently given at hand. So number one type of problem that frequently occur is any particular grid based problem. So whenever you see that you are trying to deal with two distinct type of character and it makes sense for you to generate a grid to iterate over all the permutations and combinations, definitely this is a clear clue that you can use 2D dynamic programming in order for you to solve this problem. Second one is typically substring related problems. So whenever you are given like two words, you are trying to find all the substrings of one word from the other word, or you are given two words and you are trying to see that how many distinct ways you can generate like word 2 from word 1. All of these things can also be done using 2D dynamic programming. And third one are typically partitioning and permutation and combination problems. So for partitioning problems, it could be possible that we are only given just one set of value, but we will have to partition it in such a way that multiple different form of path are being generated from that particular given value, and for each of the subsequent path we might have another classic path on their own. And that in such scenarios we can also start thinking about using 2D dynamic programming. And don't worry, we are going to see examples of all these three. Now, what are the typical prerequisites in order to understand this dynamic programming course? Now, usually I don't put prerequisites in my courses that I teach. But the thing is, this is a special one and this is an advanced level course. So I would highly recommend that first you understand or you have good grasp over the concept of string and array, because this is really important. Now, second thing I want you to learn is to have idea on what typical normal dynamic programming works, because this is going to taking up one step further than we already have. And third thing that you should be familiarized with or have understanding about is that how typically memoization and tabulation works. So these two are typical different ways of iterating over any particular problem, and you need to encounter like recursion and iteration in different scenarios. So you need to understand like bottom up and top down approach and different dynamic programming concepts. So I would highly encourage to have information about these three things. Now I have already created videos and courses on each one of them, so you should be able to find it very easily. Okay, now without any delay, let's get started with the most important part of this course. The lead code problem we are going to solve now is called climbing stairs. We can see that this one is an easy problem and also a very well-liked problem. The statement is quite straightforward, that we are trying to climb a staircase that currently has n steps to reach at the top. Now, each time we have the option to either climb one step at a time or two steps at a time. Now we need to determine that in how many distinct unique ways we can reach to the top of the staircase. So let's try to understand this with an example. Suppose we are only dealing with just one single step. How many distinct ways we can reach to the top? Well, obviously there is just one way we can reach to the top, by taking one step. So in this case we need to return 1 as the answer. Let's say for the same example, instead of 1, what if we have 2 steps and now we are trying to reach to the top? What are the distinct ways? So first is distinct ways, take one step and then again one step, and second distinct way is to take 2 steps directly. So in this case we need to return 2 as the answer, that these we have 2 distinct ways to reach to the top. Same way, if we have 3 distinct 3 steps, how many distinct ways we can reach to the top? Well, we can continue by taking just one step at a time. So that is going to be our path number 1. Second path, we take 2 steps and then we take one step. Or third path, we take one step and then we take 2 steps. So overall now we have 3 distinct ways to reach to the top. So this is what we need to return as part of the answer. Now let's try to understand the most common brute force approach to solve this problem. Well, the idea is quite straightforward. Let's say that we are currently dealing with 5 different stairs. Now at any given moment, starting from position 0, we have 2 options. First option is either we take one step, or the option is we take 2 steps. So let's make a decision tree based on that. Currently we are at step 0. What are the options we have? We can take one step and reach to step number 1, or we can take 2 steps and reach to step number 2. Same way, at 1 we can take one step and reach to step number 2, or we can reach to step number 3. Same way, we can reach to step number 3, or we can reach to step number 4, and over here we can reach to step number 4 and we can reach to step number 5. Now the moment we reach step number 5, this is one of the unique paths. So we will note this path down and keep on iterating with our possible choices. So once again over here we will have 2 choices, 4 and 5, and once again we will have here one more choice. But now notice that there is a big issue with this one. Why? Because at every single position we have 2 different ways to choose from, and whatever path we take, depending on that, we are once again going to be dealing with 2 more positions. So in this case the time complexity is actually going to be 2 to the power of n, which is a very expensive time complexity, and we will have to find ways to do things smartly. So that's where the most beautiful concept of the entire computer science come into the place, and that is called dynamic programming. Now notice over here that we are doing bunch of repeated work for the same amount of thing that we are calculating. We are calculating that what are all going to be all the different options from 2, and same calculation we are doing it over here. We are calculating that what are going to be all the different options from 3, and same thing we are calculating over here. So why don't we just memorize or store the information that we have already calculated and use it whenever we need to use it sometime in the future? And that is the whole idea of dynamic programming. So in order to do that, or in order to achieve dynamic programming, we will have to understand two things. What is going to be the base case scenario, or the minimum starting point for us to understand or start building the solution, and second one is what is going to be the dynamic programming correlation amongst different parties. So first let's understand the base case. Well, base case is quite straightforward. Let's say that if we are given 0 steps, how many different ways we can reach to the 0 steps. So we can only have one distinct way to reach to the 0 step, because where we are not taking any steps. Let's say if we are only given one step, how many different ways we can reach to the top. We only have one way to reach to the top, that is by taking one step. So these two are going to be our base case scenario, where dp of 0 is going to be defined as 1, and dp of 1 is also going to be defined as 1. So now these are the most common entries that are always going to be true and that we can calculate very easily. Now let's understand that what is going to be the dynamic programming recurrence relationship between or any given two parties. So for that, let's try to understand the scenario. We are currently dealing with these 5 steps, and we are trying to determine how many unique ways we can reach to step number 5. So the most simplest logic you can think of is that whenever you need to reach to step number 5, what are the ways to reach to step number 5? Well, one way is that either we reach to step number 4 and then take one step, or second way is that we either somehow reach to step number 3 and then take 2 steps. Now you must be thinking that there is one more way where we can take one step from step number 3 and then take one more step to step number 4. Well, we already covered this case when we first mentioned that whenever, like, all the different ways you can reach to step number 4 and then take one step. So overall we only have 2 unique ways to reach to step number 5, that is through step number 3 and step number 4. And once we are at either one of these locations, we are guaranteed to reach to step number 5. So all the ways we can reach to step number 3 are all the unique ways we can reach to step number 5. Same way, all the ways we can reach to step number 4 are all the ways we can reach to step number 5, and this is going to be sum of these 2 unique ways. So this is going to be our recurrence relation. Why? Because we have the liberty to choose from 1 or 2 steps, and if we do it like reversely, we can just calculate that, okay, we need to calculate all the ways to reach to step number 3 or step number 4 and do the sum, and that is going to be our recurrence relation. Based on that, we can actually create a mathematical formula that at any given moment dp of I is going to be dp of I minus 1 plus dp of I minus 2. And based on this equation, now we can solve all our problem very easily. Let's say that now we are trying to solve for the answer n is equal to 6. We already know that this is the formula we are going to use to solve this problem. On top of it, we already have the first 2 values being filled out. Why? Because dp of 0, 1, 2, 3, 4, 5, and then this is going to be the value number 6. Now for dp of 0, we already know it's 1, and dp of 1, we already know it's 1. So say based on this equation, dp of 2 is going to be 1 plus 1. So now we can notice that if we have to reach to step number 2, there are 2 unique ways to reach to step number 2, and same way has been proven by this equation as well. Same way for step number 3, the sum is going to be 1 plus 2. So we can do it 3. Same way step number 4, we can do sum of these 2 values, so it is going to be 5. For step number 5, the sum is going to be 5 plus 3, so it is going to be 8. And for step number 6, it's going to be 8 plus 5, so answer is going to be 13. So there are going to be 13 unique ways to reach to step number 6, and the solution becomes quite easy and simple. And notice what we just did is we first establish a base case, then we established that what is going to be the relationship, and then based on that we kept on populating further and further values. So even now if we have to calculate for n is equal to 100, you can do it very easily and very quickly. So logic is quite straightforward. Now we can do one more improvement over here. Because we are only dealing with 2 previous values, instead of using an entire array to store all the values, we can just have 2 variables, previous 1 and previous 2, and for every single value we can just resolve these values and keep on updating for a subsequent current values. So we'll see this in code that how this can work, but basically this is the whole idea, and based on this you can solve this problem very easily and very quickly. If we see time complexity, it is going to be big O of n, and for space complexity, well, if you use a full array it would be big O of n, but if you just use couple of variables like this, it is going to be big O of 1. So now let's try to see the coding solution for this one. Now the coding solution is quite straightforward. First we are going to take care of the base cases, that if given n is equal to 0 or 1, we can simply return 1. If that is not the case, we are going to initialize two variables to keep track of the previous two steps values, and the initial values are going to be 1 and 1 for step 0 and step 1. Then we are going to iterate over the given loop starting from I is equal to 2, or from the third step all the way up to the n. And for any particular current step, the number of ways we can climb up to that step is going to be sum of previous two elements. So we will add that, and then we will simply swap the values between previous two and previous one. So previous one is going to become the current value, and previous two is going to become the previous one value that we had before. And after we keep on updating that, in the end we can simply return previous one as the answer, and that would be the total number of ways to reach any particular nth step. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code beats 100% of all the other solutions, which is pretty awesome, and that is because this runs in 0 milliseconds. But anyways, this is a beautiful solution and a good introduction towards the dynamic programming. Hello friends, we are still not employed by FAANG company, so let's not stop lead coding till we get there. The problem we are going to do today is actually asked in a lot of top tier IT companies, and if we look at the recent data, it has been asked in Amazon 20 times, Apple 8 times, Facebook 2 times, Google 6 times. So needless to say that this is a really important problem. So I hope you provide your utmost attention. This is the outline on how we are going to solve this and the things I'm going to cover in this video. So first we'll understand the problem statement. I will be creating a brute force solution. Then we will build an optimal solution with dynamic programming. And at the end, I'm going to show the Java code for this one. Basically, this is a lead code medium problem, but in my opinion, it should be a lead code easy problem because it's not very difficult to understand. But the thing is, its concept is really important. That helps you build the conceptual knowledge of dynamic programming, which you can use in bunch of different problems. And a lot of FAANG companies loves to ask this kind of questions. So if we understand the problem statement, basically we are a professional robber and we are planning to rob houses in each street. Now the thing is, the way houses are mentioned in the street is that every single house has some amount in that particular house. But the only condition we have is, if we rob one house, we cannot rob the house that is exactly adjacent to it. So suppose we decide to rob this house. If we rob this house, which means that we cannot rob this house or this house, and we can again, if we want, we can again rob this one. So that option we have, and our aim is to maximize our profit. So basically we are given an input array nums that shows that for every single house how much amount of money is presented over there, and we need to see that what route can we take which maximizes our input or the amount of money we can steal, and we need to show that in the output. So let's try to understand this with an example. So basically over here we are given the values as 1, 2, 3 and 1. So notice that the maximum amount we can steal is basically if we go down this path. So if we start with the first house, and then then we can't rob the second house, but then we rob the third house, and the sum of these two would actually become 4, and this would be our answer. So for the brute force, we are going to solve the same problem. Basically one way to understand the brute force approach is that at every single position, initially we are at 0th location. So if we just make all the possible pairs which we can create where we can rob houses. Basically that would be our solution. So let me show you how. So initially at 0th position, now we have two options. Either we can select the value number 1 or 2. So either we can select the first value or second value, and these are the subsequent values. Now at this position 1, we again have two options. Either we can rob the third house from here, or we can skip the third house and we can also rob the fourth house if we want. So the two choices we have over here is either we go down this path or we go down this path. And at this house number 2, we only have one option. We can't rob this 1 or we can't rob this 3, so we can only rob this 1. So the only choice over here we have is actually 1. And now we just do the sum of all the values. So for this path, the sum we would get is 4. For this particular path, the sum we would get is 2. I just put it in a box so it's easier to differentiate. And down this path, the maximum sum we can achieve is 3. So if we compare these three elements, we can clearly see that 4 is maximum, so we simply return 4. Now brute force solution works, but the problem with this one is that we need to create every single pair, and in order to generate pair, essentially at every single position we have two options, that whether we need to keep this value or we do not need to keep that value, and that eventually would bring a lot of different values in our graph and on the number of decisions we can make, which means that the time complexity for brute force approach would be, you guessed it correctly, 2 to the power of n, where n is basically whatever the number of inputs given over here. And you guessed it correctly. Also, I already gave it away, but we are going to use dynamic programming over here, and let me show you how we can use dynamic programming to solve this problem. We are going to use a custom example, and I have already mentioned it a bunch of times that it is really important to have your own custom examples. That shows that you can think outside of the box. So over here initially, we are at this position, value number 2. Okay, so what we can determine is that initially at this position, if we were given only one house, what is the maximum amount of value we can steal from this particular house? Of course, the answer is pretty simple. We can only steal whatever we are given, right? Because we are only given just one house. So initially at this point, suppose if we create an additional data structure that keeps the track of what is the maximum amount of money we can steal up for any element, then our decision making will become easier, and we would be able to choose that what path we want to take. So let me show you by an example. So initially at this position, value number 2, the maximum amount we can rob will only going to be 2, because there are no other values before that. So this is the maximum amount we can rob so far. Okay, now this at value number 4, the maximum amount we can rob is actually, up until this point, it's only 4, because we can't use 2 when we are robbing 4. If we choose to rob this second house, if we choose to rob this one, we can't use it. We can't basically use this first house. So we know that for the first two values, these are the maximum amounts we can rob. Now we are at this position number 3. So at this position number 3, we have two options. Choices are pretty simple. Either whatever the value maximum we have so far over here, which means that so far the maximum value we have is 4, or whatever the previous maximum value we had plus whatever value we currently are at. Because remember, if we decide to rob this house number 3, basically we still have the option to rob house number 2. We can't rob house number 4. So up until this value number 5, the maximum we can rob so far is actually
5. Why? Because we check that, okay, up until this point, what is the maximum that previous element has dropped? Basically, like one house before this house has dropped, and that maximum value is 2. So I can do 2 plus 3. So maximum I can rob up until this point is actually 5. So okay, we have this knowledge, and up until this value, the maximum we can rob is 4. Now let's forget about this one for now, because anyways at any given time we are only concerned with the house that are adjacent to each other. Now we are at this position number 9. So what is the maximum value we can rob up until this point 9? Well, the answer is quite simple. We check that, okay, what are the two values before this 9? So this is 5, which means that if we decide not to rob this house, the maximum we have robbed so far in this sub array is actually 5. But how do we decide that whether we want to keep this 9 or not? Well, we just need to apply the same logic. The house that is adjacent to 9, before that, what is the maximum amount we have found? So the maximum for that is 4, and we do 4 plus 9. So 4 plus 9 is 13, which means that up until this point, the maximum we can get, the amount is 13, which is definitely greater than 5. So it is in our interest to keep this pair so far. Now we can forget about this 4 because we already calculated its value over here. And now at this next value number 11, again we have two choices. Do we want to keep 11 or not? So again we do the same thing. We compare 11 with whatever value we have over here. We do, first of all, we do sum of 11 plus this 5. So we do 11 plus 5. Okay, this one is 16. So which is greater than 13, which means it is in our interest to keep the value 11. So again we are going to have 16 over here. We can forget about this one because we already calculated its value. And yeah, so we are at, now the two choices we have is 16 and 13, and this value number 2, we need to check two items. So value before that, this is 16 and this one is 13. So we do 13 plus 2, 15. So far, if we decide to keep this value number 2 in our list of houses that we are planning to rob, the maximum value we can achieve so far is 15. But the thing is, we have already found a better option than this 15, and which is 16, where if we decide to rob these three houses, we will get the optimal answer. And notice that we were able to complete this whole iteration in just single we were able to complete this whole calculation in just a single loop, because we were keeping track of whatever the elements we have calculated so far, which is the exact use of dynamic programming. And we are not using more than one element at any given moment, which means that our solution is actually quite helpful and very perfect. So let's calculate the time and space complexity, and basically this would be the optimal solution. So time complexity, as you have guessed it correctly, it's actually big O of n, because we are completing everything in just one single iteration. We don't need to do multiple rounds of checks. And the space complexity we have is actually big O of 1. It's actually constant time, because notice that at any given moment, the maximum value we were keeping track of is just couple of elements. And we kept on updating our elements, that whatever we are keeping track of, which means that we are not using that much space. We are not creating an additional array to store all the values. Okay, let's create two elements. We'll name it rob1 and initialize it to 0, and we'll create a rob2. We'll also initialize it to 0, and we'll have another variable. We'll just name it max to keep track of maximum element that we have calculated so far. And now let's run a for loop. Inside the loop, first of all, we'll calculate that whether we have achieved the maximum value or not. So max would be
So whatever value we have at rob1 plus whatever value we are currently at, so this is one option, or whatever the value of rob2 we have, because notice that the rob2 element is actually right adjacent to this ith element. And now we need to update the values of rob1 and rob2. So rob1 will actually become whatever value of rob2 we had, because we are updating it every single iteration, and rob2 will actually become the maximum value we have found so far. And yeah, I think this should be our solution, and at the end we will return the max element. So let's try to run this code. Okay, now our solution seems to be working. Let's try to submit it. Oh, okay, yeah, our solution is actually runs in 0 millisecond, and it's 100 times faster than all the other solutions. But the thing is, this is not true, because we are given a limited number of test cases. We are computing everything in just a constant time, so that's why it's showing us 100% faster. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important problem, house robber 2, and this is actually an extension of original house robber problem. I have already solved the house robber problem over here, so you can check out that video, and I highly recommend that you check out that video before coming on to this problem. Typically in any interview, this problem is actually going to be asked as a follow-up question after they have originally asked this house robber problem. And that is why if we see the number of companies that have asked this question recently, it's actually quite small compared to what we are used to seeing for the other companies. But the thing is, still Amazon and Google have asked this recently, even Microsoft asked this just a little bit sometimes back, and also a few other companies have asked this. So this is a lead code medium problem, and basically the problem statement is saying that we are professional robber and we are planning to rob houses along a street. Now the catch over here is that all the houses in this given street are actually arranged in a circular fashion, and also there is one more constraint, that we cannot rob two houses that are adjacent to each other. If we rob two houses that are adjacent to each other, basically police is going to be called and we will be caught. So this is a constraint that we have to look into, and our motive is to collect or gain or rob as much money as possible without being caught. So let's try to see a pictorial representation. So basically all the houses in the street are actually placed like this. So suppose if we consider that this is our first house, actually the first house is also neighbor of the last house in the given street, because all the houses are stored in a circular fashion. And now since the houses are stored in a circular fashion, that is one more thing that we need to consider. And also we cannot rob two adjacent houses. So suppose if we decide to rob this house, we cannot rob this house or we cannot rob this house. So the first example we are given is the houses are placed like this, and these are the amount of money that is at each house. So basically, since there are only three houses, we can only rob one house, and we need to select the house with maximum money. So it's pretty simple over here, that if we select this house, we get the maximum money, and if we rob the house with value number 3, we can't rob these two houses because they are adjacent to each other. In the second example, the houses are stored like this: 1, 2, 3 and 1, and the most amount we can collect over here would be if we rob this house and this house. So in that case, the amount of money we would collect would be 4, and we won't be able to rob these two houses because they would be adjacent to each other. So we already know the brute force approach. Basically the brute force approach is to make every single pair and check out all the possibilities to see how we can find the answer. But the thing is, there is no point in exploring brute force approach over here. I'll directly go to the most optimal solution that we are going to achieve using dynamic programming, because this is an extension of house robber 1.
if you want to get more information about the approach, you can check out that video first. So for the optimal solution, we are going to use a custom example, and this is very important to use custom examples because it shows that you can create test cases on your own, and this is a really good skill to have in actual computer world. So suppose the number of houses we are given over here are in this fashion, and let's try to draw them in a circular manner. Now basically we can use the same solution we were using in house robber 1, because remember in house robber 1 what we were doing, we were just simply going through whatever the input we had, and we were just keeping track of what is at any location, what is the maximum amount of money we can rob up until this element, by checking the previous values. We are essentially going to do the same thing over here, but just in a little bit different manner, because in the house robber 1 problem we were considering the whole thing because they were all the houses were placed in a straight line, so we were able to consider them like that. The thing is, over here the additional constraint is that whatever the last amount or the last house is actually neighbor of the first house, which we can see over here that these two houses are neighbors of each other, which means that if we at any point decide to rob this house, we cannot rob this house, or vice versa, that if we decide to rob this house, first house, we need to make sure that we do not rob this house. So the answer is actually quite simple. Rather than treating this as a circular street, why don't we just run two functions? So basically during the first loop, during the first iteration, we are going to check the first sub problem, and let me show you what I mean. The additional constraint we have over here is that if we consider this house, it is guaranteed that we cannot use the last house, or if we use the last house, it is guaranteed that we cannot use the first house. So since we know that this condition exists, we are simply going to do calculation twice. In the first calculation, we are going to check between these houses that what is the maximum amount we can rob, and during the second loop we are going to check that amongst these houses what is the maximum amount we can rob, and then we just need to compare that what is the maximum value we have found across both the loops, and whatever the maximum value we find, we just we just submit it as our answer. So let's iterate over the entire problem. Okay, so these are the two loops that we are going to iterate over. So let's calculate the result for the first loop. So at the first position, the maximum amount we can rob so far is only going to be 1. And at the second house, the maximum amount we can rob is only going to be 2, because we cannot rob the first house. Now for the third house, we have two options. Either we keep whatever the value of 2 we have, or we keep the value of 1 plus the third house value, and we see that whatever is the maximum value amongst these two, we are going to keep that. So 1 plus 15 is going to be 16, and of course 16 is greater than 2, so we are going to say that up until this house number 3, the maximum amount we can rob is 16. Now we are at the fourth position. Now over here, the maximum amount we can rob is actually 2. We have two options. Either we can rob on 16 units, or we can do 2 plus whatever value at house number 4 we have. So 2 plus 11 is actually 13, which is less than 16. So even up until this point, the maximum amount we can rob is still going to remain 16 and not 13, because definitely 16 is greater value, so it is in our interest to keep this value 16. Now again we are at this position 3, and also notice that at any given location we are only considered with values that are of previous two houses that we have calculated over here. We don't need to consider all the values because we are already adding them up and we are only keeping the maximum values. So this works in our favor. So at value number 3, the maximum we can achieve is either 16 plus 3 or 16 by itself, which is this 16 or 16 plus 3. So of course 16 plus 3 is going to be greater, so we are going to store 19, and we don't care about these values anymore because we already have the latest values so far. Now at value number 6, the maximum we can find is going to be 16 plus 6 or 19. We need to select whatever is greater. So 16 plus 6 is 22. This is the greater value, so we are going to keep this and we don't care about 19. So we can see that at the end of this first loop, the maximum value we have found so far for this particular set of houses is 22. Now let's repeat the same process for the second loop. So in the second loop, for the first position, the maximum we can rob so far is 2. At the second house, the maximum we can rob is 15. Now over here, the maximum we can rob is either 2 plus 11, which is 13, or 15. So of course 15 is greater, so we are going to keep 15 over here. Now at this position number 3, we can either do 15 plus 3 or compare it with 15. So 15 plus 3 is 18, so we are going to keep 18 over here. Now at this position, we consider these two values. So either we do 15 plus 6, which is 21, or we check with 18. So 21 is greater, so of course we are going to keep this one. And now at this last position, we check that whether 21 or 18 plus 10. So of course 18 plus 10 is 28, so we are going to keep that, and we do not consider about 18. So after this entire loop, the maximum value we have found so far is 28, and the maximum value we had found over here was 22. So our job is pretty simple. We just need to see that whichever value is actually greater, we simply return that. And in this case, 28 is greater than 22, so 28 would be our answer, and we just return that value. This is a very good solution. We are building it on top of whatever we have solved for house robber 1, and because we are basically using the same solution, we are just changing the scope of up until what points we are using this solution. So just keep that in mind. And if we calculate the time and space complexity, the time complexity for this one is going to be big O of 2n, because we are running two loops, 0 to n minus 1 and 1 to n. So if we generically mention this, it actually becomes big O of n. And if we calculate the space complexity would be big O of 1, because we are, apart from storing couple of parameters, we are not using any additional space. So that's why we are able to run this in a constant time. Constant space. Okay, let's start creating parameters. So we are going to need two parameters, rob1 and rob2, and we are going to initialize both to 0. We will also need two parameters to store two maximum values, so we'll name them max1 and max2, and max1 will initialize it to the 0th house, and max2 we can actually initialize it to 0, because we are not going to consider the first house, and we are keeping the max1 as 0 because in case we are given the condition where we only have one input, so we can simply return that. Now let's run a for loop starting from the first house, so I equal to 0 to I is less than length minus 1, I plus plus. Okay, over here we are going to calculate max1. So max1 would be maximum value amongst rob1 plus the current number we are at, or the value of rob2. And we also need to update the value of rob1 and rob2. So rob1 would actually become rob2, and rob2 will become the maximum value we have found so far. Now once we are done with this loop, we need to reset the values of rob1 equal to 0 and rob2 equal to 0, because we are going to use them again in the second loop. And we are going to create another for loop, I equal to 1, and we are going to set up I is less than, so nums dot length I'll plus plus. Okay, and essentially we are going to use the same conditions. By the way, this would be max 1. We are going to use the same condition, so we can just reuse the code, and we are going to, rather than calculating max 1, we would be calculating max 2. So let's do that. And after the second loop, we simply need to return whatever the maximum value we have found amongst max 1 and max 2. And this should be the solution. Now notice that I am running 2 loops over here, but the thing is, an efficient way to do this is to create a function, and function would intake the parameters like start and end value, and you can just repeat this process. So that would be an efficient way to do this code as well. Let's try to run this. Okay, seems like our solution is working. Let's try to submit the code. Hello friends, we are still not employed by FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code problem, unique paths, and as you can see that this question has been asked in Google, Facebook, Amazon, Apple, Microsoft, Bloomberg, all huge gigantic IT companies. So I highly urge you not to miss this video and try to understand the problem as thoroughly as possible. This is going to be the framework for the video. We are going to understand the problem. We are also going to find a primitive approach. We are going to find the optimal solution, and we'll write a Java code for the optimal solution. This is a lead code medium problem. We are given that there is a robot in an M cross N grid, and robot is initially located on the top left corner. Now robot tries to go to the bottom right corner. So this is the last place where robot wants to reach. And at any given moment, robot can only make one move. It can either go down or it can go right at any point in time. No other ways it can make. So in the problem, we are given this M and N, and we need to find that how many distinct unique paths can robot take to reach to the bottom right corner or its final destination. So suppose our given M is equal to 2 and N is equal to 3. If suppose our M is equal to 3 and N is equal to 2, this is one of the test cases. So if we draw it on the board, it would look like this. This is where the robot is initially, so I'll just mark it as R, and this is the destination that robot wants to reach, the bottom right corner. Now we know we need to find that how many unique paths exist. So let's see that how many unique paths can we make. And at any given moment, robot can either go on the right side or down. It cannot make any other steps. So let's see that what are the possibilities. So this is one possibility. So this is one path. I'll just mark it somewhere. Now this is second path. I'll also mark it somewhere. So this is second path. So have we exhausted all possibilities? No, there still exists a third path, and the third path is like this. 1, 2, 1. And apart from these, we cannot make any more paths. So essentially we are exhausting all the possibilities, and we can return that for this given M and N, the number of unique paths can be 3. Now I hope that this makes problem statement more understandable. Over here initially we are given an example of M is equal to 3 and N is equal to 7. And the number of unique paths they get is 28. But the thing is, this would be such a long example, so I'm not going over it. Okay, let's understand this with a custom example. So suppose our M is equal to 3 and N is equal to 3. So we would have a grid that looks like this. Here, this is our robot, this is our destination. Now we are going to calculate that in order to reach to any element, how many unique paths we can take. So suppose if we want to reach to this element, how many unique paths we can take? We can only take one unique path, and that would be to take this right step from here. We cannot take any other step. Same goes for this element, that we can only have one unique path, and that would be to take 2 right steps from here. We cannot reach to this point any other ways. Same happens for these 2 elements as well, that we can only take 1 step down or 2 steps down in order to reach to these 2 elements. The thing is, there cannot be any other unique path if we want to get here. But the thing is, when we get to this middle points, something interesting happens. And the interesting thing is,
Suppose we want to reach to this point, how many unique paths we can take? Well, we can take two unique paths. We can take one unique path to reach over here and then over here, or we can take one unique path to reach over here and then again reach over here. So we can say over here we took two unique paths. But the thing is, if we just see that what are the entry points to get to this point, actually there are only two entry points to get to this point. One entry point is that we can, if we somehow get to this point, we just take one step downwards, we come over here. Or if we somehow get to this endpoint, if we take one step on the side, we reach over here, which means that whatever the unique paths we have at these two locations, if we just sum these two up, it will give us the number of unique paths we can take to get to this point. So let me show you by another example. Now again, let's consider this element. So in order to reach to this element, there are only two ways we can reach to this element. We can either take one step from here, or we can take one step from here, which means that whatever the number of possibilities we have over here, that once we get to this point, we will be able to come to this unique path. Okay, so that is a given. Same goes over here, that no matter how many number of possibilities we have to come to this point, if once we are at here, we are guaranteed that we can come to this point. So in order to reach to this point, the only possible ways are this one and this one. So if we sum these two, we will find the number of unique ways we can reach to this element, and in this case it would be 3. If we continue down the same path for this point, we can take 3 distinct paths to reach over here, and in order to reach to this destination D, we can take 3 plus 3 6 unique paths to get to here, and this actually becomes our answer. Okay, so based on our previous explanation, we know these things. So if we see, now we need to see that how can we use dynamic programming to solve this problem. And the reason we are choosing dynamic programming is because at any single location, we are computing that whatever the previous two results that we have already calculated, and we are using them to calculate the next values. So that pretty much indicates that we need to use dynamic programming over here. Now let's take a 2 by 2 matrix, and we'll just provide the index values. So index values would be 0 1 2 0 1 2, and we would name this matrix as DP to refer dynamic programming. Now the thing is, if we want to find out the value at this position, we know that it would be sum of these two elements. So mathematically we can write them like this, that DP of 1 1, because this is 1 and this is 1, is actually equal to dp of 0 1 that we have already calculated, which is this value, plus dp of 1 0, which is this value, and sum of these two will give us this value. So generically we can actually write them like this, that at any given location, dp of m and n would actually become dp of m minus 1 n plus dp of n and n minus 1, and this would be our recurrence relation for dynamic programming. And I already explained that why are we choosing dynamic programming, and our aim is to find that how many distinct ways we can reach to this destination. So this destination would actually become dp of 2 2 over here, and if we compare it with whatever m and n is given, this actually becomes the value over here. This would become the dp of m minus 1 and n minus 1. So we start our calculation like this, and eventually we would reach to this point, and we just need to return whatever we have found over here, and this would be our solution. So we can just create two loops. One loop iterate over the column, one loop iterates over the rows, and eventually we will reach to this endpoint. We return this. This becomes our solution, and this is a very efficient dynamic programming solution. Any FAANG companies, Facebook, Google, Amazon, whatever, they would be happy to hire you immediately. So now let's see that what would be the time and space complexity. So time complexity would be big O of m times n. because we need to iterate over this entire grid. So that's why it's big of m times n. And space complexity, remember that we are creating this additional DP array which is 2 by 2 matrix, and we are giving the size as m and n. So space complexity would also be big O of m times n, and this would be our solution. Now let's move on to coding. Okay, first of all we'll create a two-dimensional array and we'll name it as dp, and we'll provide the length as m and n. Now we'll have to create our base case, so we'll fill our two-dimensional array, and this is the way to fill a two-dimensional array. And over here now we'll create two for loops, and we'll start with I is equal to 1 and j is equal to 1, because we already have cases for 0. While I is less than m, I plus plus, j is equal to 1, j is less than n, okay. Now we will provide our recurrence relation. So dp of I and j at any location is equal to dp of I minus 1 j plus dp of I j minus 1. And yeah, this is pretty much it. This should be working. So now let's return dp of m minus 1 and j n minus 1. Let's try to run this code. Oh, it should be arrays.fill, small error. Looks like our solution is working. Let's try to submit the code. Okay, our solution is actually runs in 0 millisecond. It's 100% faster than all the other submissions, which is pretty good. And I'll be posting this in the comments. You can check it out from there.
Hello friends, I am a cloud solutions architect who like to solve lead code problem, and today we are going to solve a very interesting lead code problem called Pascal's triangle. Now if we see some of the popular companies who have already asked this question, there are companies like Amazon, Bloomberg, Google, Apple, Microsoft, Goldman Sachs, TCS, Uber, Facebook and Infosys. So that's why I am paying my utmost attention. I hope you also enjoy the video. So this is a lead code easy problem and also a very well-liked problem. Basically, we are given an integer array called number of rows, and we need to return the first number of rows of a Pascal's triangle. Now, the biggest question in this problem is, what the heck does this Pascal's triangle means? They have actually drawn a diagram over here, and you can try to understand it using this. But I'm actually going to show you an animation that what a Pascal's triangle is. Okay, so now we are actually trying to create the Pascal's triangle, and for that I found a definition online. If we read through the definition, this is saying that, okay, in order to build the triangle or Pascal's triangle, basically we need to start with 1 at the top, and then we need to continue placing numbers below it in a triangular pattern. Okay, that's a given fact. Second thing it says is that each number in the numbers is the combination of the two numbers above it added together. Let's try to understand this with an example. So over here we are trying to build a Pascal's triangle with 6 different rows, and I have drawn 6 rows over here. After marking their numbers, based on this definition, okay, first value has to be 1. So we are starting the first value as 1, right? Now what it says is that every single number is the number that is combination of two numbers directly above it. Now if we see this first box is only connected with one box at the top. So definitely the sum of this value is going to be that value by itself.
So this is also going to be 1. Same way this value is also going to be 1 because both of them are only connected with one box above it. That is the key phrase, that one box above it. Same way, if we try to take a look at this box, this is also connected with just one box. So because of that, we are also again going to add 1 over here. But when we reach to this particular middle box, things become interesting. Because if we see this above part is actually connected with two different cells. So because it is connected with two different cells, we are actually going to do sum of these two. So 1 plus 1 is going to be 2 over here. And again, remember, this 1 plus 1 is coming by sum of these two values. Why? Because this particular cell is connected with both of them. Now, if we go back, okay, this one will always be 1 because there is only one element. Now, again, this is also going to be 1 because it's only connected with just one element. But in this case, this particular element is again connected with two elements. So we are going to do the sum of it. So if we do sum of it, we get the value 3. Again, this is also connected with two elements, so sum is going to be 3, and this is only connected with one element, so sum is going to be 1. Same way we keep on repeating for the row number 5. So again, this is going to be 1. Now this is going to be sum of these two, which becomes 4. Now this particular element is going to be sum of these two elements, which is going to be 6. This element is going to be sum of these two, which is again going to be 4, and then again 1. Keep on repeating the same process, and this is how all the rows are being formed. And this is a Pascal's triangle. So in this case, we created a Pascal's triangle with 6 different rows, and we need to provide this as the answer. So as an input value, we are only given this element, that how many numbers of rows we need to create, and in the answer we need to return this one. And now the answer for these is needed to be written in a specific format, so that our program can understand. And the format looks like a list of lists. So first we create an array list, and every single value represents all the values inside this particular row. So currently the first row only has one element, so we are only going to add one element over here. Now for the second row, it has 2 elements, so we are going to add 2 elements over here. Again, for the third row, it has 3 elements, so we are going to add all 3 elements over here, and so on and so forth. We keep on adding all the values, and in the end we return the answer. And this is the answer that is expected in this case, right? Now, basically, I think this makes understanding much more clear that what a Pascal's triangle is. So now I have created a Pascal's triangle that is needed for like 7 rows, right? And for 7 rows, definitely I already showed you that how we are populating all the answers. That first this value is 1, this value is 1, 1, then again this value is 1, 2, 1. Okay, so this is the Pascal's triangle that we can create for 7 rows. But if you observe the answer, basically, first of all, we need to define that how the answer is being generated over here. The answer for any single cell is dependent on its like further value. Same goes for any single possible cell. That cell is made up or comprised of the 2 cells that are exactly above it that it is being connected to. Now that is okay. That is one property. Second property is that in order to generate any single cell, how can we find its value? Well, we can simply find its values based on that if we have some way to store the value of the previous row. If we have that value, definitely we can able to generate the answer. And the thing is, because any single result is based on the results of its previously computed values, we are actually reusing the same value that we have already used, which means we are actually going to use the most beautiful concept inside the computer programming, which is dynamic programming in this case. Now for this dynamic programming, what we need a base case. So base case, what is going to be, that is already given in the definition of Pascal's triangle, that the first triangle is always going to be 1. So that is okay, that is a given fact, right? That this becomes our base case. Now based on this base case, I just showed you that we are able to generate any single triangle of any single length. In this case, the length was 7, so we were able to quickly generate that. So the logic we are going to use in this case is that, okay, first we calculate the first value, we get the answer as 1, right? We store that answer. Now for the second column, okay, first, what are the things we know about the second row? The thing we know about the second row is that there are going to be 2 elements, right? Now for this 2 elements, what is the thing we have? The thing we have is that we have one element that is present before that. Okay, so in this case, the first element is only possible to be connected with just one element. So since we have already saved that answer over here,
we can simply leverage that. And same goes for the second element, that can only be connected with one element, so we can also store that answer over here. Okay, now we are at the third position. Now for the third position, what is the logic? So the first value is always going to be 1, so we can by default mark the first value to be 1, and also the last value will always be 1 as well, so we can also mark the last value to be 1 as well. Now for the middle values, what we are going to do is, okay, so currently if we see the index position of this middle value, the index position is going to be 1. Why? Because there are 3 elements. So in a typical array, the index position is going to be like 0, 1, 2. So this is like the first index position. Now we already know we are trying to populate this third value, and for the third row, first one value is 1. That is a given fact, right? Now for the second value, or the value located at index number 1, how can we calculate that? We can simply calculate that, okay, this is index number 1, right? So this index number 1 has to be connected with the previous value of index 0 and index 1. Then that you can see over here, that this was connected with like index value 0 and this was in an index number 1, and that is how this is connected. So all we will have to do is just do the sum of them, and that we can clearly found from the answer we have already stored over here, so which is 2, and again the next value we will get is 1. Now we need to create the fourth row. Okay, so for the fourth row, I'm not going to show you in the triangle, I'm just going to show you in the answer that how we will be able to generate that. So first value is 1, that is a given fact. We are trying to find 4 elements in this case. Now for the second element is located currently at like first index position, right? So because the index position is first, which means we will have to do sum of 0 and first index position, which is these two values. So in this case, the answer is going to be 3. Again, now for the second element, so this is like the third element inside this fourth row, and the second element in terms of like index value. So okay, the index value for this one that we are trying to find is 2, which means we will have to do sum of 1 plus 2. So okay, what is the value located at index number 1 in the previous value, which is this one, 2. Okay, and what is the value located at index number 2 in the previous value, which is 1. So 2 plus 1. So we get the answer as 3. And since we are only trying to populate 4 values, the fourth value has to be 1, because that is we already established that. So this is basically the simplest logic that we are going to use in order to populate our answer using dynamic programming. If you still don't understand the concept, I suggest you try to draw like any single Pascal's triangle. It's pretty easy to draw, and then you would be able to calculate the values. And basically using the dynamic programming, this problem can be solved really easily. If we see time and space complexity, in this case, the time complexity is actually going to be big O of n square, where n is the number of rows that are given, and that is the best we can do. First of all, we are going to create a list of lists to store our answer. Now we are going to create our base case. So base case is that always the first value is going to be the 0, like the 1. And so what we are going to do is we are going to add a new entry over here. Now we have created our base case, right? Now as an input, we are given the number of rows we need to perform. So what we are going to do is we are going to run a for loop, and inside this for loop, we are going to run up until we are going to start from row position number 1, and we are going to go up until the point where we reach to the number of rows that we need to reach to. Now for every single row, we will have to create a new array list that we need to input. Also at the same time, for any single list, we will actually have to require the previous list that we have calculated, right? So we are also going to create a new list to store the previous list, and we are going to name it as previous list. Now we have our value set up. Now first of all, for the new row that we are trying to add the entries, we are actually going to assign the value 1 into it. And now we are also going to run another loop. For this another loop, okay, let's just name the parameter integer j, and we are going to start it from position number 1. Why we are starting it from position number 1? Because we already filled out one value over here, and this is going to run until we reach to the value of this row that we are trying to reach. And now the core logic is actually quite simple. All we are going to do is for this current row, we are actually going to add the value, and we are going to add the value based on the result of the previous list that we got, and we are actually going to like get it using the j minus 1 value, and plus we are going to get it like the jth value. And basically this is the whole core of every single thing that we are trying to achieve. Now once we get out of this loop, remember the last value also needs to be 1. So again we are going to do that. In the end, all we need to do is just add this new row, that new list that we have created in our answer. So let's do that. And in the end, once we get out of the loop, basically our answer should have been populated, so we can simply return the answer. Now let's try to run this code. Seems like our solution is working as expected. Let's try to submit this code. And our code runs pretty efficiently, and it beats almost like 82% of the cases. Also in terms of memory consumption, it beats a lot of cases. Now I forgot to mention the space complexity for this one. The space complexity is actually going to be constant space. Why? Because anyways we are creating like a new answer list to store the answer, and we are only creating like couple of temporary lists over here. We are not doing anything extra, so that's why the space complexity is going to be constant space. And again, as always, I will be posting this solution in the comments, so you can check it out from there. Thank you.
Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to work upon a very important dynamic programming problem, coin change, and which in my opinion everyone should do it at least 2, 3, 4 times until you get a real grasp of the concept on how to solve it. And let's understand the problem statement. We are given an integer array of coins representing coins of different denominations, and we are also given an integer amount that represents the total amount of money that we want to generate. Now we need to return the fewest number of coins that we can use to make up to the amount that has been provided over here. And if the amount of money cannot be reproduced, we need to return -1. Let's try to understand this by an example. So in the given example, the number of coins we are given is 1, 2, and 5, and the amount we are given is 11. So based on the example, we can clearly see that the most optimal way we can create this 11 is by using 5 plus 5 plus 1. So in general, this sums up to 11, and if we see the number of coins, we are actually using 3 number of coins to generate this value. If we look at the second example, basically we are only given 1 coin, the value number 2, and the amount we are given is actually 3. So no matter how many times we use the number of coins 2, we cannot generate this amount 3. So in that case we need to return -1, while in this case we would be returning 3 because we are using these 3 coins. So once we have this clear, now let's try to understand that what could be the different approaches we can take to solve this problem. The first approach that comes to our mind is actually to use a greedy approach, where whenever we are given the number of coins, so let's take one of our own custom examples, and we also need to keep in mind that whenever you are solving or giving any FAANG interviews, make sure to have your own custom inputs, because FAANG companies really like this kind of stuff, and that shows that you are able to think outside of the box, and you can also create test cases on your own. So suppose we are given an input like this, and the amount we need to create is actually 8. So in our greedy approach, basically we at any given moment for the given amount, we will take the biggest coin that is smaller than this amount and keep repeating till we reach this amount. Now let me show you that why this approach won't work, because if we see here, the amount we have is 8, and the biggest denomination of coin we can create that is lesser than 8 is 6. So if we take this, so let's create our answer where we keep track of how many coins we are using. So we use 6 over here, we take 8 to 6, so we subtract 6 minus 8, we get the remaining value is 2. So since the remaining value is 2, we cannot use these 3 coins anymore because they all are greater than 2, and if we were to subtract this coin from 2, our result would actually become negative. So we cannot use that, but we can still use value number 1. So if we do that, and if we use the coin number 1, because this is a greedy approach, so we will add the coin number 1 to our answer as well, and so now the remaining value will be 1. So again we cannot use these 3 values, but we can still use 1, so we will use 1. The remaining amount is 0, which means that we have reached our total amount of 8, and we would add the value number 1 over here. Once we do that, essentially if we calculate in the answer, we are using 3 separate coins to reach the amount 8. So our answer would be 3 in this case, and we would return 3. But notice that this answer is actually not the lowest number of coins we can use. Actually, if we just use the coins 3 and 5, we can simply create this value 8, and our result in this case should actually be 2, not 3. So greedy approach doesn't work at all. Now let's see what could be the next approach we can take over here. We are given an input like this, and we need to reach out to a particular amount 8. So at any given point, if we basically start calculating from 0, and we will keep on making choices based on the number of coins we have until we either reach to this value 8, or our choices actually becomes greater than 8. Until these two things happen, we can keep on making choices given our coin denominations, and based on that we can actually create our own decision tree. And in the decision tree, whenever we reach at value number 8, we will keep track of the value, keep track of the path, and based on that path we can calculate that what are the minimum number of iterations we have to make. So initially we are at 0th position. So from 0th position we have 4 options that we can take. So let's make these 4 decisions: 1, 3, 5 and 6. Now at every single decision we still have 4 more decisions that we can take to reach out to this value 8. So again at value number 1 we still have 4 more decisions we can make. So let's do that. And again at every single iteration we still have 4 more decisions, and with every decisions we come closer to this value number 8. So initially over here complete 8 were remaining. Over here we are only dealt with creating the value 7, because we already used 1 coin. The remaining value would be 7. So over here the remaining value would be 1. Over here the remaining value would be 2. Over here the remaining value would be 4, and over here the remaining value would be 6. And suppose we continue on this path again, we would still have 4 choices. And notice that the remaining value we wanted to create was 6, which we are able to achieve over here. So the sum for this particular path, 1, again 1, and then again 6, is actually 8, which means that we have found a potential route. And if we see the number of coins we had to use 1, 2 and 3 coins. So current amount, current answer we need to return is actually 3. And since we have found this route, all the other routes, if you see, the values would not reach to 8, and we can cancel out these values. And basically because if we keep going on, we will still have to make more decisions, and the number of route will definitely be greater than 3. So we can start eliminating these routes, and we have one potential route over here. Again, if we keep on going down this path of 3 and keep making more decisions, we would end up with an result that would be greater than 3, or we would not reach 8 at all. So we can ignore this. Again we can ignore this from 5, and at 6 we would still find a route something like this. where, because notice even at 6 we still have 4 decisions we can make. So we can we can choose either 1, 3, 5 or 6, and notice that only one is remaining over here and we can select this one. So we would have another potential route starting from 1 going to 6 and then again going to 1, that sums up to 8. But again for this route as well we need to use 3 coins, so our answer will still remain 3 and it won't be changed. But this is where we find another answer. And now we have exhausted all the possibilities from value number 1, so we can just ignore all of this. Let's get rid of it, so we have something that is more clear and not so much congested. Now let's try to see that what could be the possibilities from this value number 3. So even at value number 3, the remaining amount we have would be 5, and at value number 3 we still have 4 more possibilities that we can choose from: 1, 3, 5 and 6. And notice that in all of these these 3 possibilities we would not reach 8. So we would not reach, basically the remaining value would not be 0, which means, but if we get down over here 5, over here only 5 is remaining and we directly have a coin 5 present at the decision tree 3. And if we calculate the route would look like 1 and then 2. So basically we are only using one coin over here and we are using second coin over here. So we are only using 2 coins to reach to this value 8. So we can simply update our answer that we have found a new minimum value that can come up as our answer, and we can set the value as 2. Now we can continue to search and keep on making more decision trees, and even for those nodes we will continue to making further down decisions to see if we can find a better answer. But we won't be able to find a better answer than 2, and eventually we would have to return this value. So this solution, in a way, it works, and it works as expected. At least we are getting the answer. But the issue with this approach is that time complexity is actually so bad. It's not even in polynomial time, it's simply in exponential time. And the time complexity, suppose the amount we are given, if we consider it as m, essentially until we reach this amount m, we are at every time keep on making multiple decisions based on the number of coins that are given. So we can compute the time complexity as big O of m to the power of n, where m is the given amount and n are the number of coins that are present at any given moment. This is such a bad time complexity that we, even if we ask NASA to run this command, they won't be able to do it more than up to a certain values, and we need to find a better approach. And in the optimal solution, we are simply going to use just 2 golden words: dynamic programming. And let me show you how we can solve this via dynamic programming programmatically. And we are just like a rational person. We are just going to think it in terms of intuitively, that if we are given this problem just to solve on a pen and paper, how we are going to do it. And one approach is that we can basically start from the value number 0. We can keep on reaching towards the amount we want to reach out to, and for every single element that we have found, we will find that for 1, 2, 3, 4, how many number of coins it took us to generate that particular amount. And once we are sure with this value, whatever value we have generated, the amount for 1 or amount for 2, we would be able to use this later down the road. And let's take an example. Let's continue with our example and see how can we achieve that. So we are given the example 1, 3, 5 and 6, and the amount we want to generate is 8. So initially we would create an array of amount from 0 all the way up to amount of 8, and we will initialize all the values by any value that is higher than 8. So let's say 8 plus 1. And now we will start with our solution. So far all the values are actually 8 plus 1 in this amount array, and this represents that these are the number of coins that are needed in order for us to generate any particular value. Now if we just want to generate 0 coins, how many number of coins do we need? Well, answer is pretty trivial actually. We simply need 0 coins, and this becomes our base case. So now let's say for the second value, amount of 1, that if we want to generate value number 1, how many distinct coins we need. So whatever value is, we will check first of all in our coins for all the values that are given in the coin, to see if we can directly use, if the given coin is lesser than the value we are trying to achieve, can we use that coin. So since the value is 1, we can clearly see over here that this 1, if we just use one coin, we would be able to generate this value 1. So the answer in this scenario becomes pretty simple, that if we just use one coin, we would be able to generate this value. And notice that for value number 1, we cannot use any of these 3 coins because they are all greater than our value 1. So there is no point in using them. Now let's repeat the process for amount 2. So for amount 2, if we want to generate the value 2, how many minimum number of coins we need? So first of all, let's check with the first value. Okay, so coin is actually less than 2, so we can use this coin. We will use this coin. So if we use that coin, basically we have already used one coin so far, and since we use coin number 1 and we want to achieve value 2, we can say that now the value we are trying to generate is actually 2 minus 1. So again, value number 1. Now we want to generate value number 1, and if we can do either two things. Either we can go back to all these coins, again we try to generate that value, or notice this beautiful thing over here, that we have already calculated that if we want to generate amount 1, how many coins we are going to need. So why are we being so picky, and why are we doing all this extra work, and why are we making our lives miserable, our CPU's life miserable by doing all these additional calculations? Why can't we just store this somewhere, and if we have stored it, we can simply use it over here. So in this case, we can say that we have already used one coin in order for us to generate this one, and now once we have generated this one, we know that the number of coins that are needed to create value 1 is already computed. So we will do 1 plus amount to generate one coin, and this would be the answer if we want to generate the value 2 from the given coins, and this would become 1 plus 1, so 2, and this would be our direct answer. And these are the minimum number of coins that we can use to generate value number 2. The reason I'm emphasizing so much on this is because this exactly is the core concept of dynamic programming, and we have just hit a very big hammer to its head. Basically, we have said that, hey, I'm going to take this dynamic programming all the way, I'm gonna chew it, swallow it up, so it becomes a second nature to me. And now let's continue with our example. This is going to be a really long video, and I recommend that if you just understood at any point, I would just suggest you to go ahead and start skipping over. So now the value for amount 2 is actually 2. Now let's calculate for amount 3. If we look at for amount 3, we have two options. Either first of all we can start with this value 1. We'll take value 1, then again the remaining value would be 2, and we have already calculated that what is the amount that is remaining for value number 2 over here. So let's take that approach just for the sake of understanding. So first of all, we use coin number 1. So we use coin number 1, and plus the amount that is remaining is actually 3 minus 2. So we still have amount 2 that needs to be computed in order for us to achieve this value 3. So we can say that for this one, the way we can do it is one coin that we already used plus whatever the amount 2 that we need to use. And notice amount 2 has already been computed over here. So we can say that 1 plus 2 equals to 3. So if we choose one of these coins and we try to achieve the value number 3, initially we would be able to find our answer by using minimum of 3 tokens. Now again we notice that now since we have computed this coin, we notice that 3 value number 3 is actually less than or equal to this given coin 3, and we can use it to our advantage. So now we know that we want to achieve value number 3 over here. If we just use this one coin, we would be able to achieve this amount number 3, and current minimum amount that we have calculated that is that we need minimum 3 coins in order for us to achieve value number 3. So why are we using 3 coins? Because our aim is to use the minimum number of values. So we can simply just say that if we just use one single coin that is of denomination 3, we would be able to calculate the result as 3 for this amount 3, and we won't be able to do anything with these two because they are already greater than 3, so we can't make 3 with those denominations. Now let's move forward with our with the next value, amount of 4. And if we generate the amount 4, how many number of coins we need? So basically if we just take this first coin, we know that we have already used one coin, and plus we have the value remaining as amount 3. Amount 3 is already computed. We are using the best knowledge of computer processing we can, and based on that we can simply determine that, oh, and by the way this would be 1 not 3, my mistake. So we can just simply say that if we want to generate amount 4, we can do 1 plus amount 3 is already 1, so we can use 2, and this would be the minimum solution, that even if we use the first coin as 3, we would use second coin as 1, and still we will get the same answer. So I'm not going to do whole computation, but you get the idea. So for amount 4 we can say that 2 are the minimum number of coins we need in order for us to generate amount 4. If we want to do amount 5, how many coins we need? And the answer is pretty simple. We already have this 5 present over here, so we can just simply write 1, and notice that we are going to check all the coins, and when we get to 5, we will be able to say that this is the minimum number of coins we can use. Next is amount of 6. If you want to generate amount of 6, again the answer is 1, because we are already given a 6 over here, and we are going to check through all the coins that are less in the value of whatever the amount that we are trying to calculate. Now let's calculate for amount of 7. If we are calculating for amount of 7, and if we check for the first coin is actually 0. So basically we can just simply say that the first coin is actually 1. So basically we can just simply say that we have already calculated the one coin, plus now we need to calculate the amount 6, because 7 minus 1 is equal to 6, and we already have the result for amount 6. So we can just simply write that we need at least 2 coins in order for us to generate the value number 7. And now let's try to calculate our output that we have already given, that we need to calculate the 8. So if we want to calculate amount 8, and based on this table, it becomes pretty simple. Initially, so first of all we will calculate this with value 1. So basically we would be doing the calculation something like one coin that we have already used plus amount of 7, and we know that amount of 7 from our previous computation is actually value number 2. So we will do 1 plus 2 equals to 3 for this amount 8 that we are trying to calculate. But can we do something better? And remember that we are going to check all the coins. So because we are going to check all the coins, when we get to coin number 3, our solution would be that we have used one coin, and that is the coin value is 3, and because we have used 3, now we need to generate the amount 8 minus 3 equals to 5. So we can say that we used one coin to generate the value 3, and now we need to generate value 5 in order for us to achieve this amount equals to 8. So if we do 1 plus amount of 5, what is the answer? And the amount of 5 is already calculated over here as 1. So we'll just simply use that value and we'll do 1 plus 1 equals to 2, and we will carry on with our computation with this value value 5. Again we will find the answer 2 because we'll do 5 plus 3, and when we get to value number 6 we will again find the answer to generate the amount 8 as 3, because we'll do like 6 plus amount of 2. So the minimum number of coins that we can find in order for us to generate value number 8 is actually 2, and we can simply return this value 2. Now notice that we also have to take care of the scenario where we cannot create the amount based on the given coins, and if we cannot create the amount at the end of our computation, the value for amount would amount of any given, let's say 8, that we cannot compute in this case, would actually be the value 8 plus 1, so equals to 9. Because notice that at the beginning of our array, this is how we initialize the values to, and if after all the computation we found that the value of amount is actually the original by default value that we set, which is amount plus 1, if that is the case, we know that we are not able to generate this value and we are not able to make any impact with our solution because the coins cannot generate this value. We will simply return minus 1, and this solution would work perfectly fine. This is a really beautiful solution, and if you go through with this approach in your interview, you are gonna just be very impressive candidate, and all the FAANG companies would want to hire you. So let's calculate the time and space complexity. So time complexity for this one would be actually big O of n times m. Now why n times n? Because we are running the loop to calculate the value n, and n is actually the value of this amount of whatever is given. So we are going through a loop n times, and m are the number of coins. Because notice that over here for every single element we will have to go through all the coins in order to generate the value. So the time complexity would be big O of n times m, and the space complexity would be big O of n, because we are creating an additional data structure array to store all these values, and the values we are storing up to is actually the amount, whatever amount we are given. So we can say that the space complexity would be big O of n. Okay, so let's create an array amount, and its size would be amount plus 1. We fill out all the values inside the amount as amount plus 1. This would help us determine that whether if we cannot create the value, we need to return minus 1 or not. And now we will set up the initial value for amount of 0 would be 0. Now let's create our loop. So we will start with I equals to 1, because we have already calculated the value for amount 0, and while I is less than or equal to amount. Now notice that for every single value of I, we need to calculate for all the values of coins. So we will have another loop that would iterate over coins. And first of all, we'll check that if our present I is actually greater than or equal to whatever value of coin that we are comparing it with. So if this is true, then only we will check that whether what is the amount for any given j, any given I. So we'll do a minimum value of either the value itself, so whatever value we already have, or we will take one coin of any j and we will do an amount of I minus j. And yep, this is the main logic, because in this logic we are calculating all the amounts and we are using it further down the road as well. So after this iteration we just need to check that if for any given amount, so amount of amount, if that is less than the value amount plus 1, which means that we have been able to generate this amount. So in that case we would return whatever the value we found, else we can simply return -1. Let's try to run this code. We made a silly mistake. Again. Oh, we need to check with coins of j. Yeah, looks like our code works. Let's try to submit this. And yeah, our submission is actually pretty efficient compared to others who have submitted. So I hope you like this video. It took me a lot of time to make it, and I know it was a really long video, but it was, believe me, it's equally informative. Once you master dynamic programming, you are almost guaranteed that you at least have a foot in the door for FAANG. And yeah, we are not gonna stop till we clear FAANG. See you. Hello friends, we are still not employed by FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code problem, Decode Ways, and this problem has been asked in a bunch of different FAANG companies like Amazon, Google, Facebook, Microsoft, Uber, Lyft, Apple. So I highly recommend that you focus full attention to this problem. This is the breakdown that we are going to do for this problem. We are simply going to understand the problem first. We are going to see a brute force solution. Based on the brute force solution, we are going to see that how can we create an optimal solution, and eventually we will write the Java code for that. And this is a lead code medium problem, and we are given a note that basically a message containing letters can be encoded into numbers using the following method. So A is 1, B is 2, and up until that, if we keep doing that, Z is actually 26. And we are given a string of S that contains digits, and we need to return the number of different ways we can decode it. So let's understand this with an example. Suppose our given input S is equal to 12. We can decode this in two ways. So one way to decode this would be to consider 1 and 2 as separate elements, and 12 by itself as a single digit. So this the value for 1 and 2 would become A and B using this logic, and the value of 12 would become the letter L. So we don't need to return these values, we don't care about them. The thing is, we need to return that how many different ways we are decoding this given input string, and in this case the answer would be 2. Let's take another example. So suppose our given input S is equal to 226. How many times, how many different ways we can decode this one? So one way to decode this one is 2 and 26. So that's one way. The second way to decode this one is 2 and 6. So that is second way. And the third way to decode this one, 22 and 6. And if we check out the values, so this would becomes B Z, this would becomes B B F, and this would become V F. So over here we can see that there are 3 ways we are decoding this given string. So in the answer we will return the value as 3. Now let's consider one more case. suppose the value 0 would be a special case, and there could be multiple possibilities where 0 can appear. So suppose our given input s is something like 0 1 1. So in this case we won't be decode it in any manner, because remember that our range starts from this value number 1 up until 26. So 0 is not part of the range, so we cannot begin our string with value 0 at the beginning. So this won't work. Second possibility, that 0 could be somewhere in the middle. So suppose our given input s is equal to 1 0 1, something like this. So in this case we cannot decode this in 1 and 0 1. We can't do this. Why? Because we can't decode this 0 1, because remember that in this scenario, if 0 comes at the beginning, we can't decode it. The way we can decode this is, we can consider this as 10 and this as 1. That value of 0 can appear at the end. So our input string s can be something like 2 0 0. So in this case we can decode this value 2 0, but we can't decode the 0, so we won't be able to return anything. Or our value s can be 5 2 0. So in this case we can decode this. We can decode this value 5 and we can decode this value 2 0, because 2 0 is again between 1 to 26. But if we are given something s is equal to like 5 7 0, we can't decode this, because we can decode this 5 but we can't decode 7 0, because 7 0 is not part of this 1 to 26 range. So when value 0 comes in, it becomes a little bit tricky and we have to just take care of it. For brute force approach, let's take a custom example. Suppose our given s is equal to 2 1 2 3, and we need to see that how many different ways we can decode this one. So brute force approach is pretty simple. We just take all the possibilities starting from the first value and keep moving and keep building our solution, and when we reach at the end at any given path, we consider it as a one way to decode it. So initially we can decode this as 2 and whatever the remaining value 1 2 3. We can decode this further into 2 1 and whatever value remaining, again same thing, 2 1 2 and this 3, and in the end we can decode this as 2 1 2 3. So this would be one way we would be able to decode this. So where if we treat all the values as separate entities. Now let's see, let's go back and see that can we have more possibilities. So over here we cannot have any more possibilities, because this 2 1 and 2 are already being decoded, and this 3 we only have one possibility to decode it by itself. So we don't have any possibility over here. So we go back further up. Do we have any possibility over here? So yes, over here we still have possibility that we can decode this 2 and 1 the same way we have decoded over here, but this 23 we can decode it as a single value. So of course we reach at the end of the loop. So this is one more possibility on how we can decode it. Now let's go back. So for this value 123, of course we still have more possibilities, because over here we are considering this value as 2 and 1 separately. So over here we will consider this as 2 as already being decoded, and rather than considering this as 1 as separate character, we can also consider it as 1 2, and then we can decode 3. So this can also be another way. So we'll just mark it. Okay, now we have exhausted all the possibilities over here, considering this value. If we start from this value number 2, so we come back at our main point, and let's see that what are the more possibilities we can have over here. So we can do, rather than choosing 2, we can choose 2 1 and whatever the remaining stream. So remaining is 23. Okay, now let's see that how many different possibilities we can have over here. So we can have two possibilities now. We can do like 21 2 and 3, so that is one option, or we can do 21 and 23, so that is second option. And yeah, both would be a separate ways, and apart from these we cannot make any other possibilities. So essentially we can say that there are 5 different ways to decode this 2123 string, and those 5 ways are mentioned over here. Uh, what is the problem with this brute force approach? Well, the problem with brute force approach is that actually we are doing a lot of repetitive work. How we are doing repetitive work? If you notice over here that we know that we need to calculate that for this 23 how many different ways we can compute this one, but this 23 we have already computed it over here. So since we have already computed it over here, it is not very fruitful to compute the same thing twice, and in brute force we are not doing it. So that is why our path will keep on growing and growing until we reach to our all the possibilities, which means that we are actually doing exponential work for this brute force approach. So of course the time complexity would be big O of 2 to the power n, which is really bad, and we should avoid it in all cases. And actually it can be avoided pretty simply if we just use memoization. If we just create an additional data structure, something like an array or something, where we store the value of calculations that we have already done, and if we at any point come back to the same calculation that we have already computed, we can simply return that value. So we can use something like an array or hash map. I think hash map would be more efficient in this case because we are able to look up things in constant time. And if we only apply that, we can actually implement this solution, this brute force solution, in very effective manner. We can actually use recursion because remember, at every single moment we are repeating a sub problem. So we are repeating a sub problem and we are computing that. So if we just use memoization with recursion, so for this approach, we can actually achieve the answer in time complexity of big O of n rather than this 2 to the power n, and that would be really efficient. Okay, before I go into the optimal solution, I want to show you a few observations. Suppose our given input s is equal to 7. So how many different ways we can decode it? Of course, only one way. We can just use 7. Suppose our input is 7 7. We can still only decode it one way using like 7 7, and that would be the only way we would be able to decode it. Even if our value is 7 7 7 7 7 7 7, whatever the value we have, all of these can only be decoded just one way, because all of these values, they are forming a value where we can only use individual characters. Now, what is the scenario where we can use the characters that are not individual and we can collectively use the pair of elements? Okay, now let's take one more example. S is equal to 2 1 2 3, and now let's try to see that how many different ways we can decode this one. This is the same one we have used in our brute force approach, so we know that there are 5 different ways we can decode this one. The thing is, we are going to do things a little bit differently over here. We are going to decode all of these values. So first we'll start with value number 2. How many different ways to decode this one? Only one way, and that way is 2. Now let's consider the second value, 21. How many different ways to decode this one? Well, of course, 2 values, 2 different ways, and those ways are 2 1, so that is one way, and second one is 21 by itself. And let's take the third value, 2 1 2. So there are actually 3 different ways to decode this one. So let's consider the next value as 2 1 2 3. So we know that for this one there are actually 5 different ways to decode this, and the 5 ways are, okay, you must be thinking that why am I writing all these letters? Because the thing is, there is actually a very important relationship that exists whenever we find out, whenever we add a new value to our calculation, and if that value that is being added, if the previous value of that with that particular value, if that falls between this 10 to 26, actually something interesting happens. So notice over here that this 21 came in. Okay, we are checking for this value number 21. Now the thing is, just for a second, imagine if this value was actually 27. So how many different ways would we be able to decode this one? Well, only one different way, and that one different way would be 2 and 7. So treating both values as separate values. Same goes for 28, 29, and any value above. But the thing is, because this value falls between this 10 to 26 portion, we are able to do something interesting. So notice that whatever value we append over here, there will only always be one way to decode it. I'm not talking about the value 0. Forget about 0. Apart from 0, if there was any other value, the way to decode it would be to whatever the way we have been decoding the previous value. If we just add that value, then that would be the way to decode it, which is over here. That 2 and 1, we are already decoding it with whatever value we were decoding before, and we were using that way. But the thing is, over here, this 21 by itself falls under this 10 to 26, which means it is a letter by itself. So we are able to add it to our decode list, and that is why we have 2 over here. Okay, but now the interesting part comes in. Okay, now over here we are adding one more 2, and this 2 falls between the values 10 to 26, because the appending value becomes 12. So this 12 falls between this 10 to 26. Now let's see that how many different ways we are creating the pairs. Actually 2, 1 and 2. This is same from whatever the pair we had before, just one iteration before. Okay, now this 2, 1, we already had a 2, 1 over here, and we are just appending this value 2 over here. So that is also okay, because we can append it, right? So whatever the ways we were decoding before, we are still using those ways. But the thing is, over here something interesting happens, because this 1, 2 by itself is a way to decode. We are actually able to create this 2, 1, 2 pair, which we were not able to generate over here. We are not able, I mean, we are using this 2 over here, but the thing is, we are using it for 2, 1, but we can't do anything further than that. We are already also using this 2, 1, 2 over here. And how can we say that we are using this 2, 1, 2 over here? Is because this value is basically 12, falls between 10 to 16. But the thing is, this 2 actually comes from the first value, this one. And why? Because at any given moment we find out that there exists a pair with the new value being added, and that comes between this 10 to 16. We can actually do sum of previous two values that we have calculated so far, and the sum of these two would actually give us the number of different ways we can actually decode this one. If you still don't believe me, let me show you with another example. Let me clean this up a bit. Now over here we are seeing that 5 distinct pairs are being made, and we are adding a value 3 over here, and we know that this pair 23 exists between this 10 to 26. So that is all okay, right? We know all of these stuff. Now let's see that how many different ways we are generating the pair. So one way is 2, 1, 2, and we are just appending 3. This would be the case even if the value was 2129. If the value was 2129, we would still be able to use this way, because apart from this 3, there would be a 9 over here, but that's not the case right now. But the thing is, we would still be do it. And if you look over here, this is the same path we were taking, and we are just adding one more node, so no impact on the number of results. Second pair we are making is actually 21, 2, and we are appending 3 over here. Again, that is the case over here, that we already had a 21, 2, and we can append 3 over here, so that gets taken out over here. If we had the 21, 29, we would be appending 9 over here, so that still remains common. Okay, there are no issues with that. Now next pair over here is 2 and 12. So we also have a 2 and 12 pair, and we are adding a 3 over here, which means that even if we had this 9, we would still be adding 9, and that would be it. We don't care about it. But the thing is, if we had this 9 we won't be able to generate these two pairs, because notice in these two pairs we are actually creating an additional value by the value that has added over here. And if this value was not between this 10 to 26, this value would not be able to be generated. Okay, now the question comes that we have already exhausted all the possibilities over here. So where does these two additional values comes from? Well, actually, if we look above over here, this one is actually 2 1, right? So we are also using 2 1, and we are creating a new decode node 23, and we are appending it over here. Also notice over here that this one is 2 1 and this one is 2 1, so we are appending a node over here 23, which means that at any given location, if we want to see that how many times we can decode it, if we know the information of previous two elements, and if we do sum of those, we can actually generate it. So that's why the value for this 2 1, this can be decoded 2 times. This value 2 1 2, this can be decoded 3 times. So for the value 2 1 2 3, actually this 23 falls between 10 to 26. That is okay, that is perfect. If that is the case, we simply do an addition, and if we do an addition and we just find whatever result we have calculated, and we can simply return this. This is a very effective solution. Now what could be the other case? Well, the other case could be that the new value we are adding, that does not fall between this 10 to 26. So suppose over here the new value we are adding, suppose the new value is 2128, something like this. So after adding this new value, this becomes 28. It does not fall between this 10 to 26. Because it does not fall between this 10 to 26, actually we don't need to do addition over here. We simply need to, whatever the route we can make before this element, that would be the only possibility we would be able to decode this one as well, because that I just showed you over here, that over here I was adding a 9, and because I was adding a 9, I was only able to make the new decode paths for these three elements. I won't be able to generate these two values, and this becomes our recurrence relationship, and this actually becomes our dynamic programming solution. Now let's try to solve this dynamic programmatically. We know that we care about the two previous elements. So suppose our given input is like 2 1 2 3. We initialize two values before that as 1 1. Say we have these two as 1 1. Now we check at any given location that whether the value we have, does this value with its previous value, does it fall between this 10 to 26? Okay, in this case this 2 does not fall between 10 to 26. If it does not fall between 2 to 26, we just need to take whatever we had from the previous element. So previous element over here we had 1, so we'll just take 1. Okay, now we have this 1. So again we check with its previous element that whether the value falls between this 10 to 26, the value becomes 21. It falls between this 10 to 26. So we do whatever the previous two elements were, we do sum of it. So the previous one element is 1, and the previous second element, this one is also 1. So we do 1 plus, so we do 1 plus 1. So we can put 2 over here. Now we have new element. This falls between this 10 to 26. That's good. So we do sum of two previous elements. Sum of two previous elements is actually 2 plus 1. So we can put 3 over here. Now we have this 3. Now it creates the value 23, again falls between this. So we can do sum of 2 plus 3, and that becomes 5. And this 5 would be our result. So this is a very important dynamic programming solution. And at any given moment, if we find out that suppose over here we have an value 8. Now this 38 does not fall between this 10 to 26. So it becomes simple that for this pair, the number of ways we can decode this will still be 5, because we'll just take whatever value we have calculated over here. The solution works perfectly fine, and the time complexity for this case would be big O of n, because we only need to do one iteration across all the strings, and the space complexity would in this case would actually be big O of 1. we would be able to complete this in constant space and time, because remember that at any given location we only need to keep track of just 2 elements. We don't need to keep track of this whole entire array. We just need 2 starting elements, and we would keep on iterating them over different values. So this is a very good solution. And okay, first of all we'll check that whether the first element is 0 or not. If this is the case, we can simply return 0. Okay, so we will create two parameters, 1 and 2, and we will initialize both to value 1. Let's run a for loop. We'll start the loop from first position, and we will go up until the length of the given string. We are running it from I equal to 1 because we already checked for the 0th position. First of all, we create a value current to keep track of the current element, and now we check that if the current if the new character that we are trying to add, if that is not equal to 0, we can assign the value of 1 to current. Now we also need to check that after we are adding the value at ith position, are we getting the 2-digit value between 10 to 26? So first of all, let's create a new variable called value, and we will try to calculate the 2-digit value. We check the condition. So if value is greater than or equal to 10 and value is less than or equal to 26, which means we need to update the current value is current plus whatever the value of 2 we had, because remember the value at current we are already adding it as 1. Now we need to update the values of 1 and 2. So 2 would become whatever the value of 1 we had, and 1 would become whatever the value of current we had. And yeah, I think this would be our solution. So at the end of the solution we need to return the value of whatever the current value we had, but since we are initializing current inside, we'll just return the value as 1. And let's try to run the code. Oh, we can initialize the current as 0. Let's try to run the code. Okay, looks like our solution is working. Let's try to submit the code. Okay, our solution works pretty fast and pretty efficiently. So I'll be posting the solution in the comments. You can check it out from there.
Today we are going to do maximum product subarray. This is a very popular problem on LeetCode, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, LinkedIn, Microsoft, Google, Apple, Bloomberg, Facebook, and Uber. So that's why I'm paying my utmost attention. I hope you also enjoy the video. Okay, so this is a LeetCode medium problem, and as mentioned, a very well-liked problem on LeetCode. Basically, we are given an integer array called nums, and we need to find a continuous non-empty subarray that has the largest product, and we need to return the product. We are also given the definition that what a subarray is. That is basically a continuous sequence inside any given array. And let's try to understand this problem with an example. So I have broadened this example over here, and basically we are trying to find the maximum product subarray. So a subarray that contains the maximum product. In this case, this is a negative value, and that changes the dynamic equation. So in this case, the product of these two elements, that is a subarray, is actually going to be 6. And all the other subarrays, they are always going to have lesser values than 6. So in this case, as the answer, we need to return 6, that is the maximum product subarray we can make for this given input array. And this is what the problem is asking us to do. So first, let's see that what is going to be the brute force way to solve this problem. Well, the brute force way to solve this problem is that we are asked to find the maximum product subarray, right? So if we are asked to find something of a subarray, why don't we check every single subarray,
see that what is the product we can make and find the maximum amongst that. So like do the baby steps. So what we are going to do is we are going to keep on iterating over every single sub array that we can make. We are going to see that we are going to have a variable called answer, and in the answer we are only going to store the maximum value we have found so far, and then we will keep on repeating the same process for all the remaining sub arrays, and eventually we would find a pair that contains the maximum product sub array. And in this case the answer is actually going to be this 6 times 7, that is 42, and we will have 42 populated as the answer eventually. So the brute force way is a very trivial way, but it leads to the correct solution. So if you are only looking for a solution, you will get it using brute force. But what are the issues with this one? Well, the issues clearly we can see over here, that we will have to iterate over every single sub array that is there, and that would lead us to have a time complexity of big O of n square. So which is very bad, because for every single element we will have to iterate over every other elements and then keep on repeating the same process. So the idea is to see that can we find something of a better time complexity. We can actually achieve that using the most important concept inside our computer programming, and that is called dynamic programming. Using the dynamic programming, we are basically going to have two pointers to store some critical important results, and that is going to lead us to find the maximum product subarray. So first let's understand one thing regarding what is being asked. We are trying to find the product. Now we know that for the product, suppose if all the integers are just positive integers, then basically it is the product of all the integers that we need to return, right? The thing is that is not always the case. We could encounter negative integers, and the negative integers leads to very interesting results. The interesting results are that first of all, we suppose in this case these three values, if we do product of them, okay, the product of these two is 6, and the 6 times minus 3 leads us to minus 18 to be the product over here, right? The thing is, now this value seems very low value because of the negative value. But imagine that over here, rather than this 4 being positive, if we had a negative 4, then that is actually going to lead us to have a very beautiful results, that if we do minus 18 times minus 4, the answer is going to be plus 72, and that is going to be the maximum product subarray. So you see what I'm trying to say? The moment we encountered a negative value, immediately we found it to have the minimum value, but that negative value lead us to have some better consequential results in the future. So we don't know that whenever we encounter a negative value, we don't know whether we should keep it or not. So that is a tricky part. That is why we are going to use dynamic programming, and we are actually going to use two pointers. And these two pointers are going to be that at any given position we are at inside our array, we are going to see that up until this point, what is the minimum value we have been able to achieve and what is the maximum value we have been able to achieve. Or basically what I'm trying to say is, what is the minimum product we have been able to achieve and what is the maximum product we have been able to achieve. And every single value, we could have three possibilities. So let me clean this up a bit. At every single value we are at, there could be three possibilities. Either this value could be part of a sub array that leads us to have the maximum product, or it could have been a part of a sub array that leads us to have the least value up until this point, or this could be the start of a new sub array that leads us to have a maximum product in the future. The idea is, at any given position, we are going to check three things. And the three things we are going to check is that up until this point, whatever the minimum value we had, which we have stored so far, we are going to multiply this value with this minimum value. We are also going to multiply this value with whatever the maximum value we have been able to store so far. And we are also going to compare this value by itself. So we have basically three values at any given position: the value with the previous minimum value, the value with the previous maximum value, and the value by itself. And for all of these three values, we are going to see that what is the minimum value we are able to make, we will store that. What is the maximum value we are able to make amongst these three values, we will store that as well. And eventually we would reach to the end of our loop with the maximum value we have been able to generate, and we will have a parameter called answer, and in the answer parameter, whenever we identify a better maximum value, we would populate that. So this is the approach I'm suggesting. Now let me try to go over an example. Okay, so suppose this is the example we have, and now let's try to use dynamic programming in this case with two pointers. So we are going to create two pointers called min and max, and for every single value we are going to compare it with three values that we are going to compare it with, and we are going to populate these results. We are also going to have a variable called answer. We will update it based on the maximum value we have found so far. Okay, so first value is 5. So we for all the three values we only have 5. We can't compare any with anything. Okay, so the minimum value we have found so far is going to be 5, maximum is also going to be 5, and that's it. Now this next value is 3. Okay, so now let's see that what are three values that we have to compare. So first value is 3 by itself, next value is 3 times the minimum value, so 3 times 5, next value is 3 times maximum value, so again 3 times 5. So the three values we have is 3, 15 and 15. Okay, so now the minimum value amongst these three is going to be 3, so we are going to populate that, and the maximum value is going to be 15, so we are again going to populate that. The answer so far that the best we have received is 15, so we are going to populate that. Okay, now let's get rid of this one. Now again we are at the next element, that is 1. So now the three values we have is 1 times whatever the minimum value, so that is 3, so the value is going to be 3, and the 1 times the maximum value, that is 15. Okay, now amongst these three values the minimum value we can able to make is going to be 1. Okay, so let's populate that, and the maximum value is going to be 15. The answer is going to remain the same. Now let's clean this up. Okay, now things become interesting when we reach to this value 9 minus 2. Okay, now the three values we have is going to be minus 2 by itself, then minus 2 times the previous minimum value. So previous minimum value in this case is 1. So minus 2 times 1 is going to be minus 2, and the previous maximum value. So previous maximum value in this case is 15. So minus 2 times 15 is going to be minus 30. Okay, now these are the three values we have, and now we are going to see that what is the minimum and maximum value we are able to generate, right? So currently the minimum value we are able to generate is going to be minus 30, so we are going to store that over here. Okay, and the maximum value we are able to generate in this case is going to be minus 2, so we are going to store that over here. Okay, now we are good up until this point. Now this value is 0, so the three values that we have to compare is going to be 0 times the minimum value, so that is again going to be the 0, and 0 times maximum value, that is again going to be the 0. So all three values are 0, so let's put zeros over here. Now again we are at this value number -5. So now the three values that we have to compare is going to be -5, and then both of these are 0, so it's going to be 0, 0 again. So currently the maximum value we are able to generate is going to be the 0. So we are again going to populate the value with 0, and the minimum value we are able to generate is -5. So we are going to populate the value with -5. Now the next value is 8. Okay, so now the three values we have to compare is 8. 8 times -5 is going to be -40, and 8 times the 0 is going to be 0. Okay, now the three values that we have, let's compare them and let's find the minimum value. So minimum value in this case is going to be -40, so we are going to put it over here. The maximum value we are going to have is 8, so let's populate that over here. Okay, now we are at this value number -3. So with this -3, we have three options. So -3, and then -3 times this -40, that leads us to positive 120, and -3 times 8, that leads us to -24. Okay, so now in this case the minimum value we have so far is going to be -24, which is this one, and the maximum value we are going to have is going to be 120, and this 120 is greater than this value number 15, so we are also going to update that in our answer. And now we have reached to the end of our array, so end of our dynamic programming journey. So we'll stop here, and whatever value we have found in the answer, we are going to return this as the answer. So in this case answer is 120, that is the correct answer. If we see and if we compare this to our brute force, well, essentially because we are using the beautiful concept of dynamic programming, we are completely everything in just one single iteration, and all we are doing is just storing couple of variables to store the previously calculated results and comparing different values. That leads us to have the correct answer and find the maximum product subarray in a single iteration, which is wonderful. If we see time complexity, in this case the time complexity is actually going to be big O of n, and the space complexity is actually going to be big O of constant space complexity, because apart from storing couple of variables, we are not storing any other data. So this is a very good time and space complexity to have compared to our brute force approach that had the time complexity of big O of n square, which was very bad. So first let's take care of some edge cases, that if the given number is empty, we can simply return 0. So now we will initialize a min variable, a max variable, and a result variable. Okay, so now let's run a for loop to iterate over our given nums array. Let's initialize a variable called current to keep track of the current variable we are at. Okay, now we will have to calculate max and min value. So first let's calculate max value. So this takes care of comparing three values for our max variable, and we are using math.max function 2 times because that is the way to do it. I think in Python you can do it just without using like two math.max functions. Now let's calculate our min value as well. The thing is, for our min value we will also have to use the max value, but since previously we have already calculated our max value, it makes no sense for us to use that over here. So what I'm going to do is I'm going to create a temporary variable, and this temporary variable I'm going to calculate the max value. Then for the calculation of min value, basically I'm going to use the previous max variable. Now because this is the temporary variable, we will assign this value to max. We will also have to keep on updating our result variable as well. That's it. Basically when the loop ends, we should have our answer populated in the result variable. So let's return that. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty efficiently compared to a lot of other solutions, and I would be posting this solution in the comments so you can check it out from there.
Now the next problem we are solving is called longest increasing subsequence. This problem actually has two optimal solutions. First optimal solution is a dynamic programming solution that can solve the problem in big O of n square time, and which I'm explaining in the first part of this video. Now for the same problem there is an even better solution which is very tough to understand, and that is something that is using a patient sort algorithm. So the thing is, if you are only considering and trying to learn dynamic programming, I think part 1 of the solution should be fine. If you also want to learn the optimal approach for the same problem, you can also see the part 2 of the same question. So there are going to be two solutions for the same problem, and now let's start understanding the problem statement.
Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code medium problem, longest increasing subsequence. And I have decided to break this video in two parts. In the first part, I'm going to discuss the brute force solution and an accepted solution for this problem. And in the second part, I'm going to show the optimal solution. But the thing is, the optimal solution is really difficult to achieve, and it's a little bit tricky to come up with. So let's understand the problem statement. Basically, we are given an array of numbers, and we need to find the length of longest strictly increasing subsequence. So subsequence means that suppose we are given an input like this, 1 2 4 5. So we can say that the value 2 and 5 is actually a subsequence of this given initial problem. Let's try to understand that what is the input given. So we are given over here an 18, and this example, and if we take these numbers 2 3 7 and 101, this would be our longest increasing subsequence. So if we get rid of this value 5, this would be the longest subsequence we can make, where all the values are in increasing order, and the length of all the values would be 4, which is what we need to return as a part of this output. So once we know the problem statement, let's see that what could be the brute force approach. So in the brute force approach, we are simply going to take every single subsequence that we can possibly make, keep a parameter that tracks the length of any subsequence, and eventually at the end we should be able to find a subsequence with the maximum length. So let's take a small example and see that what are the possible subsequences we can make. So suppose our given input is 5, 3 and 8. I'm only taking 3 elements because I need to show that why this approach is bad and what are the possible subsequences we can make out of this. So let's start making all the possible subsequences. The possible subsequence would be 5, 5, 3, 5, 8, 3, 3, 8, 8 and 5, 3, 8. These are the possible subsequences we can make out of only these given three problems. And if we check the length of each of them, and if we find out the property that which one is which one is a strictly increasing order, we found that this is the strictly increasing order and the maximum length we can achieve is 2. So this solution works, it works fine. The problem is that notice that we are only given 3 elements over here, and based on this 3 elements we were able to make almost 7 subsequences. Mathematically it's actually 2 to the power of 3 minus 1, and for any single given n, this is the number of subsequences we can make. So suppose we are given n values in the given input, the number of subsequences we would be able to make would be 2 to the power of n minus 1. So if we calculate the time complexity, we can just say that the time complexity is actually big O of 2 to the power of n, which is extremely horrendous time complexity, and this is exponential. So even with enough numbers, even NASA won't be able to solve this one. So let's move on to the next approach. Now we want to find the better approach, and we know that the way to do is to use dynamic programming. But the thing is, how can we identify that we need to find the solution using dynamic programming? Also, what dynamic programming solution are we going to use? So I'll be discussing both the things in next portion. And first of all, let's take an example. We'll try to see how we are going to solve it. Then I'll show you how we can determine that we are using the dynamic programming, and after that we would be implying the result, and I would be showing you the coding example. So suppose our given input is, suppose this is the input given, and we need to find the longest increasing substring. So just by looking at the given example, we can determine that the longest increasing substring actually exists between 7, 8, 16 and 27. And now let's see that how can we come up with this solution. How do we determine that this is dynamic programming? Suppose we are just given an example like this. We are just given one value, that let's say the value is 7. If we are only given 7, what is the longest increasing substring we can make? Well, the answer is quite simple. We can simply make just one substring of length 1. So this actually becomes our base case, that if we are only given one value, we are guaranteed to have at least one substring that would be the longest increasing substring that we can make. So now let's see that how can we use this logic. Say that for all the given elements, basically there exists one substring at least that is the longest increasing substring. Let's just mark all the values as 1. We know that if we are only given the value 10, the longest increasing substring we can make would only be 1. But when it comes to the second value, now we have something to compare to. Suppose the 7 value, if this was greater than 10 and we only had 2 values, we can say that at this second position, the longest increasing substring that we would be able to make would actually be whatever we have made so far plus 1. So we would have been made 2, but over here that's not the case, and over here the value 7 is actually less than whatever we are given the value before that, which means that the longest substring we have at the value 7 would also be 1. So this would be true in this case. But now when we come to 8, we have two possibilities. What are the total substrings we can make up until this point, up until 8? Okay, so for this value 8, what is the one thing that we can determine? We can basically determine that there are 3 possibilities of the substrings we can have and we can compute. One possibility is we could have a substring like 10 and 8. Second one is we could have substring 7 and 8, and third one is we could have a substring 8 by itself in case if all the values before 8 are actually greater than 8. So in this scenario, from 10 to 8, we know that 10 is already greater than 8, so we cannot create a substring over here. So let's ignore this scenario. For the second scenario, 7 to 8 actually this is a valid increasing substring because 7 is less than 8 and it comes after it. So what we can determine is that the longest increasing substring we can make at value number 8 would be whatever the longest increasing substring we have made up until this point. So whatever the longest increasing substring we have made for the value number 7 plus 1, because 8 is coming after 7 and 8 is just one step after it. So we can say that longest increasing substring at value number 8 would actually be whatever we have found up until longest for the longest increasing substring of 7 plus 1. And this is how we can determine that this should be solved as a dynamic programming problem, because in dynamic programming basically whatever calculations we make in the past, we keep track of them in some way, either through an array or storing them in variable somehow, and based on those results we actually use it in upcoming future calculations, so that we don't have to calculate everything from the scratch. So this is one way we can determine that this problem should be solved using dynamic programming, because if we just look at the problem, we understand that we need to find the longest increasing substring, which means that we need to keep track of whatever we have calculated so far in the past, and using those results we would make decisions that whether we want to keep this current value or we want to ignore this current value. So this is a very important thing to keep in mind, and this is basically the core concept of finding the pattern whenever you are given that whether the problem is dynamic problem or dynamic programming problem or not. Because in the interviewer is not going to tell you that hey, this is a dynamic programming problem and just go and solve in that manner. So now let's again continue with our example. So we can determine that currently the value at 8, the longest increasing substring we could make at value number 8 is 1, but we just found that from 7 to 8 we can actually make a substring as well. So this would become actually 2, and we can say that up until the point of 8 the longest increasing substring we can make is actually 2 and not 1. Now let's move forward. Now let's consider for value number 5. At value number 5, let's again compare from 10 to 5. We cannot do anything because 10 is already greater than 5, so there is no point of doing this conversation. Let's compare 7 to 5. From 7 to 5 we cannot do anything because 7 is greater than 5 and also 8 is greater than 5. So at value number 5 there are no values that are less than 5. So at value number 5 the longest increasing substring we can make is actually size 1, because there does not exist a smaller number before 5 in our given input. So we'll keep this 1 as it is because we have already made all the calculations. Now let's calculate for this value number 16. And actually for value number 16, if you notice that all the values are smaller, so this would be a very good point for us to understand that how everything works. So from 10 to 16 we notice that 10 is smaller than 16, so there is a possibility. And basically we can say that whatever the longest increasing substring we have found at 10, if we do it plus 1, that would become 16. So the longest increasing substring for 10 we have found is actually 1. So 1 plus 1 equals to 2. So let's just update the value to over here, and now let's move on with our calculation. So we are done with this 10. Let's calculate with 7. So if we do 7 to 16, actually again we will do 1 plus 1 because LIS of 7. So 1 plus 1 is again 2. We already have 2, so there is no point in updating the value. Let's ignore this. Let's do again with the value 8. So from 8 to 16 we know that the value of 8 is actually 2. So over here at value number 16 we can say that increasing substring at value number 8 plus 1, so it becomes 2 plus 1, and 2 plus 1, okay, I made a mistake. I think this is 1 that represents 5, and the value for 16 is actually over here, so I'll just write it down. So LIS of 8 plus 1 is actually 2 plus 1, which is 3, which is greater than whatever the longest increasing substring we have so far. So which means we can update this value. So over here the longest we have found so far is actually 3. And now we can also create one more substring from 5 to 16. If we calculate from 5 to 16, we found that the value is actually 1 plus 1 would be 2, which is not greater than whatever we have at 16. So we can say that up until this point 16, the longest substring out of all of these values we can make is actually 3 for the values up until the point of 16. And let's move forward with our calculation. So again, the next value is 27. 27 is greater than all the other values. So if we do 10 plus 20, 10 to 27, we would find the value as 2. We'll do 7 to 27, we will find the value as 1 plus 1, again 2. We will do 8 to 27, we would find the value 2 plus 1 as 3. Again we will do 5 to 27, the value we would find would be 2. And at the end we would do 16 to 27, and we know that the value at 16 is 3. So we would be able to find the value as 3 plus 1. And because we have calculated all these results, we don't have to do calculations all the way from beginning, and we are just able to use the results we have stored so far. So we know that the maximum value we can find is 3 plus 1. So we would update the value at longest increasing substring at value number 27 to 4. And then we come to our last value, 9. So, and again we will do the whole thing for 9. So 10 is greater than 9, so we cannot do anything. 7 is less than 9, so we can for this one we can have the value as 2. 8 is also less than 9, so from 8 to 9 value we can have would be 3. 5 is also less than 9, so from 5 to 9 the value we would have would be 1 plus 2, 2. From 16 to 9 we cannot do anything because 16 is greater than 9, and from 27 to 9 we cannot do anything because 27 is definitely greater than 9, which means that the maximum value we could have find so far over here for 9 is actually 3, and that comes from the 8 plus 1. So we will update the value over here as 3. And now we just need to find that what is the maximum value we have found in this array that we have created based on the calculation. So basically clearly we can see that this value 4 is the maximum value we have found, and that would be our answer. That is what we would be returning as longest increasing substring. The thing is, we actually don't need to iterate over the entire array again. We could have actually done this when we are calculating or when we are making this array. We could have just keep track of one parameter called max, and we would compare it with whatever the value we calculate at each location. So whenever we find a new maximum value, we'll just store it in this value, and at the end of our loop, in this max parameter should have our final solution, and we can definitely return this, and this solution would work perfectly fine. Now let's calculate the time complexity. So basically the time complexity for this one would be big O of n square, and it's pretty simple to understand that because for every single element we are basically taking all the elements before that and comparing it with whatever the element we have. We did the same for every single element. So for n element n, we might have to compare it with n minus 1 values, so the time complexity becomes big O of n square. And if we calculate the space complexity is also big O of n, because we need to create this additional array to store all the values. And this is a good time complexity and good space complexity compared to our brute force approach. Remember our brute force approach, the value we had was actually 2 to the power of n, which was way higher. This was almost exponential time complexity, and we have done significant improvements from this one, and we have actually moved to n square. So this solution would work perfectly fine in any interview. And I'll move on to coding, but the thing is I would be making another video to explain that how can we solve the same problem using n log n complexity. and this is actually pretty ideal. And if you can achieve this in any interview, if you can come up with this time complexity right then and there in an interview, you can be guaranteed that you would be placed in any company you want. So let's move on to coding now.
So first of all, we will create a new array called lis, and we would create the array of size, whatever the size we are given for the input nums. And we will initialize the array with value 1. We will also create a parameter called max that will keep track of the maximum longest increasing subsequence inside the loop, and we will initialize the value as 1. So now let's create our two loops. So first of all, we will create a loop that is starting at position number 1, not 0, because we need something to compare to, otherwise all the values would be just 1 before that. And we will run it till the length of the given array. Well, now this would be our inner loop, and we would start it from position 0, and we will run it all the way up to the position I. Now inside the loop, first we need to determine that whether our current I that is on the right side of the array is actually is actually greater value than whatever our j is. If that is the case, then only we would move forward with the calculation. So if I is greater than j, now we will do our calculation for the dynamic programming. So the value of I would actually be the maximum value we can achieve for whatever lis of I we already have, or 1 plus whatever lis of j we have achieved. And this would be our recurrence relation. I guess that is what it is called in dynamic programming. So this is just to keep in mind that yeah, if you mention that this is the recurrence relation, it sounds really good impression. It sounds cool as well. And also we check that whether the current lis value is our max or not. So we'll just check the existing max value with the new lis that we just created. And yeah, I think that's pretty much it. After this loop runs, we can simply return whatever we have found for the value max, and this should be our answer. Let's try to run the code. I think we made some silly mistake. Yeah, looks like our code is working. Let's try to submit it. And our submission works, but if you notice that our submission is not actually the best submission, it's only faster than 55.54% of the online submissions, and that is because our this solution is actually work in big O of n square times, so n to the power 2. But there is another solution that actually runs in big O of n log n time, and I would be creating a new video explaining that solution. And this is actually a pretty interesting solution. It's actually a sorting algorithm that we are going to use to achieve this. So hope you like the video. Let me know what you think, and if you have any suggestions, just feel free to reach out to me. Our goal is to get employed in any FAANG company, and until we get there, we are not gonna stop. So hope you like it. Thank you.
So basically the previously when I solved this problem, I mentioned in that video that I was solving it in big O of n square time, and this would be perfectly good and reasonable to expect from any candidate in an interview. But the thing is, if you want to be an exceptional candidate, if you want to make sure that you don't leave any gaps in your FAANG journey and your so you need to know these things. So that's why I'm creating this video, and in this video we are going to solve this problem in actually big O of n log n time. And the way we are going to do it is something called as patience sort. So let's take our custom example. And as I have mentioned previously, that it is very important to make custom examples, because using those custom examples you can determine that you have the ability to think and make sure that how can you create your own test cases. So this is our example, and it's quite a long one, but the thing is I need to make sure that I go through all the possible aspects in the given example, and that's why I took so many integers, so it becomes absolutely clear in your mind that how we are going to achieve it. So basically, at any given location we can either have a null string, so a subsequence that has no entries, a subsequence that has just one entry, a subsequence that has two entries, so this is null, one entry, two entries, subsequence that has three entries, subsequence that has four entries, and so on. So, and our aim is to find out a longest increasing subsequence that we can achieve. So for this one we are going to use couple of arrays. We are going to put them in a different manner, and as you would have guessed that because the time complexity we get is actually n log n, somehow we are going to use binary sort over here. So let's start the problem. First of all, we are going to create two arrays. First array is to keep track of the longest increasing subsequence that we have found, so whether it's value 1, of value 2, of value 3, whatnot. And second thing is we are going to store the last digit for any given longest increasing subsequence. So what I mean by this last digit is that suppose we find an increasing subsequence over here, that the values 5, 16 and 27 is an increasing subsequence. So in the longest increasing subsequence array we are going to note an entry as 3, where because the length of values are 3, and the last entry we have in this subsequence is 27, and the combination of these two is going to allow us to create some pretty interesting things. So let me go over the example, and I would be explaining every single time what we are doing and how we are finding it, and at the end I'm going to show you that what could be the intuition behind this. So at first location 10, basically we don't have any substring so far. So the current substring we have found up until this point 10 is just a single value 10, and in this single value 10 in our LIS we can create an entry like 1, and the last digit we have for this entry 1 is 10. So we are good so far. Now let's move on to the next one. Now next entry is currently we only have a substring 10. Next entry we have is 7. Now we cannot create an increasing subsequence just by these two pairs, because obviously 10 is greater than 7. But the thing is we can replace this 10 with this 7, and how we can replace it is because up until this point 10 is a substring of length 1 and 7 is also a substring of length 1, so both of us are just same. But the thing is, whenever we move forward, all the values that are greater than 10 will also be greater than 7, which means that suppose we have value over here 11, 15, 18, something like this, And if we take it with 10, we would be able to create a longest increasing substring like 10, 11, 15, 18. But the thing is, same thing can be done for 7 as well. So it makes no difference that which entry we keep. But if we have a value that is between 7 and 10, 10 won't be able to do anything in that case. Suppose we have an entry like 8, 9, 11. So in this case, if we would have just considered 10, the longest substring we would be able to make is 10 to 11. That's it. But from 7, we can actually make 7 to 8, 8 to 9, and 9 to 11. This would be of size 4 and this would be only of size 2. So it is in our interest to keep 7 as our longest increasing substring and not 10, because value of 7 is actually less than it. So we will replace this 10 in this array we have created. So currently the last element we have becomes 7, and this 7 is also of just length 1. So we have only kept this one entry and we have basically just discarded it. We have went over it and we didn't find anything good. Now at this point we only have a substring of 7. Now comes the value 8. Now 8 is greater than 7 and 8 is in itself a higher value. So we have two possibilities. Either we can keep 7 as it is as a longest increasing subsequence, or we can have a subsequence like 7 and 8, and we are not appending 8 behind this 7. We are creating that the longest increasing subsequence we have so far of value of size 1 is still 7, but this one is, we are creating a new subsequence that is of size 2, and we are appending this 7 behind 8. So which means we would be creating a new entry over here in our longest increasing subsequence of value 2, and the last element of this value is actually 8. But the thing is, meanwhile the first element is still 7, because we only up until this point, if we consider a substring that is of only value that is to be only of size 1, the best element to choose for size 1 would be 7, because it is the smallest. And this is the main logic behind the patient sort. So let's move on to the next element. Again we go to value 5 now, and the substrings we have so far are 7, 7 and 8, and now we have this 5. So we cannot append this 5 over here, we cannot do anything with this. But the thing is, if we consider these 4 elements and if we consider the substring of size 1, 5 would be the most ideal candidate and not 7, because 5 is actually less than 7. So it is in our interest to replace this entry 7 with the entry 5, and we will update in our array with entry 5. Let's clean this up a bit. Now due to space constraints, we are going to write down our subsequences over here. So far we have found 2 subsequences. One is just 5, that is of size 1, and second one is 7 and 8 that we have stored over here, and we are keeping track of the last digit that we have appended. Again let's consider 16. So now for this 16, and if we consider the last 2 elements, 16 is definitely greater than 5, but there is no point in appending 16 at 5. It is in our best interest to append 16 behind this 8. So our algorithm is basically, what we are doing is we are taking the value from the input, we are checking in our last array to see that what is the best position to fit that value, and the best position to fit that value is to keep the increasing order intact, because notice that previously the value we had was 7 and 8, that was increasing order. Now the value we have is 5 and 8, that is also increasing order. And now the next value 7, next value 16 comes, we can actually append it behind 8. So after 8 we can create a new entry, and we would do that. So we would create a new entry called 3. And why we were able to do a new entry is because this 7 and 8, we are not going to replace 8 by 16. We are actually going to leverage this 7 and 8 because they are already a subsequence, and our aim is to find the longest increasing subsequence. So why would we replace 8 with 16? It's actually in our favor to keep this 7 and 8 and create a new subsequence 7, 8 and 16, so that we can use, because suppose if all the values that come after 16 are like 9, 10, 11, 12, 13, and if we have created a subsequence called 7 and 16, so these all values, we would not be able to consider them as our longest increasing subsequence because we don't have this 8. But if we have this 7 and 8 over here, and if these values comes after 16, and we have created a separate entry like this one, 7, 8 and 16, so this is separate in itself, we can actually append all these 9, 10, 11, 12, 13 values behind this 7 and 8, and this would be our longest increasing subsequence. So I hope that this makes things more clear, that why we are choosing to have a new 7, 8 and 16 as substring. And we would create a new entry in our array as well. So now these are the 3 substrings we have. Next value is 27. So 27 is again greater than this 16. So now we are going to create a new entry 7, 8, 16 and 27, and we are going to have a new entry in our LIS with value number 4, and we are going to add the last digit as 27 over here. I hope that what I'm doing is understandable, that why we are actually creating this new entry from the given input. The next value we have is 9. So let's see that where is the best place we can fit this 9. The best place we can fit this 9 is actually after 7 and 8. So like this 9. The thing is, we are not going to replace the 7 and 8 with 9, because up until this point, up until 9, if we see the best pair with 2 entries only, that with the least value is actually 7 and 8. There are multiple pairs that create the that are creating the longest increasing subsequence of length 2, like 5 and 16, 16 and 27, 5 and 27. The thing is, they're all greater values. If we see the last element over here, 7 and 8, the last element is the perfect fit. So that is why we are going to keep the 7 and 8, and we would be creating a new entry at this place. So we are going to replace the 16 with value number 9. So let's update this in our array as well. So for the value 3, the best we can find is 9, and that would be the subsequence 7, 8 and 9. So far we are keeping track of all the subsequences that we have found with the values 1, 2, 3 and 4, and we are also keeping track of the last digit that we have calculated so far. And because all the values are in an increasing order, it becomes very easy for us that whenever we find any new value like this, it becomes pretty easy for us that where we are going to add it in this array, and which value we are going to update it. So this is the main logic behind patient sort. Now the next value is value number 1. So where in this array we can store value number 1? It's pretty simple. We can only store it at position 1. No other position we can store. And based on this, we can say that up until this point, if we only have to create a subsequence of length 1, it would be the most ideal to have the last digit as 1, because all the values after that would actually be in an increasing order, and we can replace this 5. In our list of subsequence, we will have entry 1 over here. Now let's consider this value number 13, where over here we can add this value number 13 so that it would give us the most value. And actually we should not be replacing this 9 with value number 13, because we are not trying to achieve a substring like this. Rather than having 7, 8 and 9, we are not trying to get 7, 8 and 13, because that is not in our favor. Because notice that this is already existing and 13 can be appended next to it. So what we can do is, actually we can replace this 4, what the subsequence with 4 entries, with this 7, 8, 9 and 13. So our new subsequence would become 7, 8, 9 and the 7, 8, 9 and 13. And why we are able to replace the 7, 8, 9 and 13 with previously 7, 8, 16 and 27? The reason is quite simple, because both generate the value 4, so that is okay. But the thing is, with this 9 and 13 we have higher odds of making longest increasing subsequences for the upcoming values, and which we are going to see right for with the next value. So we will update the value 13 over here, and so far these are the 4 subsequences we have. Now the next value is actually 15, and imagine that if we had kept this value as the substring of 4 values, we won't be able to insert 15 over here, because though both of these were same, 15 is easier to be appended over here, but it cannot be appended over here. So that is why in the previous step we actually replaced this value 4 with 13. So I hope this makes it more understandable. Now let's see that what we can do for this value number 15. So the logic is quite simple. We are simply going to append this value number 15 behind this 13. So the new substring, and we are going to keep the value number 7, 8, 9 and 13 as a 4 substring, as a substring of length 4, and we are going to create a new substring 7, 8, 9, 13 and 15, and this would be a new entry in our array. So we will have a substring of length 5, and the last digit for that would actually be 15, and this would be the end of our array. And since we have reached to the end, we just need to iterate over this one and find out that what is the biggest length we were able to find, and we just simply return this value. So this is as simple as it can be. And why we are able to achieve it? Because at every single location, for every single element, we are trying to see that where we can fit that element that best represents that position, and based on it we were keeping track of the longest increasing subsequence. So basically we were intellectually choosing our own longest increasing subsequence, and we are also keeping track of whatever we have calculated in the past. Because if we were to choose a value of 3, that what is the longest increasing subsequence up to the point of 3, we can easily say that hey, it's this one, and the last digit is actually 9. So if we find some better digit, it becomes pretty easy for us to calculate that where we are going to append that value. And I hope this makes things more understandable. Now let's calculate the time and space complexity for this one, and it's pretty simple. That at any given location we are iterating over the entire array, and for any single position we are checking that where we can store that position in this given new array that we are trying to create. But the thing is, this new array is already sorted, so because it is sorted, we can actually achieve that in log n time, and initially we have to iterate over this entire actual input once, so that will take n times. So basically we are calculating this whole approach in big O of n log n time, which is a very good time complexity. Because if you remember correctly, originally for the brute force approach, our time complexity was 2 to the power of n. For the second accepted approach that I completed in last video, our time complexity is actually n square. The thing is, n log n this is a thing of beauty. Now let's move on to coding. And if you still don't understand the concept, I again ask you kindly to go over this example again, because if you can master this, sky's the limit for you. So let's do the coding now. Let's create a new array list. We can start by adding the first element, because the first element would actually be the first list of size 1. And then we will initialize our loop to iterate over the entire input array, and again we will start the loop from second position, I equal to 1. Inside the loop we need to find that whether the given number is it actually greater than whatever the last value we have in this subsequence. If it is, we need to append it to the subsequence. So and we can just add it to the subsequence. If not, we'll need to run the binary search. So, and over here we can just create a new function to run our binary search, and in the input we will provide the substring and current ith value we have. And now let's create method for that. Inside the loop, first of all, we'll create a left and right variable. So left would be of size 0 and right would be of whatever the size we have for the integer, for the given substring. Now we will just run a condition that while left is less than right, we are going to calculate the mid pointer, and then if the mid pointer is already existing, we simply return that value. If not, we either move on the left side or right side. So we'll do left is equal to mid plus 1, else we can simply do right is equal to mid, and after the loop we can return the value of left. Now over here in the J we are receiving whatever the value of left we got, so we add the subset to our existing subsequence. That should be the logic. So after the return, we after the end of the loop, we just need to return the size of the list, and this should provide the longest increasing subsequence. Let's try to run this code. Looks like we put the values out of order. Yeah, looks like our solution is working. Let's try to submit it. And yeah, see, our solution is actually faster than a lot of other submissions, and that is because our runtime is actually n log n. And I'll be posting this solution in the comments, and hope you like the video. Thank you.
So the lead code problem we are going to solve now is called longest common subsequence. Now we can see that this one is a lead code medium problem and also one of the most liked problems on lead code. So I'm going to pay my utmost attention. Now let's understand the statement. We are given two strings called text1 and text2. Now we need to return the longest common subsequence, and if there is no common subsequence that exists, then we need to return 0. Now we are given the definition of a subsequence is a string, that is a new string that can be generated from the original string with some characters that can be deleted without changing the relative order of the characteristics. So without getting too much into the details of the definition, let's try to understand what we are being asked to solve. Basically, we are given two strings text1 and text2. Now we can notice that text1 currently has 5 characters A, B, C, D, E, and text2 has currently 3 characters A, C, and E. Now the thing is, if say for an example from text1 we decide to eliminate this characters B and D, we can also create A, C, and E, and this is going to be the exact same manner, or the sequence of relative order remains the same between both the strings. So we can say that for this given example, we actually have a longest common subsequence that we can make that follows the relative order, and that is of size 3. So we need to return 3 as part of the answer for in this case. Now let's try to understand it with one more example for this one. Now we can see that currently the characters we have is x, y, z, and the characters we have for this text 2 is y, a, b. So now we can only find one character that is common between both of them and that follows the relative order, and that is this y. Apart from that, we don't see anything common. So in this case, we can only create a longest common subsequence that only consists one character. So we need to return 1 as the answer. Now, if we take a look at this example, text1 and text2, we see that there are no characters that are same between both the text. So in this case, we will have to return 0. But in the same example, say for some reason, if we are given the values like A, B, C and D, E, F over here, and then we are also given D, E over here, then we will need to return 2 as the answer, because the relative order of D and E remains the same even if this string had 3 additional characters. So we will have to solve this problem, and definitely this is going to yield to some very interesting results. Now let's understand the brute force approach to solve this problem. The logic is quite straightforward. Let's say that we are currently given two strings in this particular fashion. Then what we can do is we can go through every single possible combination of any particular string and try to match it with the other string. So what I'm suggesting is that for this text one, we start taking permutation of all the other substrings that we can make out of this one. And we know in terms of making permutations, we can actually make 2 to the power of n permutations for any given value. Why? Because at every single character we will have to make the decision that whether we need to include this character or not to include this character in order to generate the permutation. So this would eventually yield us the correct result, because what we'll do is we'll try to create all the different permutations and combination, compare it with this given another string, and we'll try to see that what is the longest common subsequence that we are able to make. But this is very inefficient approach, and also the time complexity goes in some sort of exponential form, so I'll not go into the depths of this one, and we'll try to do something smart in order to solve this problem. Now let me come to the optimal way to solve this problem, and for that we are going to use one of the most beautiful concepts in computer science, and that is dynamic programming. Now let's take a quick recap. Let's understand that why do we actually have to use dynamic programming in this problem. Well, the answer is actually quite straightforward, because let's say that we are currently given the two strings as A, B, C, D, E, and then once again A, C, and E. Now notice that if we start comparing the two strings at any given moment, character by character, it would not be very much fruitful. Why? Because okay, let's say that we define that this A is common between both of the subsequence. Now we are at this character B, and we don't know that next character B is not present over here. So we don't know that whether B is going to be present somewhere down the road or not. So do you think that we should compare B with every other character that is currently present inside the T2 string? Well, we could do that, and we are going to do that, but In order to do that, we'll also have to remember that what was the relative order of sequence that we have been able to identify beforehand. And it could be possible that if we are dealing with multiple sequences, which subsequent to consider. So let me give you one example like this. Let's say that we are given currently strings like a b c d e, okay, and we are given the t2 string to be a b, then x y z, and then once again we are given the string to be, let's say, b c d e. So do you think that from this particular point forward, if we see, the longest common subsequence we can make is going to be 2? But the moment we start identifying these characters, we can, if we just drop this b, we can actually create the longest common subsequence of size 5. But we have to drop one b that was already part of one of our relative subsequence, which means the result that we are going to make later down the road is actually going to be dependent on the previously calculations that has been made, and also future calculations that we are yet to be make. And when we are at the last position, we should make the best judgment on which path to take. So that's why this is a good candidate for dynamic programming. Now the question is how we are going to use dynamic programming to solve this problem. And for that, what I'm suggesting is, number one, we have to check every single character for all the other characters, and same way for any particular character we will have to compare it with all the remaining characters. So there is no getting away from that in this problem. We will have to do n square work, or m multiplied by n work, where m is the length of text 1 and n is the length of text 2. Okay, so this has to run in big O of n square time complexity. But how we are going to do that? Number one thing I'm suggesting is that we actually create an m cross n grid, just like the one that I have shown over here. And for this particular grid, we'll need two things for our dynamic programming. We'll need a base case scenario. So base case is quite straightforward, that if any particular character is not matching with the other character, then we simply define it as 0. And notice that we actually have created an extra space at the beginning. So there is an extra row and extra column, which means this is not strictly an m cross n matrix. This is actually an m plus 1 multiplied by n plus 1 matrix. So we are adding one more extra line, and that is to consider our base case. Now at any given moment, what we are going to do is, if we identify that there exists a combination, there exists a value that is common. Let's say that over here the c and c is going to be common for this particular cell, which means what we can definitely say in this case is that this cell is going to be an addition to the previously calculated longest common subsequence. Now where is going to be that information for the longest common subsequence? To the diagonal value. Why it would be at the diagonal value? Well, let's take a simple example. Let's say that currently the values are a b c, and this value is a b and c. So notice that for this particular square, the logic is going to be quite straightforward. We are going to have a and a common at this place, then we are going to have b and b common at this place, and then we are going to have c and c common at this place, which means longest common subsequence is directly represented towards the diagonal value in the best case scenario. And this is the fact that we are going to exploit. So whenever we identify that at this particular location there was a common subsequence, then we had to add one value to the previously found longest common subsequence. But we haven't found any subsequence because this value is 0. So definitely the longest common subsequence at this 8th location is going to be 1. So we are going to mark it by 1. Same way, the longest common subsequence at this location is actually now 2, because we are comparing AB with AB, and that's why this is going to be an addition to the diagonal. So we are going to mark value 2, and same way this is going to be value 3, one more addition. So same logic we are going to apply over here, that whenever we identify any particular common characters, we will check the diagonal value. That is number one thing. Next thing is that let's say we identify any particular character that does not have any common values, so both characters are different than each other. Then it becomes the question that what is the longest common subsequence we have found so far. And there can be two possibilities. Why? Because let's say that I'm currently at this bth position. So on one side I'm checking against AB, but for AB I have checked with A, I have checked with AC, and I have checked with ACE, because I'm trying to fill up this row.
same way for any particular cth character, I'm also comparing it against a, against ab, against abc and whatnot. So the answer for the longest common subsequence where the characters do not match is actually going to reside on the adjacent cells for any particular cell. So let's say I'm trying to consider the values for this cell. Now we know that b and c don't match, so in this case we'll have to check that what is the longest common subsequence we found either way, because we are not only comparing text 1 with text 1 or text 2 with text 2, we are comparing them with each other. So we'll have to take the maximum value amongst the adjacent cells, and this is going to yield us the correct result. So now let's recap our rules. Number one, if we find equal characters, so let's say that if an I and j value are equal, then we are going to do the +1 operation compared to its diagonal value. So diagonal value is going to be I minus 1 and j minus 1, this cell. Okay, and if that is not the case, if we find that I and j character do not match, then we will have to find the maximum value from its adjacent values or subsequent neighbors. So now let's try to do the solution right now. Okay, let's start filling up this particular whole matrix. Now very first value we find a and a, there is a match. If there is a match, we are going to compare it with its diagonal value and add 1. So diagonal value is 0, so we are going to add value number 1 over here. Now next thing is that we will also have to check, let's go row by row. So now we are checking this a with this value b. A and b do not match. So if they do not match, we'll have to, for this cell we'll have to check its neighbors. So we check this neighbor and this neighbor, and whichever is the maximum value we add this one. So what we are saying is that up until this point inside our input, we have calculated a b with a. So in this text 1 and text 2, we can see that the longest common subsequence we find was of size 1, and this is what we are defining it over here. Next we are comparing a with c. Once again, a with c, once again there is no commonality, so we'll add value 1. A with d, once again no commonality, so we'll add the maximum value 1. And a with e, once again the maximum value is going to be 1. Now let's repeat the same operation once again, but now this time we are going to be doing it for value c. Now c and a do not match, so we'll try to find the maximum amongst these two value, and once again the maximum value amongst these two is still going to be 1. So let's just mark it as 1. Same way this is going to be 1 as well. Now we are at this position of c matches c, so we'll have to do an increment with the diagonal value, and we are going to be adding +1 over here, so we can mark this as 2. Now for this d with c, we'll have to compare the maximum amongst these two, and the maximum value is 2, so we'll mark the value as 2 as the answer, and same way 2 as the answer over here. Now we are comparing e with this a, so once again the maximum amongst these two values is going to be 1. And notice we found 2 over here, but why we are marking 1? Because notice what we are calculating or comparing so far. We are comparing a with value a c e. So in this case the longest common subsequence is going to be of size 1, and that's why we are marking 1 over here. Same way this is going to be 1 because we are comparing the maximum amongst these two. Same way with c, we are now the value is going to be 2 because this value was 2. And why it was 2? Because notice we are comparing the values a b c versus value a c e, and amongst this comparison we can see that there exists the longest common subsequence of size 2, that is, which is represented over here. This is the beauty of dynamic programming solution. Now for this d comparing with this e, once again we'll choose the maximum, so answer should be 2. And now we have e common for this last cell, so we'll have to do +1 with the diagonal, so 2 plus 1 is going to be 3, so we'll mark it as 3. In the end we simply need to return whatever we find in the very last cell as part of the answer, and that is going to be 3 in this case, so we can return this with confidence. See how beautiful the solution looks. All we need to do is just fill up this matrix and things work out beautifully for us. Now if we have to calculate the time and space complexity for this one, time complexity is going to be big O of n square or m multiplied by n, and space complexity is also going to be big O of m plus 1 multiplied by n plus 1, so we can say m cross n for simplicity. But anyways, this is a beautiful time and space complexity and very awesome approach.
Now let's see the coding solution for this problem. Basically, we are going to define two characters m and n to define the length of both of the given strings text1 and text2. Then we are going to initialize our new array dp array. Now notice that we are defining it as a length of m plus 1 and n plus 1 to take care of the zero case scenario that is going to be our base case for our dynamic programming table. Now for this matrix, we are going to fill in all the details. So we are going to use two for loops to iterate over every single row and every single column. Notice that we are starting the values from 1 and 1 because for ith value of 0 and jth value of 0, we already defined the values as 0. Now first thing we are checking is that at any given moment we identify that the character at I minus 1 and character at j minus 1 location are equal to each other. Then for the current ith and jth value we are going to add 1 to the existing diagonal value, that is I minus 1 and j minus 1 value inside the DP array. If that is not the case, then we are simply going to pick whichever is the maximum value for any particular ith and jth element from its adjacent neighbors. So whether the top value or the left value of any given cell. And in the end, we should have completed all the values for the longest common subsequence, and the very last element inside our DP array is going to represent that. So we are simply going to represent that value that should give us our correct longest common subsequence. So now let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code beats almost 90% of all the other solutions. That is excellent in terms of time complexity. Now for the memory, we can improve on some aspects, but we are using like an m cross n grid, and that is also a fine enough solution. But overall, this is a beautiful solution, and once again, it is available on our GitHub repository, so feel free to go ahead and check it out from there. Thank you.
Hello friends, we are still not employed by FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code medium problem, word break. Let's understand the problem statement. So basically we are given a string s and we are also given a dictionary of string word dict, and we need to return true if s can be segmented by all the words that are given inside the word dict. So if we look at the example, suppose our s is lead code and the word dict we are given is first set is lead and second set is code. We can clearly see that this lead code we can generate from whatever the values we are given in this dictionary, so we will return true in this case. And we are also mentioned that we can use the same word multiple times. So suppose if this problem was lead code code something like this, we would still return true because or whatever words are, we can still make it through this dictionary. But if we were given some wording like this, that lead code lee, so up until this point we have the words that we can make from this dictionary. The thing is, this lee, there is not a specific word given for that. The word we are given in the word dictionary is lead, so it does not match. So in that scenario we would return false, otherwise we would return true. Okay, let's try to understand that what would be the brute force approach. Suppose we are given s is equal to ESPN and the dictionary we are given is E, S, P and N. So we can clearly see that all the words are present in the word dictionary, so the answer should be true. And in the brute force solution we are going to use a bottom up approach. So and in this video I'm going to show bottom up approach all the way, even for the optimal solution. So this can also be solved as a top down approach, so let me know if you want to make a separate video on that. And there is also one more thing to consider. Suppose we are given something like s is equal to null value or empty string, and in the word dictionary we are given some elements like a b blah blah blah. So this case we can clearly return as true. Why? Because this empty element will always be there, though it might not be showing, but the thing is if there are no elements in our given string, we can always return true, because the emptiness is also exists in this word dictionary. So we are going to use this logic, and let's see that how we can build our brute force. So we are doing bottom up, so we are starting from the lowest value and eventually we are going to make the whole world. So the first value we need to, so we are at the 0th position. The first value we need to make is simply the word break of a value e, and the word break of value e is very easy to calculate. We only need to check that whether the word break of empty string and the value e exist in this given word dictionary or not. So basically, and we know that if there is an empty string scenario, this will always be true, because I just explained it to you how. So we only need to see that whether this e exists in this word dictionary or not. If this exists, we can clearly say that this is true, and we can denote the value of word break of e as true. Now the second decision we can make over here would be to see the word break of two elements, so e and s. And how can we determine the word break of e and s? Well, again, it's simple. So we need to we have two ways to determine that. Either we can do a word break of empty string, and we can check that whether this es value is present in this word dictionary or not, or we can do a word break of value e, because we know that this is always true. The word break of empty is always true, so we can do a word break of e, and we can check that whether the value s is present in this given word dictionary or not. And word break of e, we already know how to do it. For this word break of e, we need to do word break of empty, and we need to calculate the value of to see that whether this e is present or not. The third option over here we can have is and you guessed it correctly, the word break of three elements, so esp. And for this three elements, we again have three more possibilities. So word break of empty string, and we need to check that whether esp, all these three exist in this scenario, or we need to check that whether the word break of this e and sp exist, and the word break of es and p exist. And yeah, so these are the three ways we can determine that whether the word break of esp exists. The next option we have is the final scenario, that whether the word break of espn exists or not. And to check that, we will have four possibilities. So first one is that we check the empty string, and we check whether the espn, the whole word, is present in this word dictionary or not. Or we can check that whether the word break of e is present and spn, these three values are present or not. Or we can check that word break of es is present, and we can check for pn. Or we can check word break of esp, and we can check the value n. So these would be the four cases where we need to calculate all of these, and for every single one of them. So even in order to calculate this word break of e, we will use this method. To calculate this word break of es, we will calculate this whole method. And yeah, so this would be the brute force solution. Eventually we would find that whether we are able to make this espn or not, and whatever result we get, we just need to bring it upwards, and we would be able to find the solution. So this solution works, but it works in a very horrible way, because at every single location we have two possibilities to make, whether we want to keep that element or not, and our decision tree keeps on growing and growing and growing. And though we will come to the correct solution, but it's gonna take us a lot of iterations to achieve that, because over here you can see that we only had these four elements that we need to consider. We generated such a big tree, and over here most of the values we did not even completed the whole sub iteration for them, because I would be running out of space. So the time complexity, as you have guessed correctly, for this approach is actually big O of 2 to the power n, because at every single location we are making two decisions, which is pretty bad. And why it is 2 to the power n? Because we are calculating everything at the same time. So see that do we have a room where we can save whatever we have calculated before, and can we use it further down the road? Of course we can, because notice over here this w word break of e, we are using it over here, but we have already calculated its value. So why do we need to calculate its value again over here? Same goes with this word break of es. We have already calculated the value over here. So why are we repeating this whole process? There are a lot of repeated effort. This is repeated, this is repeated, this is repeated. We have already calculated all these values. So somehow if we just create a cache, we store that whatever the values we have calculated so far, and keep track of that cache, and whenever we need to encounter that whatever value we are calculating right now, we can simply check that whether that has already been calculated, and using that we can actually come up to a better solution. Since you guessed it correctly, that because we are using something that we have already calculated in past, we are keeping a track of it in some form, and we are using it further down in our next iterations. So basically we are using the most beautiful thing in the computer programming, the dynamic programming approach. In the dynamic programming, we are going to create a single array of size whatever the given input string is, and based on that particular array we will calculate all the values that have been calculated so far. And because this is a bottom up approach, we are going to start filling up array from the 0th position, and we will reach at the end, and in the end, after all the calculation, we will just simply return whatever the value we have calculated over here. So let's see that what would be the optimal solution. Suppose again we are considering the same example, s is equal to ESPN, and the word we are given is ESP and N. And now let's create a new data structure called DP of an array that is of size 4, and there would be 0 1 2 3 4. Now we know that this 0th position would always be true. And why it would be true? Because this indicates that for DP of size 0, which means that for string of size 0, does the word dictionary contains this particular element or not? This is what this DP is representing, that at every single location, whether the value of that length of the character, is it present in this word dictionary or not. So DP of 0, we know that that's an empty string, and if it is an empty string, we can determine the value as true. So this would become our base case, and this is very important to identify in a dynamic programming problem, that we need to have a base case. And initially we would set up all the other values as false, and we will run our iteration. So let's see that what each of these values are going to represent. And you guessed it correctly, that this value represents a word break of 0. This represents the word break of 1. So in this case, it would be the value E. This represents the word break of value ES. This represents the word break of value ESP. And this one represents the whole word. So word break of the value ESPN. And yeah, so at the end, whatever result we find over here, if we just return that would be our perfect solution. So example we are going to take is the same one that we have been discussing. So the S is ESPN, and the value of word is E, SP and N. And we know that our dynamic programming of value 0, this is our base case, that is true. So what we are going to do is, we are going to iterate over, starting from single element, we are going to keep on increasing the size of our element. Depending on the size of our element, we are going to fill up this DP array, and at the end we will just return the value. So initially we will calculate just for value E. So DP of 1 would be calculating the word break for value E. So let's see that whether this value E is present in this word dictionary or not. So the value is present, so we can say that the DP of 1 is true. Okay, this is good. Now let's check for the second element. So for dp of e2, this would be calculating the word break for es. Now we know that we can break down this word break for es in two parts. Either we can do like an empty string and we can check for this value es, or we can do the word break for the value e and we can check for the value s in this given word dictionary. If we go for this one, es is not present over here, so we are left with the second approach. In the second approach, we know that word break of e, which means this dp of 1. So dp of 1 is already true, so we can say that okay, this is true. Now we only need to check that whether this s is present or not. So s directly is not present in this word dictionary, which means that this condition is not satisfied, this condition is not satisfied. So we can say that the value for dp of 2 is actually false. So we will just mention it over here that this is false. Okay, let's try to calculate the dp of 3. So dp of 3 means word break of elements esp. Word break of esp means three things. First one is that we can directly calculate to see that if esp is present or not. This is not present, so this condition won't work. Second one is we can check that whether the word break of e is present and the word sp is present or not. And third we can check is whether that word break of es is true and the p is present. Now the thing is, we already know that this condition is not true, the esp is not present, which means we need to check these two conditions. Now let's check this bottom condition first. So word break of es, this word break of es is actually in the dynamic programming array, it's the second position. So dp of 2, so dp of 2 and the value p. Now we know that dp of 2 is already false, which means that this condition will also be false. So we don't even need to calculate, and we don't even need to check for this element p in the word dictionary, because we know that since this dp of 2 is false, we can just ignore this case and let's focus on this one. So word break of e, which means that dp of 1, so dp of 1 is true. If dp of 1 is true, which means that at least this condition is true. Now we need to check that whether sp exists in the word dictionary or not, and sp also exists in the word dictionary, which means that dp of 3 we can consider this as true. Let me also put this one on this side. Now let's calculate the dp of 4, which means word break of espn. So again, this will have 4 conditions. Now I'm going to write this in a different manner. So we can also say that this is dp of 2 and pn, because dp of 2 represents this es, and we can also say this as dp of 3 and n. And yeah, these are the 4 conditions we need to check, and if any of them are true, we need to return true over here. So let's check the first one. Does espn exist in over here? No, it does not, so this is false. So wb of e is true, so at least one is true, but spn does not exist over here, which means this is also false. Now dp of 2, this is already false, which means we don't even need to calculate and check for this pn. Now the last one is dp of 3. dp of 3 is true, so this is good. Now we need to check whether n exists over here or not. So n exists over here, which means this is true. So we find one case that is true, so which means that over here we can mark this value as true. And remember that this given string, this is of length 4. So because this is of length 4, we simply need to return whatever value we find as dp of 4, and that is true. So in this scenario, we'll just return the answer as true, and that would be our solution. This is a very good solution, because notice that we are already calculating what we need so far. We are keeping track of it at every single position. Because we have calculated these values, we are able to use it effectively and come up to the result. Let's calculate the time complexity. So we are iterating over all the elements at least once, so that is an n. Then we are also creating substrings. So for every value n, there can be n minus 1 substrings, which means that we need to do additional n work. So the time complexity would be big O of n cube. So this is also pretty high time complexity, but if you compare it with 2 to the power of n, this is actually way lesser. Because this time complexity that can still be calculated, and this is a polynomial time complexity. But the thing is, this one is exponential, and yeah, we need exponential salary but not exponential time complexity. So let's code up the solution. Okay, let's create a boolean array to store our cache, and we'll name it as dp. We'll assign its length to s.length plus 1. And we know the base case where dp of 0 would always be true. Also, for this word dictionary, this is a list. So we are going to create a hash set that will store the strings, and we will store this word dictionary over there, so it becomes faster for us to access the word dictionary. We'll just name it word set. Now I think we are all set to start our loop. So we'll create the 2 loops. Notice we are starting our loop from I equal to 1 because we don't need to, we already have the value for I equal to 0. And we are going to start the second loop from 0th position, and while j is less than I, because we only need to go up to ith point. Now inside the loop, first of all, we will check that whether the dynamic programming for the jth value exists or not, and this is what I already explained in the solution explanation, that if this is true, then only we check that whether the word set contains the substring. So we'll use a substring method, and we'll provide the parameter as j and I, because j is less than I. And if this is true, basically we just need to assign the value of dp of I as true. And yeah, I think that's it. We don't need to do anything, and at the end of the loop we can simply return the value of our dp of s.length. And yeah, also when we find this value dp of I is equal to true, which means that we can break out of this inner loop, because there won't be another pair that we need to calculate, because even at any moment if we find a single true, that's sufficient for us. So let's try to run this code. Okay, looks like our solution is working. Let's try to submit this. Yeah, our solution works. It is accepted by LeetCode, but notice that this solution is actually pretty slow. It is taking a lot of time, and it is not as fast as our other solutions. So there is one trick we can do is, rather than going from from j equal to 0 to I, we can actually go in reverse. So we can start the position of j equal to I minus 1, and we can see that whether j is greater than or equal to 0, and we will do j minus minus. That way we would be able to find this a little bit faster. So let's try to run the code first. Yeah, this works. Let's try to submit it and see the significant difference. Now our solution is much faster, and even if you see over here, previously this one was running in 13 milliseconds, and this one is now runs in 4 milliseconds. Basically we are just eliminating and breaking out of this inner loop faster. We are not doing anything special. So yeah, this is just something to keep in mind. And yeah, I hope you liked it, and I will be posting this code in the comments.
Hello friends, I'm a cloud solutions architect at Microsoft and my aim is to create free resources that will empower every single engineer in this world so that they can do better with their technical interviews. Now continuing in that direction, today we are going to solve a very important problem called regular expression matching. So let's get started with the problem. So if we see some of the popular companies who have already asked this question, there are companies like Microsoft, Amazon, Facebook, Google, Bloomberg, Adobe, Apple, Uber, Snapchat, Tesla, Goldman Sachs, and Airbnb. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a lead code hard problem and also a very well-liked problem. Basically, we are given two input strings. One is string S and the other one is pattern P. Now we need to implement a regular expression matching function that can support a dot character and a star character inside this pattern P as well. Now we are given the definition that what does a dot and a star represent. Basically, a dot can represent that it can match any single character and the star represents that it can match 0 or more preceding elements. Now first let's try to understand both of these with examples. So suppose we are given a pattern P that looks like A, B and dot. Now dot by definition it can support any single character. Now inside our given string S, suppose we are given the values to be A, B, C. Now can we conclude these two to be matching strings? The answer is yes. Why? Because for this particular dot we can consider it to be C because it can match any character. Suppose if we are given an S that looks like ABX, is it true? Yes, this is also matching with this pattern P because for this time for this dot we are actually considering it to be X. But if we are given S that looks like AAX, is this matching? No. Why? Because the second character over here, this is A, meanwhile the second character inside our pattern is B. These two are not matching, so this is not a matching sequence. So basically this is what does a dot represents. Now let's try to see one example of what does a star represent. So basically suppose we are given a pattern P that looks like this where the values are again A, B, star. Now what does this star is saying by definition? The star is saying that it can match 0 or more preceding elements. Now what is a preceding element of this X? The preceding element is B. So which means that now this particular pattern can match bunch of different other strings. So strings such as A, B, 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 B. Does this match this particular pattern? Yes. Why? Because if we see, okay, first character A is matching each other. Now for the second character B, we can have multiple B's over here because of this star value, because that is what is given in the definition. So based on the definition, we are now in this case considering the star to be all of these B's. Suppose we are given a string S that is only A. Is this matching with this pattern P? Yes, this is also matching. Why? Because this star can represent that we have 0 or more preceding elements. So in this case, we are considering that we have 0 B's in the pattern, which means that our given S is actually matching. And in this case, since both of these are matching, now let's try to take one more example. Suppose our given S is equal to like ABX. Is this matching? No, this is not matching. Why this is not matching? Because this AB portion, this is matching, that is good. But we do not have an X over here, and that is why this is not a match. Does this match? And pause the video for a second. Try to guess that whether this matches or not. Let me come up with the answer. The answer in this case is that this is actually a match. Believe it or not, this is a match. Why this is a match? Well, okay, first F is matching. This is good up until this point. Now, because we have a star with dot, which means we can have n number of occurrences of dot. And we know by definition that dot can represent any single character. So in this case, what we are going to have is, we are actually going to have 7 different dots. And these 7 different dots, they are going to represent each character that is missing in the remaining string. And then eventually when we reach to the end, we are going to declare this as a match and we will be able to return true in each of the cases. So I hope after so many examples, things would make sense and you would get the idea that what this problem is asking us to do. Basically, we need to return a Boolean answer, whether true or not. that whether any given two strings, do they match or not match. Okay, now before we come up with the solution, first let's see that what could be the different possibilities for our problem and what could be the different things we can do in the solution. Now I have drawn a table over here where I'm representing different like string values and pattern values, and we'll try to see that what happens in every single scenario and what are the actions we can take. Now I have noted that there could be like a C mentioned over here in this column file, and this means that it could be any character from A to Z, because in the string we can only strictly have A to Z characters. Meanwhile, for the pattern we could have definitely C, or we could also have a dot and a star. So that means different things, and if they are present we might have to do things a little bit differently. So first let's see the first scenario. In the first scenario, basically both the values we are given is like a simple character. So for S and P, suppose we are given the values like A, B, C and X, Y, Z. This is pretty simple to match that whether the string matches the pattern or not. We simply need to judge character by character. In this case, we can simply see that whether they are matching or they are not matching. This is a very simple binary operation. Second option we can have is the most beautiful option, that whether we are given one character and we are given a dot value. This is also very straightforward. If there is a dot present, definitely it matches the character. We can simply return that there is a match for that particular character. Second scenario is that we could be given bunch of different characters, and we could be given like some characters at the beginning, and then we might be given like a dot and a star. In this possibility, basically what we need to check is that whether like a single character like this first character, and whether this first character, I mean this could this could represent like more characters. These could represent something like a and like a dot star, something like that, right? There could be like different matching things. I'm just noting down C. But this means that if like the before portion matches, everything at this position is definitely going to match. So in this case, if like the values before the dot and star matches, then everything is a match, right? If we take a look at this example, basically we are simply given dot and star. In this case, 100% there is going to be a match. Why? Because all the values that are present over here, we can take like 0, 1 or bunch of different dots, and all of these dots can represent all the characters that we have. Now comes the interesting part where we are dealing with a star. What could be different possibilities? So let me give you like one possibility. Suppose for this our string and P value, we are given the values like A, B, and over here we are given the values as A, B, star. Question is this a match? Yes, this is a match. Why? Because this is the first value. This is a match in itself. And over here we only have one value of B. Now over here we have B star. So this B star could represent that we don't have any values, or we have one value of B, or we have two values of B, or we have infinite values of B all across like the board, whatever we want to choose. So in this case, we are definitely going to choose one value of B, which means this is a match. So in this case, what are we considering? Value before the like preceding value of star. So value before preceding value of star. If that is a match, definitely we can find a match, right? There could be another possibility. We could be given a string, we could be given a P, we could be given a bunch of different values like A, B, X, Y, Z, A, B, X, Y, Z. So far everything is a match over here. And then over here we are given something like 2, 3, 4, 5 Z's, right? And over here we are given like just a star value. In this case, how would you define that whether this is a match or not? Well, definitely this is a match. But the way you are going to define is that the values that this Z and star that we are considering, like these values, before that we are checking that whether all the values that are present before that, are they a match? If all of these values are match, definitely we can create this to be a match. So again, we are considering like all the values before the preceding value of star. I know I'm using a lot of abbreviations, but you just have to be with me. I'm not going to write all of them. And if that is a match, we can consider this to be a match. There is also one more possibility where we actually do not need to consider this like preceding value at all. What could be a scenario? Suppose we are given string as is equal to like a, b, c, d, and over here we are given some p is equal to a, y star, and then b, c, d. In this scenario, this is definitely a match. Why? Because for this y star, we are considering this to be 0. If this is being considered as 0 values, which means that this is a match, and then all the other values, they are match. So we will find a potential match over here. So again, we are considering like if the value before the preceding star, if that is a match, then we can consider this to be a match. So now we are just like dealing with lot of possibilities where every single time for value inside the pattern, we will have to keep track of the value, like two value before that whether that is a match or not. And in order to calculate any single calculation, we are always checking that whether the values before us, are they matching or not. So this is a very good candidate for a dynamic programming solution. Why a dynamic programming solution? Because first scenario, we are definitely like using whatever the results we have calculated to check that whether the current result we are at, if that is a good or not. Second, already calculated results are going to give us the ability to decide that what do we do in the current position, because we are not only dealing with like simple characters, we are also dealing with like a dot, and we are also dealing with a star. So this is going to be really helpful. And we can use something like recursion to solve this problem, but that is going to complicate things. We are actually going to use recursion with DP, and that is going to make things much more easier. So let's try to take one example over here. And the question is, for a dynamic programming, we are not only going, because we are dealing with two different like string and pattern, it would be better to create a 2D matrix. And inside the 2D matrix, for every single like string and every single pattern, we will try to see that whether the characters match or not. And based on their true and false values, we would be able to calculate some interesting results. So let's see that in action with an example, and that would make things more clear. Okay, so currently we have created an example for a string and a pattern, and we need to check that whether they match or not. Now also for this pattern, I have created a 2 by 2 matrix where inside every single row represents the string value we have, and every single column represents a character inside the pattern we have, and we will try to see that whether there is a match or not. Now remember, for the first row and column, I have kept it as empty. Why? Because these we are going to use to create our base case. Now our base case is that currently for the string, the first character we have is empty character, and also for the pattern, the first character we have is empty character. Now, because these two are empty characters, definitely empty characters are going to match for sure. So in this case, this value is always going to be true. Now we will try to see that whether there is a match over here or not. So in this case, because this is an empty character and we have some character over here, there is not going to be a match. So definitely we would always be able to like have all these values as false. So currently we are at this first position. This value is f, this value is f. Both of them are characters, both are same. And when both are same, we will also have to check that all the values before that, if they are also match or not. So currently the only values before that were two empty strings, and that represents this diagonal corner. So because this diagonal corner was true and we have matching set of characters, we are going to take the value that is diagonally present and put it at this position for this 1 1 box. Again, I'm repeating myself that because these two characters are same. So first we check, okay, these two characters are same. Then we check its diagonal value, because what this diagonal value is going to do is it is going to check that whether all the values before these two values, are they a match or not. And this will come in handy when we are at some position like this, because if over here we find this a to be matching, which means this value is a true, but do we need to keep it as true? Because if this is false, which means if we are, say for an example, we have string to be FA and we have patent to be PA. So in this case, though these two match, but this is not a match. Why? Because this F and P does not match. So we can break out immediately. And that is what we need to keep track of every single time. And that is why this is a dynamic programming problem. So in this case, as explained, this is going to be true. Okay, now again, let's start filling up all of these files. And what we are going to do is, okay, this one is true. Now we will have to check that, okay, currently we have FA and the value we are comparing it against is F. Is this a match? No, this is not a match. So this is going to be false. Again, currently the value is FA star and the only value we have is F. Is this a match? Yes, this is a match. Why? Because for this A star, we can actually consider this to be an empty string or zero values of A. And if we do that, then we will have no values over here. So in this case, this F and this F is match. And why this happened? Because we had a star value over here and we were dealing with the star value. So now again, the new theorem comes that whenever we are dealing with a star value, we will have to check the value before its preceding value. Again, whenever we are dealing with a star value, we will have to check the value before its preceding value. And if that is true, then we can directly mark true over here. So we check, okay, this was true. So definitely we are going to put true over here. Awesome. Now we are at this position number n. Now currently, what is the scenario we are comparing? We are comparing the values of F, A star, N, and we are comparing it with F. So N and F, there is no match. So definitely we can mark false over here. Now we add a dot over here. Again, there is a no match. So we can mark false over here. And same way, this is also going to be false. Okay, now we are at this position. So now we actually have two values, FA. Now for this FA, if we only compare it with this value F, is this a match? No, this is not a match. So we can mark false over here. Okay, now after marking false over here, currently we add this positions. Okay, so FA, definitely there is a match. So because these AA matches, we will compare its diagonal value, and the diagonal value we get this result, and we will mark the value over here. So this is going to be true. Awesome. Now currently we are at this FA star. So FA star, is this a match with this FA? Again, now we have the star value. So we will have to check. First thing we will have to check is whether we can consider this to be just like an F and empty string, or we can consider this to be an FA, or we can consider this to be an FAA. I'm talking about this value, right? And if we see this FA is a perfect match. So now because we have a star value again over here, we are going to mark this as true. But this true, we are getting it from the value before. Because remember, in this case, you must be wondering that, hey, for this particular position, this value is actually empty. Then why are we marking this to be true? We are marking this to be true because this one is true. Because we found a match of FA, and because this value is true, we will mark this as true. So let's do that. Awesome. Now currently the next value we have is like FAN, and this value we have is FA. So definitely there is no match. We will mark this as false, and if we add dot, we will again mark this as false, and blah blah blah. Right? These are all the values going to be false. Now currently we are at the position of FAA. Let me clean this up a bit. So currently we have FAA over here, and currently we only have F over here. So definitely this is going to be false. Again, this FA is also going to be false. Now again, we are at the critical juncture. We have a star value. Now because we have a star value, you must be wondering that what will be the possibility. Well, the possibility is, again, over here for this FA star, we can consider it to be like only F or FA or FAA. In this case, we are going to consider it to be FAA. Now you must be asking that, hey, previously when we were at this position, you mentioned that because this is true, we are marking this to be true. Then when we were at this position, you mentioned that though this was false, but because this was true, we were marking this to be true. Now we are at this position, this is also true, sorry, this is also false, this is also false. Then how come we are marking this as true? We are marking this as true because this value is true. Mind blown. Yes, this is like the most important point for this problem, that whenever there is a star present, we will have to check three different values. So whenever there is a star present, we were checking that whether the value before the preceding value, if that is true, we can mark this as true. If there is a star present, we will check that whether the value before this, if that is true, then also we can mark it true. And if there is a star present, we can check that whether the value above it, if that is true, then also we can mark it as true. Which means whenever we were at this position, if we don't want to get into all of these like calculations, all we need to do is that currently we are at this box, then we will have to check three different boxes. First box is the right, like before box. Second box is this one, like the box before box, and third box is a box above that box. So for this particular box, if either this or this, if any one of the value is true, we will need to mark that value over here. If all three are false, then only we will mark it as false. And why this happens? Because this was a star value and there could be bunch of different possibilities we can use over here. And this was the most difficult part of this problem, and congratulations, you understood it perfectly. And now because this was true, now currently we have this FAA, and now we have this like F. Now we are at the next value, so next value is FA star N, and this N is not a match, so this is going to be false, and then all the subsequent values are also going to be the false. Now this is a very easy problem to tackle, because now we are at this position N, so this is not a match, so this is going to be false, this is also going to be false, this is also going to be false. And now we are at this N and N, because both of these are characters, so there is a match. Because there is a match, we are going to consider it's like diagonal value, so diagonal value is true, so this is also going to be true. Now this is a dot value and we only have values up until this point, so which means we are going to mark this one as false, and we are also going to mark this one as false. Now again we are at this value number G, so all of these are going to be false up until this point. Now there is a dot over here and there is a G over here, which means there is a match. So if there is a match, we are going to compare its diagonal value. The diagonal value is T, so that is true. So because this one is true, this is also going to be true, and the last value is going to be false, because we only have value up until G up till this point, and we have this M over here. Now the last value is, okay, this is going to be false, 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 and this is also going to be false. Now we are at this last position. This M is a match with this M, so because this is a match, we are going to take its diagonal value, and the diagonal value in this case is true, so we are going to take this value as true. Now our dynamic programming table is complete, and all we need to do is we need to check this diagonal file, and we need to check this last value. Because this last value was true, we can return true in this case, and this would be the answer we need to return. And that is the whole logic behind this problem. And this was a very beautiful problem. If we were only dealing with the dot values, this would be much easy to solve, but because we were also dealing with the star value, it added a layer of complexity. Now if we see time complexity, in this case the time complexity is actually going to be big O of M cross N, where M is the length of a string and N is the length of the pattern. And if we see space complexity, because we are creating a 2x2 matrix, basically the space complexity is also going to be big O of M cross N. And this is a beautiful solution, like one of the best dynamic programming solutions I have seen so far. So I hope you would have enjoyed it. Now let's move on to the coding. First we will check for an edge case, that if both the values are null, we can simply return null. If that is not the case, we are going to initialize our dynamic programming 2D array, and for this 2D array, let's name it as DP, and we are going to assign the length of whatever the length of S is +1 and also length of P +1, and we are going to assign the base value of the 0 0 to be true. And now let's populate the first row. So this should take care of the first column. Now let's start our loop. So we are going to iterate over I and j, which means we are going to do 2 for loops. Inside the loop, we are going to check for all 3 different possibilities. So first possibility is that the given characters, the p is actually a dot. If that is the case, which means it would be able to match any single character, we are marking like the dp of I plus 1 and j plus 1 to its diagonal value. Now you must be wondering, why am I dealing with like I plus 1 and j plus 1? Because for the first row and first column, remember, we mark their values as 0 and we actually started the value of s and p on the first position. So that is why every single time I'm going to updating like I plus 1 and j plus 1 values, because the ith and jth value is actually located at like 0 0 position. They don't have any values. So if there is a dot present, we simply check the diagonal value. Now the second possibility is that both of them are characters, and if both are characters and they both match, we can also mark their value as same as their diagonal value. Now we are at the third possibility, and the third possibility is that if the given character, if that is in the pattern a star, if that is a star, then we will have to do some additional calculations. So now for first we are at the value star. So there could be two possibility. We could have some value as like character and a star, or we could have some value as like a dot and a star. So if there is a dot and a star, we only need to check that whether all the values before that, if they are match or not. And if that is the case, we would be good. We can mark it as true. And so first let's take care of the scenario that if the given value is actually a dot star. Now we have done that check, and then we will check all of those 3 boxes I mentioned, that if either one of them is true, we will simply add that value over here. With this value, we are actually comparing all of those 3 boxes. So if any one of them is true, we can mark it as true. And in the end, this concludes all the possibilities we can do inside our loop. So basically we are done with our calculation. Now simply in the end, we need to return that what was the last value inside our dynamic programming diagonal. That should be it. Let's try to run this code. Okay, seems like our solution is working as expected. Let's try to run this code. And our code runs pretty fast compared to a lot of other solutions, and which is really good. And it's great in terms of time complexity and also in terms of space complexity. And I would be posting this solution in the comments so you can check it out from there. Thank you. Hello friends, I'm a cloud solutions architect at Microsoft, and my aim is to empower every single person to be better at technical interviews. Keeping with that goal in mind, today we are going to solve a very interesting lead code problem called race car. And if we see, this has been one of the most popular problem at Google. Though not many companies have asked this, but the companies that did, they are really popular companies. So Google, Amazon, and Microsoft, they all have asked this question, and Google literally loves this question. So let's start understanding the problem statement. So this is a lead code hard problem, and quite justifiably this is a hard problem. Basically, we are given a car that is currently located at position number 0, and the initial speed it has is +1. Now we are dealing with two factors here. First factor is that we have the ability to accelerate the car, and second factor is that we have the ability to hit the reverse button or reverse instruction in the car. And we are told that car can go infinitely in a number line, and car can go in like positive direction or negative direction, and basically it follows whatever the instructions we are providing. So what does these accelerate and reverse instruction means? Basically, whenever we hit the accelerate instruction, car is going to change its position. So car is going to change its position based on whatever speed it had previously, and then its speed is going to double. So what it means, I'll explain it to you just in a second. Also, if we see the instructions for the reverse button, basically whenever we hit the reverse button, whatever the speed of our car was, if it was positive speed or if it was going in the positive direction, basically the speed is gonna turn to -1, or if it was going in the negative direction, the speed is gonna turn to +1. So basically car is gonna change its direction, and also speed will come back to 1. But the car's position is gonna remain same, which means car will only move when we hit the accelerate button, but this reverse button is there to dictate that which direction the car moves into. Okay, so now I have drawn a numbers line over here, and now we will see that based on different instruction, how does our car proceed and what are the different changes it happens. So we have few factors that we need to consider in this case. First factor is instructions that we are providing. Second one is what is the current position, what is the speed, and what direction the car is going into. So let's start with this one. Let's start filling up with the initial positions. So initially car is located at position 0 and initial speed is 1. These are the two factors that we are given by default. Now as for the instructions, suppose we provide the instructions to accelerate car. What would happen is initially car was located at position number 0, which was this one, right? So previously car was here. Now we provided the instructions to accelerate. And also one more thing I forgot to mention, the direction, currently we are going in the positive direction because the speed is positive. Now the position is going to become position speed plus speed. So 0 plus 1, it's going to become 1, and speed is also going to update to multiply by 2. So now this is the new position of the car, and the speed is 2, but that will come in effect when we provide the next instructions for the acceleration. So let's do that. If we add one more instructions for acceleration, what is going to happen is that, okay, currently the position was 1, but now we are providing the accelerate instruction. So basically it's going to be 1 plus 2. So now position is going to become 3. So currently our car ends up at position number 3, and the speed is going to become 4 because speed multiplies by 2 every single time. If we add one more instructions for accelerate, basically our car is going to end up at 3 plus 4, it is going to be 7. So let's just clean this up a bit. So now the position becomes 7, our speed becomes 8, and car's position is 7 currently. So this is what happened after 3 instructions that we provided. That initially our car was at position 0, then it came to 1, then 3, and then 7. But notice all of these are just accelerate instructions that we have provided. Let's try providing a reverse instructions. If we provide a reverse instruction, basically currently the speed is plus 8. So this is a positive speed. We are told that if the speed is positive, speed is going to turn negative. So this is going to become minus 1, which means that direction that previously we were going in the right side of direction, now we are going in the left side of the direction. We are going to proceed negatively. Remember, car's position is not gonna change because that is what we are told that the definition of this instruction right is. So now currently car is still located at this position number 7. Now let's try to put one accelerate. If we put one accelerate, what is going to happen? Well, position is going to change. Position is going to become 7 plus whatever the speed is, and speed in this case is -1. So 7 plus -1 is going to become 6, which means that now the position of car is going to end up at this position number 6, and speed is also going to double. So now speed was -1, so speed would be -2. Let's add one more accelerate. If we add one more accelerate, basically this is what this is going to do is that current position is 6. So 6 plus -2, this is going to end up at position number 4. So now car ends up at position number 4, and the speed will become -4 for the next iteration. Say for example, we decide to add one more reverse over here. If we add one more reverse, basically nothing is going to change in the position. Position is still going to be at value number 4, but the speed that was originally minus a negative value, now it is going to become +1. So if it becomes +1, which means that the direction now on is going to go on the right side. And this is the whole logic of this accelerate and reverse instruction means, and this is what happens on the number sequence. So after understanding this, let's see that what does the question is asking us to find. Basically in the question we are given a target value, and we are told that we are initially starting at the position number 0 and with the speed 1. So we need to see that what is the shortest sequence of instructions that we can provide that will get us there, and we need to return the length of those instructions. So let's try to see what does this mean and see a couple of examples that what this is asking us to do. So I made some changes, and we also added one parameter target that we need to consider. So say for an example, suppose we are given the target value to be 3. So we need to reach at the position number 3 inside our linear distance that we are given. So let's see that what is going to be the shortest set of instructions. So if we provide one accelerate, which means position is going to become 0 plus 1, it's going to become 1. Now speed is going to become 2 for the next step, and our car is going to end up over here. Now let's add one more accelerate. If we add one more accelerate, basically our original position was 1, so 1 plus 2 is going to become 3. This 3 is critical because this is what the target is asking us to find. So we have already reached the target value, and speed, like, it's going to become 4, but this is not going to be of concern because we already hit our target value. So since we hit our target value and this is the shortest possible way to do it, it took us 2 instructions to reach to the target value 3. So in this case, as the answer, we are going to return 2, that we need minimum of 2 instructions to reach to the target value of 3. Say for an example, we take one more consideration. So in this case, we provide the first instructions of A. So in this case, our position is going to become 1, our speed is going to become 2, our car is going to end up over here. We add one more accelerate. In this case, our car is going to end up over here, our position is going to become 3, and our speed is going to become 4. Let's put one more A. So our car is going to end up over here, and we are going to, the position is going to be 7, the speed is going to be 8. The thing is, we were intending to reach to this position number 6, but this 7 is actually greater than 6, which means we have already surpassed it. So we need to come back, which means we will have to change the direction. So previously the direction we were going is in the right side direction. We will have to change the direction. Whenever we have to change the direction, we are going to use a reverse. If we use the reverse position, car's position is not going to change, but speed is going to become -1. Now because the speed is -1, let's try to add one more accelerate. If we add one more accelerate, basically the position is going to become 7 plus -1, so it's going to become 6, and our car is going to end up at value number 6. Now the speed is going to become -2 for the next iteration, but we don't care, and in this case the target value 6 has been achieved. If we see how many instructions it took us 5 instructions to get there. So in the answer we are going to return 5, that we need minimum 5 instructions to reach to target value number 6. And this is what the problem is asking us to solve. Now let's see that what are going to be the different approaches to solve this problem. Well, there are actually 2 ways to solve this problem. First way is to treat like every single value as nodes and use like a breadth first search to solve this problem, and treating this as a graph problem. The other way to solve this problem is treating this as a dynamic programming problem. And Google is actually huge in dynamic programming concern. Like, they really love their dynamic programming concepts, and this is what I'm going to show you in this approach. So let me know in the comments if you want to see the BFS solution as well. I can show it to you maybe sometime in the future. So before we come up with the optimal solution, first let's try to understand that what are the moves of accelerate and how it works for every single instructions. Suppose, okay, initial position is going to be 0 and initial speed is going to be 1. We all know that. If we add one instruction of A, okay, our car is going to end up over here. This was the first position, right? If we add one more instruction of A, our car is going to end up over here. If we add one more instruction of A, our car is going to end up at position number 7, and if we add one more instruction of A, our car is going to end up at position number 15. Why this happens? Because speed gets multiplied by 2 with every single occurrence of A, and that is where we are doing like position addition, right? So is there a mathematical sense behind these values? And yes, there is. How can we define that? Suppose we define a parameter called x that refers to the number of accelerations we use. So in this case, currently we have used 4 accelerations. So currently x is going to be 4, right? We are just using some arbitrary variable to define a mathematical equation. Now in this case, if we directly want to know that what is going to be the position based on the number of x, can we directly know it? Yes. The equation is, if we do 2 to the power of x minus 1, then it will provide us that for any number of accelerations, what is going to be the position of the car. And this is a really important thing to find. Now, how can we define this theorem? So say for an example, if we are originally given only with 2 A's, So 2 times we are using this. So currently x is equal to 2. We know that when we provide 2 accelerations, the value we have is car is going to be position number 3. If we apply this formula, basically it's going to be 2 to the power of 2 minus 1. So 4 minus 1 is going to be 3, which is correct. Same way, if we try to apply x to be 4, in this case, the answer is going to be 2 to the power of 4 minus 1, which is going to be 16 minus 1, which is 15, and which is what we calculated. And why this is happening? Because every single time speed is being multiplied by 2. So we can actually see a relationship forming between the position of car by the value of a. And the important thing is a is only being used to move the car. So car can move in this direction or this direction. That depends on the value of r. But the thing is, car is only going to move based on the value of a. Okay, now after knowing that what are going to be different possibilities of a, there can be 3 distinct possibilities for us to find the target value. Suppose the target value we are given, it is located someplace like this, right? Now there can be 3 distinct possibilities, and currently we are only considering that we are only using accelerate function. We are not using reverse function for now. When we use it, I'll let you know. So first possibility is that we find some arbitrary value of accelerate that gets us somewhere over here, which means we are not at target value, but we are one value before that can, like, as further as we can get near the target value using only accelerate. Another possibility is that if we do one more accelerate, we go beyond the target value and we reach somewhere in this area. Now the third possibility is that if we only use accelerate function, we directly hit the target value. If this is the case, this is going to be like the minimum number of effort we need to find the answer. And this is going to be the best case scenario, but that rarely happens. There can be infinite numbers and there are only so many numbers that can directly hit A. So now let's see that what would happen in each of these scenarios where either we are located before the target value or we are at after target value. What should be our approach in each scenario, right? So let's try to understand this logic with something important concepts. First concept is that, say for an example, we are in a scenario where our position is somewhere over here and this is the target value, and if we do one more direct acceleration, we are jumping away. So other logic is that we already know how much effort it took to get here, right? We have already those sets of instructions, so we won't bother doing anything. But now from this point, we can actually break down the problem in a smaller sub problem where we only need to check that how much effort it takes to make these moves. And we can actually do that. Why? Because at this position, whatever the speed is, say for example speed is 8, right? If we use a reverse in this case, speed is directly going to be -1, which means we have the ability to go like on this direction, and it could be beneficial to go in this direction for a bit and then come back directly towards the target direction, because we already have the equation that position is going to be 2 to the power of x minus 1. And using this, we can do some pretty cool results, right? Now in this case, if we slow down over here, if we use a right over here, which means immediately we have 2 possibilities. Either we can use accelerate and go in this direction, or from here we can directly use one more reverse and then directly go to this T. Because if we slow down here, we definitely would have to use 2 different R's, because first R is going to make the direction go negative and second R is going to make the direction go positive, and then we would be able to reach to this target value. That is one logic. Second logic is, suppose we are in an opposite scenario where the target value we are given, it is located here, and the answer we are trying to find, or based on the accelerates we did, we end up somewhere over here. So if we have already gone beyond the target value, the basic logic is that we definitely will have to use the reverse gear, and after using the reverse gear, our speed is going to go in that direction. We only need to be concerned about finding this smaller path rather than finding the whole path. So we are only finding the difference between, say for example, this is the target value and this value we call it like I value. So we are only considering to finding that how many moves it takes for us to do like I minus t target value, and this is a smaller sub problem. And same way, in this scenario, suppose this is value I and this is value t. So in this case, we are finding a smaller sub problem t minus I to find that how many moves it takes to do this. And we keep on breaking this again and again and again until the point where we reach to a target position, and using acceleration we get to the same value and then we mark its moves. So this is the whole logic of the solution we are going to use. And for every single position there can be different options we can take, but basically this is how we are breaking a bigger problem and grinding down in the smaller sub problems to find the answer that we need. So basically we are using dynamic programming at its finest. So let's see that with some of the examples how we can actually solve this problem, and at the same time we are also going to use some logic to our advantage. The logic we are going to use is that we are going to initialize a DP array. Now inside this DP array, we are actually going to mark the positions of accelerations using the formula we already established, that is 2 to the power of x minus 1. And over here we are going to mention the index values as the number of a's or the number of x in this case. And we are going to see that what position does it ends up at. So if this is 0, this is definitely 0. Then for the this is 1, this is going to be 3, and this is going to be 7, and this is going to be 15, right? These are the different possibilities we have. I have already drawn a number series over here as well. Now say for an example, the target value we are given, the target value is value number 7. If the target value is value number 7, do we need to do any calculations? No, right? Because we can directly see over here that this provides us the value of 7. Then basically it takes us 3 steps to reach to the value target number 7. So in the answer we can directly return 7 as the answer. And why we were able to do it? Because we only use acceleration to get there. So this is like the best case scenario. This is one of the examples. Say for an example, the given problem is not so simple. Suppose the given target we have is value number 9. What we are going to do in this case? Now things becomes a little bit tricky, right? We are trying to reach this target value. We already have our this DP array. So based on this, we already know that target falls between these two values. So it has to be playing around between these two numbers, right? So let's mark both of them down. So first, this is the first position that we can reach, and it takes us 3 steps to get there. So we already know that there is an effort of 3 steps to get to the value number 7, and our aim is to reach to the target value number 9, right? Also there is another possibility that we can end up at value number 15, and it takes us like 4 steps to get to this value number 15. So now let's just mark down all the 3 steps that we took to get over here, and we are also marking down all the 4 steps that we get to reach to this value number 15. And now we will try to break the problem into a smaller sub problem. And the smaller sub problem is that what is missing over here? We need to recover these 2 steps. How we are going to recover these 2 steps? How many effort it takes us for each 2 steps? If we look at this DP array, we do not find a direct entry that can only be done using only accelerate values, right? But what we can do is, at this position number 7, we can add a reverse over here. If we add a reverse over here, what's gonna happen is that now speed at this position is going to become -1, and currently, okay, so position is 7 and speed became -1, right? Now what are some of the interesting things we can do? First interesting thing we can do is we can try to find that if we go in this direction and we are able to calculate some direct DP that we can make. So say for an example, if we take 1 step, now the position is going to become 6, the speed is going to become -2, and over here we took 1a, and currently this is the position. And now what is the difference between these 2 entries? The difference is actually 3. We can directly make. So let's see that what is going to be the effort to make this answer viable, right? The effort is that now at this position we will have to do another reverse. So if we do another reverse, the value is going to become 1. And now we need to move 3 steps. So 3 steps means 2 accelerations. So we can do 2 accelerations. What is the cost of this one? The cost of this is 1, 2, 3, 4, 5, 6, 7, 8. So in total, it took us 8 steps to get here. Still have one more possibility. And that possibility is that we need to find the target value to be 9 and we have this 15. So let's see that how much effort it takes for us to get there. Okay, now currently we are at this position number 4 and currently we have 4 A's. Now we need to change the direction, so we hit a reverse and now the distance we need to cover is 6. From the previous example, we already know that if we want to cover 6 direction, basically we need 5 steps. I'm not going to go in detail on showing all 5 steps, but that is how many number of steps we need. So let's see that what would be the effort in this case, because previously the best we could find is 8, but in this case the effort is these many steps plus 5 steps. And notice we only have to use a single R over here, because once we change the direction, we don't need to change the direction again, because it's in our favor to keep the same direction. In this case, the answer is actually going to become 10 steps. So again, 8 is going to be the best number of steps we can do in order to find the target, what are the minimum values needed for target value number 9. And in this case, we are going to mark 8 as the answer. Let's do a quick recap on all the things we did. So the number of things we did is, okay, this was the target value. We choose what is the minimum A that gets us and what is the next A that gets us. And then we try to make this distance by comparing all the possibilities. So over here, we actually went backwards and then we went frontwards. But we were able to do it pretty quickly because we had this DP array setup. If we see time and space complexity, in this case, the time complexity is actually going to be big O of n log n. And space complexity is actually going to be big O of log n. Now, why we are dealing with a logarithmic time complexity? Because remember, with every single jump, we are actually jumping in 2 to the power of n. So we are eliminating lot of values with every single jump. And this is a very good time and space complexity. So I hope you would have liked this explanation. Now let's move on to the coding. So before we start implementing the race car function, we are actually going to create a helper method. So let's initialize our recursive helper method. So after initializing our helper method, we are going to check for a condition that if the given value inside the dynamic programming array, if that is greater than or equal to 0, we are simply going to mark it as our successful case. If that is not the case, we are going to assign the current value of dp to be the maximum value possible. Now let's initialize our couple of variables. So first we are initializing our variable x, and that is going to be of the value 1. And we are also going to initialize a value called j, and that is going to help us to iterate over the smaller distance. Okay, now we are going to run our for loop, and inside the for loop we are going to utilize the function of like 2 to the power of x minus 1, and basically we are going to keep updating the value of j until we come to a position where we are just before the target value. And after doing that, inside we are also going to initialize a for loop to find the smallest distance between the two values. So all we will have to do is every single time we are going to calculate the value of dp of I, and for that we are going to compare that what is the minimum cost that is happening for us. So we are going to compare the value of the dp of I that we have already stored, or we are also going to compare the value of the given number of steps we need to take, so number of x, plus we will also have to add one more value, that is to take care of one reverse function, and we will also have to add one more value, that is to take care of the another reverse function, and we will also have to take care of the number of queues that we need to jump, and plus we will also have to call the recursive function and see how many steps does that takes in order for us to get there. So over here we are going to provide the value of the target minus the number of j minus p that we received. So this is the jump that we take, and we are also going to provide our DP array that we have created. And basically this is the whole logic behind our solution. And once that is done, basically we can get out of the loop, and now we can compare again the smallest result possible. So for this scenario, what we are going to do is we are actually going to again compare the two values, and inside the two values, first value is going to be the existing dp of I value that we have received from running this loop, and second value we are going to compare it is going to be this second scenario takes care where we are actually jumping one step above the given values, and in the end we simply need to return the smallest number that we have been able to find from our main function. We will have to make call to this one, and we will also have to initialize our dp array, also going to fill the value with all the negative values except the first one. And now we are going to call our function. Okay, seems like our solution is working as expected. I put I in place of target at many places, so I just fixed that. And now let's try to submit the code. Okay, seems like our solution is working as expected, and it is reasonably faster than a lot of other solutions. And I know this was a very tough problem to understand. I hope you had a good chance to understand the explanation and also go through the code a couple of times. I'm going to post this in the comments, and I also have my own GitHub repository where I have solved like a lot of different problems, and I'm going to put the code here as well. So it's up to you wherever you want to check the code from. uh, I hope you like the explanation. So today we are going to do a full course on greedy algorithms, and we are going to learn everything there is to know. And I can guarantee you that by the end of this course, you would become a complete pro on all sorts of greedy questions. You would be able to identify, understand, and solve them flawlessly. So without any delay, let's get started with the course. So greedy algorithm is nothing but a problem solving technique where you take the given problem and try to carve out the biggest possible solution you can, and then try to deal with the remaining portion, and also again repeat the same problem, and even with the remaining portion of the problem you also try to carve out the biggest solution that you can, and so on and so forth. So you basically break a problem down into sub problems, and then even in the sub problems you also repeat the same approach, but at every given chance you are trying to find your best way to solve as much of a problem as you can. Let's try to understand this with an example. Suppose you are a cashier at one of the gas station, and you realize that someone comes to you with $100 bill who only had the amount that you need to charge was $67.35. Let's say that this was their bill and they hand you over $100. What is going to be your first approach? The immediate thing that would come to your mind is that you need to return $22.65 to that person. Now if you have to return $22.65, the first thing you are going to do is take out the biggest chunk by the biggest denomination of money. So you are going to take a $20 bill, which means now the remaining amount is going to be $2.65. Once again, for this one you are also going to repeat the same problem and same approach. So you are going to take a $2 coin, and yes, in Canada we have $2 coins, so we can use that, or a $2 bill. And then now you only have to deal with 65 cents, and for 65 cents once again you are going to take 2 quarters, so that is going to be 50 cents. And now for the remaining 15 cents you can take one dime, so 10 cents, and one nickel, so that is 5 cents. And overall with this denomination you would have created basically the ideal amount of money that you will have to return to that particular person, and you can just hand them over. This is where you took the biggest problem, that is that you need to return to $22.65, and then you started breaking this down into the subsequent portion of the different denominations that you could, and at every given step you were being greedy and you were trying to solve the most amount of problem at any given point. And that's the whole approach on solving greedy problem. Now, if you see the structure of the greedy problem, it looks very similar to a lot of other approaches that we have seen. Number one, it seems very similar to dynamic programming approach. Second thing, it seems very similar to recursive approaches that we see, because we are dealing with solving sub problem within a sub problem within a sub problem for different inputs. And third thing is, many times you can also consider it closely related with most simple brute force approach. And you would be true in saying that greedy approach looks very similar to all of these three techniques, but there are slight variations and differences. First, let's understand that what is going to be the difference between a greedy approach and a dynamic programming approach. Well, for the greedy approach, you are trying to solve the biggest chunk of the problem. That's it. But in the dynamic programming approach, you actually take a problem and you break the problem in sub pieces, and for those sub pieces you try to store their answer, and based on that stored result you try to build more sub pieces, and then you build your solution. So if we have to consider greedy approach, you can treat it as if eating a cake, where you have a big cake, you take out a big chunk of the cake, so now you are only dealing with a smaller sub portion of the cake, and once again you can take out the biggest chunk, and now you are only dealing with even smaller portion of that cake. But meanwhile, in a dynamic programming, you can treat it as building bunch of different Lego bricks, and based on the combination of having these Lego bricks, you would be able to combine them together to build your solution in a particular fashion on top of already computed results. So this is the visual difference between a greedy approach and a dynamic programming approach. And you would see in many problems where you would feel like, hey, this should be solved using greedy approach, but eventually you would hit a brick wall, and you would find that dynamic programming would be much better way, and vice versa. So you would always be using these two tandemly, interchangeably, and you can make that judgment call that what do I need to choose, a greedy approach or dynamic programming approach. Next thing is that what is the key characteristics to understand that this is a good suitable candidate for a greedy problem solution. Number one thing is, it should have an optimal substructure. So what do I mean by optimal substructure? Well, because originally you are trying to solve a bigger problem, and you are taking some or majority of the portion out of that problem, and now you are only trying to solve a smaller problem, and once again repeating the same process, so on and so forth. So this is a good candidate to understand that, hey, can I apply greedy solution to this? Let's go back to our question of the cashier who was trying to break money, because originally the cashier had a bigger amount that needed to be returned, and then after taking a big chunk out of it, $20, we still had a smaller amount that would still needed to be returned, and we would apply the same logic on top of it. So that is number one. Number two thing is, whenever you are trying to deal with maximizing or benefiting from your input. So let's say that I give you an example. Let's say even in the cashier's problem, I would have told you that you need to return the change in the minimum possible bills or coins, and that minimum word would be a key characteristics or a key phrase for you to understand that, hey, let me try to solve this problem using greedy approach. So whenever you are trying to maximize your profit or minimize the amount of work that you have to do, or there is the greatest value that you are trying to find or the lowest value that you are trying to achieve, some keywords like this, if whenever you see something like this, always think that, can I use greedy approach to solve this problem? And more likely than not, you would be able to do it. Like if you see a very popular example, we have a very famous algorithm called Prim's minimum spanning algorithm, and I have done a separate video on this, and you can find it at any different place. But this algorithm typically uses the greedy approach, where if you are trying to traverse between any two particular node at any given moment, all you need to do is you need to pick the direction which leads the smallest edge weight, and if you keep on doing that, basically you would be able to traverse the entire tree in the minimum spanning or with minimum cost. And that's a great example on how this very popular and very famous tree and graph related algorithm can use greedy algorithm technique to basically exist. So there are many benefits of using greedy algorithms, and we are going to see about everything about all of them in the top 10 lead code problems that we are going to solve. So now, without any delay, I won't spend much time explaining the theory. I would rather explain you these 10 problems, and you would be able to understand that what different problems can be asked, what are the pattern that we are trying to recognize over here, and how do they actually work. So without any delay, let's get started with these questions now. Today we are going to do maximum sub-array lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like LinkedIn, Amazon, Apple, Microsoft, Google, Adobe, Facebook, Bloomberg, Uber, ByteDance, Yahoo, eBay, and Splunk. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a lead code medium problem and very well like problem on lead code. Basically, we are given an array called nums and we need to find a continuous sub array which has the largest sum and then return the sum value. We are also told that a sub array is a continuous part of any array, so we are given the definition of it. Now let's try to understand this with an example. So suppose this is the example we are given. Well, I have actually drawn this example in much bigger format over here. So for this example, what we are going to do is we are going to see different sub arrays, and then we are going to see that what is the maximum sum we are able to find so far, and then in the end we will return whatever the maximum sum we have found. So first of all, this value is actually -2. So because this value is -2, even if all the remaining values they are positive, it makes no sense for us to keep this value. So we are going to ignore this value and we are not going to keep it in our current sub array. Now this value is +1, so that is good. But again, combination of these two is actually -2. So again, we cannot keep this in the our continuous sub array. Well, now this value is actually +4, and which is good sign. Now these two values, this is again still +3, which is also a good sign, and the combination of these three is again 5, and then we add this value, so this becomes 6, and we are going to keep on updating the max value as well. So max value so far we have found so far is 6. That we can say that up until this point, the sub array there where we have found the maximum value to be is 6. Now this is again -5. So if we do 6 plus -5, we still get +1 value, which is again positive. So we are keeping this as a sub array, and then again this value is +4. So +4 plus 1 becomes +5. So this is also positive. The thing is, in the end, up until this point, the maximum value we were able to find is 6. So because it was 6, we are going to return 6 as the answer. This is what the problem is asking us to do. We need to find the sum of maximum sub array and then return that value. So let's see what would be different approaches to solve this problem. Basically, we need to find the maximum sub array. What we can do is we will try to find every single possible sub array, try to see the sum of all of those characters, and whichever possess the maximum sum, we simply return that sum. So let's see that in action. So first of all, what we are going to do is we are going to take sum of this character, then we are going to take sum of these two characters, then we are going to take sum of these three characters, and so on and so forth. We are keep on repeating the process with the first element. After we are done with this, essentially we are going to get rid of this first element, and now whatever the remaining elements are, we are going to start taking some of those values. So in this case, what again we are going to do is we will take this element, then again we will take these two elements, and again we will take these three elements, and overall we will keep on making the sum, and eventually we would find the answer, and the answer in this case is going to be the sum of these three characters, and whatever the answer is, we can simply return that. So this approach would work as expected, but the issue with this brute force solution is actually that we are doing a lot of repetitive work. If we see the time complexity in this case, the time complexity is actually going to be big O of n square. So let's see that what would be the better way to solve this. Before we come up with the optimal solution, first of all, let's make a couple of things very clear. What is our aim and what is the thing that we are trying to find? Well, basically we are trying to find that what is the maximum sum sub array. At any given moment, there can be any current subarray that we are iterating over, which could be the maximum subarray or could not be the maximum subarray. We don't know. But at any given moment, we will need to have the ability to keep track of sum of all the characters that are present in that particular subarray. So which means that we are going to have a variable called current or current subarray, where we are going to keep track of the sum of all the current variables that we have iterated over and we are keeping track of. Well, second thing is,
that we need to find the maximum subarray, and amongst any of the subarrays, anyone could be the maximum subarray. So we are also going to keep track of another variable called maximum subarray, where we are going to keep track of maximum current sum we have found so far. So well, these two things are understandable, right? They are from programming perspective. But there is also one more thing that is actually rational, and the rational thing is that at any given moment, suppose this value is actually -3. So current sum or current subarray we have found is actually -3. So if this value is -3, because this value is negative, so if this value is negative, even though all the remaining values they are positive and they keep on increasing the value in size, this -3 is always going to have to cause them to have a lesser value. So if that is the case, why are we even bothering to keeping this value at our bay or at our disposal? So the idea is at any given moment for our current subarray, the moment we would identify that the current value or some set of current values, they are causing it to have a negative value. If that is the case, we are going to immediately update our current subarray, and then we will keep on moving towards the next values. And based on these two logics, all we are going to do is we are going to iterate over our given array and keep on going to updating the current subarray, and then keep on updating the maximum subarray we have found so far, and in the end we should be able to find the answer. So let's see that traversal in action. Before we start iterating over this array, we are going to define some default values for this current and maximum variable. The default value for current is going to be the 0, and for maximum it's going to be whatever the first element of this given array is, which is -3. That is to cover an edge case where we are only given one element. Now let's start iterating over. Okay, so now the sum of these two elements is actually going to be -3 plus 2. So -3 plus 2 is actually going to be -1, which is still less than 0. So because this is less than 0, we are not going to update our current max variable, and the maximum sum we are actually able to find so far is going to be 0, which is definitely greater than -3. Now again, for these three variables, again the sum is going to be negative, so we are not going to do anything, and we are going to ignore all three of these cases. Now this value is actually positive, so because this value is positive, the current sum we have is going to be 8, so which means we will have to update the maximum sum we have found so far to be the value 8 as well. Now again we add the sum of these two values, so 8 plus -1, so 8 plus -1 actually becomes 7. So this becomes 7, which is less than whatever the maximum value we have found so far, so we don't need to update the max variable. Now we again add this value to our current sum, so 7 plus 2, 7 plus 2 is 9, 9 is greater than whatever the maximum value we had, so this becomes 9. Okay, now again this is also a positive value 3, so we can do 9 plus 3, which becomes 12. So we are again going to add the value 12 to our maximum sum that we have been able to find so far, and then this value is actually -5, so we can do 12 plus -5, so 12 plus -5 is going to be 7. And again, because this value is still positive, we are keeping this current subarray going on, because we don't know, future values might be positive values, and this can also go up pretty quickly. Now we have actually reached to the end of this array, and we don't have any more elements to go over, so the maximum sum we have found so far is 12, and this is what we need to return as the answer in this case. And so this is the most optimal approach to solve this problem. If we see time and space complexity, in this case the time complexity is actually going to be big O of n. Why big O of n? Because we will have to iterate over every single array or every single value that is present inside this given array, which takes big O of n time. If we see space complexity, in this case the space complexity is actually big O of 1 or constant space, because apart from storing these couple of variables, we are not using any additional space, so that's why space complexity is very minimal. First of all, we are going to initialize two variables called current sum and maximum sum. For current sum, we are going to initialize the value to be 0, and for maximum sum, we are going to initialize the value to be the first value inside this given nums array. We are going to create a for loop to iterate over this given array. Now we are going to check that whether the current sum, if that is less than 0 or not. If that is less than 0, we are going to update the value of current sum to 0. That is not the case. We are going to calculate the value for current sum and maximum sum. So current sum is going to be current sum plus whatever the current value inside this given nums array we have, and we will have to check that whether the current sum we have created, if that is the maximum sum or not. And after loop ends, we simply have to return maximum sum. Let's try to run this code. Seems like our solution is working as expected. Let's submit this code. and our code runs pretty efficiently. I would be posting this in the comments so you can check it out from there. Thank you.
Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do jump game problem. Recently this problem has been asked in Amazon, Facebook, Apple, Google, Oracle, TikTok, all these gigantic companies, and they are some of my dream companies. So I'm going to do my utmost focus for this video, and I hope that you find it enjoyable. This is going to be the framework for the video. First we are going to understand the problem, then we will come up with a brute force approach. We'll improve our brute force approach. We'll find the optimal solution, and then we'll write the Java code for the optimal solution. This is a medium problem, and we are given an integer array nums, and we are initially positioned at the first index, so 0th index. Each element in the array represents that that is the maximum jump we can take, and if that is true, can we reach to the last position? So if we are able to reach to the last position, we would return true. If we cannot reach, we will return false. So let's understand this with an example. Suppose our given input is like 2, 3, 1, 1 and 4, and initially we are located at this position. This is the same example over here. So we can see that if we over here we can take maximum 2 jumps. So either we can take 1 jump and reach over here, or we can take 2 jumps and reach over here. Let's get the greedy approach, and we'll take the maximum amount of jumps. So over here if we take 2 jumps, we end up over here. Over here the maximum jump we can take is only 1, so we'll reach over here. Again the maximum jump we can take is just 1, so we'll reach over here, and this is our last position. So since we have reached over here, which means that we can conclude that we can solve this jump game, and we can reach to this end position. So we'll return true in this case. Now let's take one more example. So suppose we are given input like this: 3, 2, 1, 0 and 4, and if we check for the possibility, so over here the maximum number of jumps we can take is 3 jumps. So if we take 3 jumps, we reach at 0. From 0 we can't move anywhere forward. So let's, rather than taking 3 jumps, we'll try to take 2 jumps. So if we take 2 jumps, we end up over here, and over here the maximum we can take is just 1 jump. So again we end up at 0. And lastly, rather than taking 2 jumps from here, we'll just take 1 jump. So we'll end up over here at this position number 2. Now at this 2, the maximum jumps we can take is 2. So again we end up at the 0, which means that in any circumstances, if we start at this position number 1, we cannot reach to this last position. So over here we would return false. This is basically the problem statement. I have given a custom example that we are at any position. We are going to first of all see that what is the maximum jump we can take. We'll try to make that jump. We'll try to see that using that jump, if we can reach to this end index. If we cannot reach to the end index somehow, we will backtrack. We will go back to the position where we initially took the jump from, and we'll try some other possibilities. So let's see that in action. So over here we are initially at this position number 2. The maximum jump we can take is at value number 2. So that jump will bring us over here. Now over here the maximum jump we can take is at this position 0, which means that we can't move any further. So we will backtrack. We will come back over here. Now again we are at this second position. Now let's, rather than taking the 2 jump, we will reduce our jumping possibility, and we will just take jump of 1 step. So now we reach at this value number 3. And over here with this value number 3, we can take maximum jump of 3 steps, which means that we can, if we take 3 steps, we will end up over here. So 1, 2, 3. And at this position 2, the maximum number of steps we can take is 2, which means that even if we take 2 steps, we will cross our last entry, which means that in any case, we would be able to reach to this last element, and we would return true in this scenario. Now this approach seems sensible on pen and paper, because we are dealing with a small number of things, small number of input, and we are able to clearly see that how the pattern is going on. So let's take another example. So these are the values. Let me also denote the index values for these. Now with every single iteration, I'm going to note down the index value transition we are making. Okay, so initially we are at this position number 5. The maximum jump we can take is a 5 step, which means that we would end up over here. So initially we would do something like this. So 0 to 5. This is one step we take. We are at 0 position, which means we can't go forward, which means we have to backtrack, which means that again from 5 we will come back to this 0th index. Now from 5, rather than making a jump of 5 steps, we will make jump of 4 steps, and we would end up at this position 4. So from 0 we would end up at this position 4. Now from this 4, the maximum jump we can make is 1. So again we will take one step jump and we would end up at this position 5. Again from we are at 0, we can't do anything, so we will have to backtrack. So in order to backtrack, we will go back to this position number 4. Again we have to backtrack from this position 4, so we will end up at 0. Again we will, rather than making a jump of 4 step, we'll make a jump of 3 step and we'll end up over here. So we end up over here, and so on and so forth. So you can see that this in this approach, all we are doing is just we are going someplace, we are coming back. Again we are going, and then again we are coming back. Again we are going to some next element, we are going to some next element, and we are coming back. And suppose this keeps repeating multiple times, you are essentially depleting your resources, because if you see the time complexity at any single iteration or at any single value, we have two possibilities: whether we want to keep this value in our current transition, or we do not want to keep our value keep this value in our current path that we are calculating. Which means that the input, if we make decision tree, the decision tree would keep on growing and growing with addition of every single value, which means that we are basically making a lot of decisions, and the time complexity in this scenario would actually be big O of 2 to the power n, because at every single position we are making two possibilities. This is a very bad exponential time complexity which we cannot allow in any scenario. Okay, so the issue in the brute force approach we had is that we were doing a lot of repetitive work, because at any point we found out that we are not able to make any progress from this point. We were still ending up at that point. So let's see that how can we counter that with a better approach. Suppose we create an additional data structure over here. So we create a dynamic programmatically additional data structure over here. Let's create an array, and in that array we are going to define that at any position can we reach to this endpoint. And if we identify that yes, we can reach to this endpoint, we would basically fill that position as true. And let's see that how it can help us. So if at any point in time we are at this final position, we know that this is the main terminating case, which means that we can put true over here. So this final element we can always put true, and this would actually become our base case. Now we have a base case. We are going to start iterating on from right to left manner, and we are going to start filling up our DP array to see. And in the DP array, the only thing we are mentioning is that at any given location, if we are able to reach to this endpoint or not. If we can, we'll just mark it as true, otherwise we'll mark it as false. Okay, so now one step over here, this is this value has potential to make two jumps, and it only takes one jump to get to this last point, which means that if we end up at this 4th position, we can reach to this 5th position, which is what we want. So over here we can also fill this as true. Now we are at this 0th position. From this 0th position, can we reach to this 5th position? No, because we basically can't make any jumps. So we'll just fill this as false. Okay, now from this one, can we end up at this 5th position? So we are going to, now the interesting part comes. Now we are going to check that, okay, this has possibility of only doing one jump, right? So with one jump, we can only end up at this 3rd index. Now we only need to check that in this DP array for this 3rd index, if the value is true or false. So in this case, this is already false, which means that the maximum we can get to is this third place. From this third place, we can't go anywhere. So we don't even need to check these values. We can only check this DP table, and we can conclude that no, we can't go anywhere forward. So we will put a false over here as well. Now we are at this third position. Now from this third position, we will again do the same check. But the thing is, this has potential to do 3 jumps. Okay, so let's do one jump at a time. So first we take a jump. If we take a jump of one step, we end up over here. We check over here that this is false, which means that this is false, right? Now we take second jump. With the second jump, we end up at this third position. We check in this DP array. This is also false, which means that we can't do anything. Now from this third position, we still have one more possibility, that we can take a jump of 3 values. So if we take a jump of 3 values, we end up at this position, value number, this index number 4. So for this index number 4, we see that the value is true. If we find any true, which means that we can say that from this second, this index number 1, we can reach to this last endpoint. And now for this position, we need to check that it has potential to do 2 jumps. We will only check for 1 jump. So with 1 jump, we will end up at this first index. That one is true, which means that we can fill true over here as well. And in the end, we just need to return whatever of DP of 0 we found. So in this case, we can determine that this is true, which means that we are able to come to final endpoint. So this solution is very good. It works perfectly fine. Okay, so the time and space complexity for this approach would be, so the time complexity would be big O of n square, because notice that we need to do one iteration to go on for every single element, and sometimes for any given element we might have to do multiple jumps, like we did in this case of 3. So in the worst case, we might have to solve this in big O of n square time, and the space complexity would also be big O of n, because we are creating this additional DP array. Now this is still much better than our brute force approach, but our aim is to go into companies like Google, Facebook, Amazon, Apple, and whatnot. So those companies expect the best out of the best solutions. And is this the best out of the best solutions we can do? Actually, no, there is still a better optimal solution, and let me show you how we can get there. Okay, and this optimal solution is actually based on the dynamic programming solution that we just saw. So in dynamic programming, what we are doing is we are creating an additional DP array, and we are storing that whether we can reach to this last element or not. But the thing is, what if rather than storing this value at any position, when we find out that, suppose from this position, we found out that yes, we are able to reach to this last position. So why do we need to check that whether we can reach to this last position or not? If at any point amongst these values, if we end up at this position, we would still be able to guarantee that we can reach the last element, because we have already checked this condition. So rather than checking for this whole thing, if we just check that, okay, from here, if we can reach to this element or not, and if this is true, we can simply return true at that moment also. And let's see that in action. So let me clean this up a bit. Let's mark all the index values. Okay, initially we create an element called final, and this final element represents the last value in the given input. And initially we set it up to this index number 5, right? Now our aim is that at any point we found out that amongst these values, if anyone can reach this final element, then that element by itself becomes this final. So rather than storing all the values of at any given location, we are actually shrinking down our boundary of search. Initially the final is at this 5th position. Now we are at this 2nd position. So all we need to do is to check that whether our current index our current index and this current value, if sum of these two is actually greater than whatever final we have. So currently the final we have is this 5. So this is the final we have. Current sum of these two values becomes 4 plus 2 is equal to 6, which is greater than 5, which means that we can update the value of our final. So now this becomes our new final, and we basically don't care about this value anymore. Now we are at this third location, and we try to see that the index plus its value. So this becomes 3 plus 0. Is it greater than our final? No, this is not greater than our final, because this is 3 and this is 4, which means that we can't do anything over here. So we drop this calculation and we check with the next element. So over here we have this 2 and we have the value 1. So 2 plus 1, is this greater than 4? So greater than final? No, this is also not true, which means we can't do anything over here. We again go back. Now this is 1 and this is 3. Now 1 plus 3, is this greater than or equal to value 4? Yes, this is greater. This is actually equal to 4, which means that we, from this point, we can come to this point. This is what this concludes, and which is what we want, right? So now we know this information, which means that we can update the value of our final again. So now the value of our final would become 1. So at this value, and now at this 0th position, we need to check that whether we can reach to this 1 or not. So over here the sum of these two value becomes 0 plus this is 2. So 2 is definitely greater than the final amount we have is 1, which means that we can reach over here. So the final element would be shifted to this point, and at the end of our iteration the final would be 0. So now the final is 0. After the end of the iteration, we only need to check that what is the value of final. If final is 0, we return true. If final is anything other than 0, we return false. And this is a very good solution. The whole thing runs in the time complexity of big O of n. And if we see the space complexity, we are only storing one additional parameter. So we are essentially using constant space, and we are solving this problem. So this is a very efficient solution. Let's create a variable called final. Oh, it's Java, I can't use final. Let's call it final with an extra L, and we'll assign it to value as nums.length -1. And now we will run a for loop, and we'll start it from I is equal to number of length nums.length -2, because we already know the result for the array length, and we will run it up until we reach to this 0th position. We'll do I minus minus, and inside the loop we are only going to check one condition, that if the current value of I plus nums of I, if they are greater than or equal to whatever the final value we have, we can update the value of this final parameter to whatever the ith value we have. And yeah, that should be pretty much it. Now we only need to check that if the value of this final character is 0 or not. So if it is equal to 0, we can return true, else we can will return false. Okay, let's try to run the code. Seems like our solution is working. Let's try to submit the code. Okay, our solution works 100% faster than all the other solutions. This is really good sign, and this is not constant time, but because we are basically shifting our boundary, we are essentially reducing the number of work we can do. And also, if you see the memory usage, we are actually better than 86% of all the other solutions. So this was a very small line of code, but this small line of code actually requires huge set of understanding. So see you in the next video. Thank you.
Hello Hello friends, I am a cloud solutions architect at Microsoft who like making lead code videos, and today we are going to solve an awesome problem called Jump Game 2. If we see some of the popular companies who have already asked this question, there are companies like Amazon, Google, Goldman Sachs, Bloomberg, DoorDash, Uber, Microsoft, Apple, Tesla, TikTok, Snapchat and ByteDance. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a lead code medium problem and also very well like problem on lead code. Basically in this problem we are given an array of integer called nums as an input, and we are told that we are initially positioned at the first position inside this given array. Now our aim in this problem is to return the minimum number of jumps required to reach to the last position. Now you must ask that how are we going to make these jumps? What are the criteria for that? So the criteria for any jump is that any given value that is presented inside this given array represents the number of values it can jump. So basically if this one is represented 2, we can say that it can reach, it can either take like 1 jump or it can take 2 jumps and reach to these positions, and our aim is to reach this last position, and basically we need to do this in the minimum number of jumps that is required. Now if you are confused, don't be. I'm actually going to show you a couple of examples to understand that how things work. So basically over here we are given 5 different values, and for these 5 different values, as I mentioned earlier, every single value represents the maximum number of jumps it can take. So this value number 2 has 2 possibilities. It can either take 1 jump and reach to this position number 3, or it can take 2 jumps and reach to this position number 1. Same goes with value number 3. It has 3 options. It can take like 1 jump, 2 jump or 3 jumps, and then do that. And our aim is to reach the last position from the first position in the minimum number of jumps possible. So if we see in this example, the answer is actually quite evident. We start our position at this value number 2, and if we just take like first jump to reach to this value number 3, okay, so currently the number of jumps we have taken is 1. Now from this value number 3, if we take another jump of the size 3, basically we would be able to reach to the end position, and in total we are only taking 2 jumps to reach to the end. So basically we need to return 2 as the answer in this case. If we try to understand the second examples, things are a little bit different. So in this case we can only take 1 jump. So okay, so currently the number of jumps we have taken is 1. Now from this 1 we need to take 1 more jump to reach to this position. So again the number of jumps we have taken so far is 2. Now from this 2 we have 2 options. Either we can take 1 jump and reach over here, but that is not the most optimal way. Most optimal way is we take a jump of 2 steps and reach to directly to this end point. So basically the answer in this case is going to be 3, that we need minimum 3 jumps to reach to this last position, and in this case we need minimum 2 jumps to reach to this last position. So this is what the problem is asking us to find, and I know it can look tricky, but it's really simple to do it. And let me show you a couple of different approaches to solve this problem. Okay, so the first approach that comes to our mind is a brute force approach, and in the brute force approach basically we are just going to use the simple logic. The logic is that at any single position we will try to see that how many jumps it can take, and try to explore all the possibilities and try to find that how many jumps it takes to reach to the end element, and also have like a minimum variable in mind that whenever we find minimum number of jumps we will keep on adding it over here, and eventually when we compute all the calculations we should have a result. So in this case what we are going to do is that okay, this value is 2. So first we will consider the possibility of just taking 1 jump. So in this case, okay, if we take 1 jump we reach over here. Again we have 3 possibilities over here, but we are only going to take 1 jump. So again we reach over here. Again this only has 1 possibility, so we reach over here and then we reach to the end. So in this case we took in total 5 jumps to reach to the end. Now secondly we are going to take like different things. So first we will take 2 jumps. So we took 2 jumps, and now we take 1 jump every single time and try to see how when we reach to the end, and so on and so forth. We keep on repeating the same process with different combinations. Now just by the explanation you can imagine that how complicated it's gonna make things, because for every single time you will have to calculate different permutations and combinations of sums, and eventually it's gonna lead to very disastrous results. Like if we see time complexity in this case, it's gonna be in the order of n factorial, because for every single element we will have to compute the process for all the other elements, and that is going to be in the order of big O of n factorial, which is really bad. So we will have to find a better solution, and the better solution is actually quite simple. So let me just directly go to the optimal solution. And now for the optimal solution, we are actually going to use a very interesting concept called greedy concept, and basically we are going to try to make the biggest jump possible every single time and try to see that where does that leads us. Now being greedy is not good in real life, but in computer science it is like the must thing, so you have to do it. Now for the greedy approach, we are actually going to keep track of 4 different variables. So first variable we are going to keep track of is the index value we are currently at. So let's just name it as index. Again, we will also have to keep track of the number of jumps we have made so far. Also we will need a variable to keep track of current maximum variable that we have been able to reach, or current maximum value we have been able to reach. And also from the current index, we will have to keep track of that what is the current end value we can reach at. So there are 4 variables. Let me go over them again. First one is the index value. Second one is the number of jumps we have made so far. These 2 are sensible. Third one is to keep track of that what is the current maximum value we have achieved so far, and we will only update it when we find like a better maximum value. When we go through the example, everything will make more sense. And the current end defines it is in correlation with the index value, that where does the current end lies, and if we are at the index value, then we will have to make some changes. So now let's look at the example, and currently let's initially assign the values. So initially the number of jumps are 0, current maximum is also 0, and current end is also 0. Now we start our journey. So first we come up at this first index. So whenever we are at the first index, okay, the index value currently is 0. Now the index value is 0. Now let's just keep on updating these values, right? So currently this has value number 1. So if this has value number 1, which means that this 0th index has the potential to reach maximum at the first index, which means the current maximum value we can achieve is that, okay, this current value is 0. Now over here it says that it has maximum potential to reach index value number 1. So 1 is definitely greater than 0. So because it is greater than 0, we will update the value of current maximum to 1, that okay, this is the maximum value we have been able to achieve. Now the interesting part comes. The current end we were at, the current end was 0 because we were at the 0th position, and also the index value we were at was also 0. So because both of these values were same, which means that in order to get ahead to the next index, which is not the last index, again remember I am repeating, in order to get ahead from the current index, which is not the last index, we will have to update the current end, because currently the current end was also here and the maximum value was also here, but this has the value 1, so we have the ability to go to the next, which means the current end needs to be updated. And whenever both of these are at the same place, that means if we are updating the current end value, we will only update the current end value in the condition when we are making the jump. So again, let's just go back to our analysis. Because the index value and the current end both were same, so because these two values were same, we can define that we need to update their values, which means we are taking a jump. So okay, so we made a jump, so we will do jump plus plus, so currently this value becomes 1. But the thing is, where do we update this current end to? We will always go this current end to the whatever the maximum value we have been able to find so far. So current maximum we found is 1, so again we are going to include this value number 1 over here. Now let me clean this up a bit. So now we are at index position number 1, so we will update our index value. So our current index value is 1. Now at this position, what is the maximum it can travel? Maximum it can travel 3 points. So 3 is going to be 1 plus 3, so that is 4. So now this is the current maximum we can achieve, that is 4. So we will compare 4 with the current maximum we had. Current maximum is 1, so 4 is definitely greater than 1, which means it is sensible for us to update the current maximum. So current maximum becomes 4. Now we will also have to check that what is the current end. Now current end is still same as the index value, because this was the current end, so which means that anyways we will have to make a jump. So because we are making a jump, we will update the value over here. So currently the number of jumps we have made so far is 2, and we will also have to update the value of the current end. So current end we can reach is position number 4, because we already established that that is where the maximum number of jumps we can take. So okay, we are good up until this point. Now again let's make the changes. So now we are at index number 2. So let's see that what story happens at index number 2. Now index number 2, the maximum we can take jump is 1. So if we take one jump, we reach at index number 3. But the thing is, if we check the current max is already 4, and the maximum we can reach is 3. So 3 is actually less than 4. So in this case, we don't need to update the current max. Okay, awesome. We are not updating the current max. And now we check, okay, current end is 4 and the index value is 2. So these two are not same. Because these two are not same, we don't need to update the current end or the number of jumps that we are taking. Now, okay, now our index value keeps on updating because we are checking this for every single index value. So now we are at position number 3. So now at position number 3, we have maximum 3 possibilities, right? So if we go to 3 steps, we reach to the index number 6. So our current maximum will become 6 because definitely 6 is greater than 4. Now we updated our current maximum. Now we also need to check few other things. Okay, so current end and index value, these two are not same. So we are not going to do any changes for now. So now our index value becomes 4. So let's update this. Okay, so this becomes 4. Now we are at this 4th position. This only has possibility of 1. So this will reach to the maximum of 5, but 5 is actually less than 6. So in this case, we will not update the current maximum. Now in this case, the index value and current end is both of them are same. So because both of them are same, we will have to do the update. So now when we do the update, okay, we are going to mark the current end as 6 because that is what the current maximum we have been able to achieve. And also the number of jumps we are going to take is going to become 3. Okay, now again we keep on repeating the same process. So again our index value becomes 5. Now because with the 5 index value, the maximum we can take is 1. So that is going to lead up to 6 but we already have current maximum at 6, so we don't need to do anything. And these two values are not same, so we are not going to do anything. Now the index value is at position number 6. Now at position number 6, we are actually able to reach to the end with just a single jump. So we are going to do that. Okay, now we reach to the end of this jump, but the thing is, we are just going to, for the sake of simplicity, go ahead with this calculation. So the current maximum we have been able to achieve is going to be 7. That is the end. Now current end and the index value, both of these are same. So because both of these are same, we will have to update our number of jumps that we need to take, and also we need to update the current end. So current end in this case is going to be 7, and we are going to check that if the current end reaches to the last position or the size of the array, that means that is the answer, and we can break out of the loop, and whatever the answer we have been able to find, we can simply return this. So in this case, for this example, the answer is going to be 4, that we can return simply. And this is the most beautiful approach of the greedy solution that I have seen so far. Now if we see time and space complexity, in this case the time complexity is so good because we are only going through every single values and calculating, keeping track of 4 different variables. So time complexity is actually going to be big O of n. So notice that from big O of n factorial, we were able to bring it down to big O of n, and all due to the greedy approach that we took. If we see space complexity, in this case the space complexity is actually going to be big O of 1 or constant space. Why? Because we are not using anything else apart from like these 4 values. So that is also a wonderful news. Okay, so let's initialize 3 variables that we need. That is going to be jump, current end, and current maximum. And initially all the values are going to be 0. Now notice that I am not using the index value over here, and that is because we can actually use it from our loop directly. Now let's run a for loop to iterate over the given input array. So now every single time we will check that what is the current maximum we have been able to achieve. So we are basically going to compare the maximum value amongst the existing current maximum value or the value of I plus whatever the value of nums of I for that particular I is, and whichever is maximum, we are going to put it in the current maximum. Now we are also going to check one very critical condition, that if the given I is actually equal to the current end we are at. If that is the case, which means we will have to update the value of the jump. So we will do jump plus plus, and we will also have to update the value of the current end. So current end is in this case going to become the current maximum that we have been able to achieve. And believe it or not, but this concludes the whole solution. After we get out of the loop, we can simply return the jump that we have been able to find, and this should be it. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And if we submit it, this is beating like almost 99.99% of the solutions in terms of time complexity, and in terms of space complexity, this is also very efficient. So this is a very good solution. And if you see, we are just only using a single loop and just like few lines of code to solve this problem. And I would be posting this in the comments so you can check it. So the lead code problem we are going to solve today is called partition labels, and we can see that this one is a pretty popular lead code problem. Basically, we are given a string that we want to partition into as many parts as possible so that every single letter in each of the partition appears at most at one and not in any other partition. Now note that the partition is done such that after concatenating all the parts in order, the resulting string would be string S. So we cannot just partition randomly from the middle of the string. It has to be sequential. Now let's try to understand it with some examples. Let's say that we are given a scenario like this. Now we want to create maximum partition where every single character only appears in just one partition. So in this case, we can create a partition with this A, B, A, because remember A appears over here and A appears over here. So they both has to be in the same partition. And then we can create one more partition called D, and notice that if we combine this ABAD, then we would get the resulting string S. Same way for this one, we can create a partition AA because that would fulfill that all the characters of A are present. Then we can create a partition called BCDB because B is present over here and here, so it has to be part of the same partition. Now for this third one, we can create a partition AA. We can also create a partition CC, and then we would be creating an individual partition called B, and then there would be a partition called D, and this is what we need to return. So basically in the answer, we don't need to return something like this, the exact partitions, but we only need to return the size of those partitions. So for this example, we would return answer such as 2 and then 2 and then 1 and 1. So these are going to be the sizes. Now the brute force solution is actually quite straightforward. We simply take a character, we iterate over every single remaining values, we see that what is the last point where the character occurs, and then tries to create a partition of that size, and we keep on repeating the same process again and again for every single remaining characters, and so on and so forth. Eventually we would get all the necessary partitions. But the thing is, this is not the most optimal approach, and we can see that this one would run in big O of n square time, so we can do something better. And let's try to find an easy and simplest solution that we can derive from originally brainstorming our brute force approach, and that is to use the greedy way to solve this problem. We are going to be very efficient in picking and choosing how we are going to go forward by selecting the partition. Now the first rule to select any particular partition is to identify that for any particular character, the starting value doesn't matter, but what is going to be the last occurrence for that particular character matters the most. Because once we identify that a character is part of any partition, then we will have to figure out that what is going to be the last place this character is going to be placed at. That is number one thing. Second thing is, apart from being like finding the last position, we would also have to figure out that this partition makes sense if all the characters present in this particular partition has the last point either being this value or before that. I repeat that this can only be a partition if every single unique character that there are present, their last point or the last occurrence would either be less than the index value that we are currently at. So based on using these two values and some additional variables like the partition end time and the partition starting variable, we can actually solve this problem very easily and very efficiently. So let's first identify our first approach, that is to find the last occurrence for every single unique character. So let's say that for A, the last occurrence is going to be index number 2. for B, the last occurrence is going to be index position number 1. Okay, so now we have our list of last occurrences for every single character. After that, we can start iterating over any particular given character in this simple fashion in this given string, and all we will have to compare is that what is going to be the last occurrence compared to its current ith position, and whichever is going to be the greater value, we are going to put it as part of our partition end, because that has to be the partition end, and whenever we find a greater value, we would update the partition end that we are currently at. On top of it, if we are at a position where the given ith value is equal to the partition end, which means we found out a correct partition, so no other character exists that has a greater last occurrence compared to our current value, and we can mark it as a partition. So we can just add it to our result list. So let's say that we are also creating a result list to store all the results. Okay, and let's just follow our approach. So first we identified value number A. So for value number A, the last occurrence is located at position number 2. So the partition end has to be at least value 2. So we'll mark it over here. Okay, and then the partition start initially is going to be 0. Then we are going to iterate over value number B. What is the partition end? Partition end is 1. 1 is lesser than value number 2. So which means we don't need to update the partition end. Next current ith value we are at is value number A, that is located at position number 2. So in this case, because I is equal to 2 and the partition end is also going to be 2, we can actually mark these values inside the result. So currently in the result we are going to have 3 characters, so that we can determine by finding out position start minus position end minus position start plus 1. We'll have to add plus 1 because we are starting with a 0 index. So in this case, first result is going to be value number 3. After that, we are going to update the position start value to the partition 3 number 3, and we are going to reset the value of partition end. Okay, so currently the partition end would be dependent on this particular value C. Okay, so C, for the current C value, the last occurrence is 6 and previous value was 2, but 6 is greater, so we are going to mark 6 as the current partition end. Now for this D, the partition end is going to be 4. So 4 is lesser than 6, so we don't need to do anything over here. Same way 5 is lesser than 6, so we don't need to do anything over here. Now we are at I is equal to 6 and current partition end ends at 6 as well. So in this case, once again we are going to do partition end minus partition start plus 1. So we will have 4 characters in this second partition as well, which are these 4 characters. Now we are at value, now the new partition end is going to be value number 7. Okay, so we mark partition value number 7, and lucky for us, the value we are iterating over for Y is also valued at value number 7. And by the way, the partition start would also be updated to value number 7. So since we found I is equal to 7 and the partition ending position is also 7, so we can mark this as a new partition, and this is only going to contain one element, and same way this is also going to contain one more element, and we can mark it as the answer. And this is the whole solution basically. Let's do a quick recap. First, we created an array that is going to store the last occurrences of every single character. Once we have that, then we can simply go over all of these characters one by one, comparing with the last occurrence, the current position end date and position start value, and we can maintain a result array. And if you see the coding solution, this would become much more sense that how does all of this operates. Now if we calculate the time and space complexity, in this case the time complexity is going to be big O of n, because we will have to iterate over the given input string couple of times, but overall it's just a linear update or the linear traversal. And the space complexity is also going to be big O of n, or this can be big O of 1 depending on how you perceive it, because if we are only talking about the lowercase English letters, then there are only 26 possibilities, and we can use a constant amount of space to solve this problem. So you can debate this with your interviewer that on how they wants to perceive it, but basically both the approaches would be correct. So the coding solution is going to be quite straightforward. First, we are going to check that what is the last occurrence of every single character, and since there are only 26 characters that could be in string S, we can use a simple array instead of using a hash map. We can iterate over every single characters and then just mark their position with the appropriate ith position and just store it in our array called last occurrence. Step 2 is to iterate through the string and determine the partition. For that we will need to have a variable to store the answer, and we are going to initialize our array list called result. We also need couple of variables to keep track of the partition end and partition start pointers. So once we have everything set, we are simply going to iterate over the given integer, and we are going to mark the current partition end as the maximum value between the current partition end that we have been able to find and the maximum value of the last occurrence of the current character we are at. Then if at any given point we identify that the given I is actually equal to partition end, then we can simply find we have simply found a partition where there does not exist any more characters further than that point. So we can add that value to the result, and then we can start working with our next partition. So we can just update the value of the partition start, and then we can keep on repeating the same process, and in the end we can simply return our result array list. So let's try to run this code. So the solution is working as expected. Let's submit this code. And our code beats 91% of all the other solutions, which is excellent. And I would be posting this in the comments, so you can go and check it out from there. Thank you. The lead code problem we are going to solve now is called merge triplets to form target triplet. Now we can see that this one is a medium problem and also not very well like problem, but a really important one. Basically a triplet is an integer array of 3 integers. Okay, that's fine. And we are given a 2D integer array called triplets with bunch of different values that contains the pieces of triplets, which means like values like a, b and c. Okay, now we are being told that there is a target triplet x, y and z. Now we need to make sure that in this given triplets, are we able to generate this target by doing the following operation on any number. So basically we can pick any two triplets from our given triplet array, and if we pick any two triplet, basically we can combine them to create a separate new triplet that is only going to contain 3 values, but that is going to be the maximum value at each position amongst these two triplets. So let me give you an example. Suppose we have a triplet 1, 2 and 3, and we have a triplet, let's say 4, 5 and 6. So in this case we know that amongst these two the higher value is 4, then amongst these two the higher value is 5, and amongst these two the higher value is 6. So if we merge these two triplets, basically we can form an operation like this. So based on this, we are being told that we can do as many number of operations as we need amongst all the triplets that are given, but we are trying to make this target number. If we can make the target number, awesome, we need to return true. If we are not able to make the target number, then we need to return false. So let's try to see one example, and we'll try to figure out different examples from that. So first one is that let's say that in any given case we are given these 3 triplets, right? For these 3 triplets we need to form a number 2, 7 and 5. Now notice that we have the option to do the operation between any 2 triplets. So let's say that we do that max operation between these 2 triplets, which means we have value 2, 5 and 3 at one position, and second value is 1, 7 and 5. By doing the operation like the merge operation, basically we can pick the maximum amongst all of these values, and we will form a new triplet that is going to be maximum of these two values. So the value is going to be 2, this is going to be maximum, so value is going to be 7, and this is going to be the maximum, so once again value is going to be 5. And notice that this exactly matches the given input target that we have. So in this case we can return true, saying that yes, based on the given input we are able to generate the target value, and hence we can make the triplet by merging 2 triplets. So let's see that what is going to be the brute force approach to solve this problem. Well, it is quite straightforward that for any given triplets that we currently have, let's say that we are given in total 5 triplets, and I'm just marking them as A, B, C, D and E. and for each of these 5 triplets we have the option to do the merge operation. So if the brute force way is that we do merge operation amongst these 2 triplets, we do merge operation amongst these 2 triplets, and so on and so forth. We keep on repeating, and every single time we compare it with the target value to see if we are able to generate the target value or not. And eventually, if we can, we would find the correct answer, but this would yield in big O of n square time, where n is the number of triplets that we currently have, which is an inefficient approach. We'll need to find a better approach, and the optimal solution in this case comes from doing things in the most simplest manner optimally, and that is to use a greedy approach. So let's say that this is the example that we are currently given. Now notice that whenever we are iterating over any particular triplet, we should always compare it with the target to determine that is this a triplet of interest or not. And the comparison should only contain 2 items. First thing is that whether if each of these 3 values, if all of these are lesser than the target value, then and then only it is a triplet of interest for us. Otherwise we need to move on to the next triplet. And why? Let's try to understand. Let's say that currently we are given a triplet 2, 6 and 5, and we are given the target to be 4, 6, 6. Okay, so in this case we can notice that every single value, so 2, 6 and 5 comparing with 4, 6 and 6, notice that every single value inside this triplet is actually less than or equal to the target triplet that we have, which means this can be a potential candidate that we can use in future for the merge operation. Now the thing is, if we are going to use this for the merge operation, then we should just put this on a side, and noting that we found a triplet which can be of potential use to us. At the same time, we should also have to keep track of a variable that what if we already found a triplet that we are all anyways going to find the optimal solution with. And in order to do that, we will have to basically compare the given triplet with the target triplet and keep track of the maximum value that we are able to generate from both of these triplets and just store that information. So let's say in this case we can notice that because this is a triplet of interest, then we are going to store the maximum value amongst these two and these two. And notice we are having a condition that this has to be smaller or equal to the target, which means either we can have all the values that are going to be smaller than target, or it is equal to target, which means we would never exceed target in this approach. So in the maximum variable, we are going to compare the max values. So we are going to, this is going to be 4, this is going to be 6, and once again this is going to be 6. Okay, so we took care of this triplet. Now let's move on to the next triplet. Once again in the next triplet we have a value called 7, 4 and 6. Now notice that for this one, for 7, 4 and 6, we did found a triplet that we currently have over here that is of potential interest, could to target or not. So notice that the very first value 7 and 4, so 7 is greater than 4, which means if we do merge operation with this triplet, then we are always going to have first value that is going to be greater than the target value, which means this would not be a use for us. So we should just simply skip over this triplet because we should not use this triplet to merge with anyone else. Okay, next we have this value 4, 4 and 6. So let's try to see that if we use this value, what is going to be the expected range or expected triplets we are going to be find. So in this case, basically once again we compare 4 with 4, so this is equal, 4 with 6, so this is lesser, and 6 with 6, so this is equal. So once again this can be a potential triplet that we can use. So now let's try to do the max operation in this case. So the current values are 4, 4 and 6. So we are doing 4, 4 and 6, and we are comparing it with the target, which is 4, 6 and 4. So now notice that maximum amongst these two is going to be 4. So we add 4 over here. Maximum amongst these two once again is going to be 6, and maximum amongst these two is going to be 6. And now in the end we are going to have a maximum variable that is going to contain values 4, 6 and 6 over here. And meanwhile we are going to have another target value that we were trying to achieve, and that was also 4, 6 and 6. So notice that because both of these values match, we can simply say that yes, there exists a triplet that we can generate by merging other triplets. And if we cannot find this maximum value, which means there does not exist a triplet that is of a good use to us, so in that case we would have returned false. So if you see approach for this solution, then we can simply run it in big O of n, where n defines the number of triplets, and in terms of space complexity we are not adding any additional space, so this is going to be big O of 1 as well. So I hope this solution makes sense. Now let's quickly see the coding approach. The coding solution is quite straightforward. First, we are going to initialize an array with size 3, naming it as max values. Then we are going to iterate over every single triplet that we are given inside our triplets 2D array. And for each of the pair, we are going to check that if the current triplet that we have, will it be contributing towards making the target or not. So we are checking that if the given triplet position, the first value is less than the target, less than or equal to target, second value is less than or equal to target, and third value is less than or equal to target. If that is the case, then we are going to simply update the maximum values we have been able to achieve based on the given current triplet and the target values. Now remember, because we are considering triplet values to be less than or equal, which means if the only case where we have the target value set as it is if the given triplet value is also same as target value, that subsequent value. So we are going to store the values for all three parameters and keep on repeating the same process for every single given triplets in a greedy fashion. In the end, we simply have to check that whether the three values present inside our array match the target values that are present. If that is the case, we can return true, otherwise we can return false. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs beautifully, and it is pretty fast. So I will be posting the solution in the comments, so you can check it out from there. Thank you. The lead code problem we are going to solve now is called gas station, and we can see that this one is a lead code medium problem and also a very well liked problem. The statement is quite straightforward, that there are n gas stations along a circular route where the amount of gas at any particular station is defined in the array gas fi, and then we are told that we have a car with unlimited gas tank that cost of I gas to travel from ith station to the next I plus 1 station. Let's do a quick recap. Basically we are given two arrays. First array is called gas and second array is called cost. Basically gas, any particular value inside the gas array defines how much oil or how much gas we can fill in the tank at that particular location. Cost at that station defines that if we have to move to the next stop, what is going to be the cost in terms of gas amount, so based on distance. You can understand it that way. Now we begin our journey with an empty tank at one of the gas stations. Okay, now we have basically need to make sure that given these two arrays, we can start from any particular gas station's index, and we need to check that if from that gas station's index are we able to travel around the entire circuit once in a clockwise direction. If that is the case, then we need to return the location of that index. If that is not the case, we need to return -1, and we are guaranteed that we would be able to find a solution. So if there exists a station, there has to be only one station that can fulfill that property, otherwise it would be -1. There would not be any duplicated answers. So let's try to understand this with an example. Currently we are given a variable called gas, and we are also given variable called cost. At any particular index position, this is the amount of gas we can fill in the tank, but if we need to go to the next stop, then this is going to be the cost associated with that, and so on and so forth. So let's try to see that what would be the answer in this case. Let's say that suppose we start our journey from index position 0, which means currently our car has so let's just mention that what is going to be the tank amount of gas in the tank. Okay, so currently tank has empty, so no gas at all. at position number 1 we would be able to fill in one amount of gas. So currently tank has only one amount of gas. Now let's say that if we need to reach to next position, index position number 1, then we will have to pay this cost. If we were to pay this cost, it would be 1 minus 3. So basically our tank would go in negative, so we would not be able to reach to this position number 2 from tank number 1. So we can clearly say that option 0, it does not work. Same way we can also check that from option number 1, currently our tank would be initially 0. Okay, let's just repeat the calculation. So this is going to be 0, but now we can fill in plus 2, so now the gas would be 2. But if we have to get to option number 3, then we would have to spend 4 units or 4 liters of gas, which means 2 minus 4 would become minus 2. Once again we would not be able to reach to item number 4, so that would also not work. So let's just start our iteration from this third index position. Once again repeating the same logic. Currently tank is going to be 0, but we can add tank as 3, so 3. And but if we have to reach to next station, the cost is 5, so 3 minus 5, once again this would also not work. So now we are at this index position number 3. So currently our tank is going to be 0, so we can add value number 4. So now tank has 4 liters of gas. If we have to reach to value number 5, then we need to spend 1 liter of gas. So once again this is also going to be 4 minus 1. So basically when we reach to this index position number 5, our tank would have 3 units of gas. Once again at this position we would fill in 5 units of gas, so this is going to be 3 plus 5. But now from this, in the clockwise direction, basically we will need to reach to station number 1, but we will have to pay cost of 2, so 3 plus 5 minus 2. So overall this is going to become once again 6. So we are going to have 6 units of gas when we reach to this position number 1. Once again over here we will add 1 unit of gas, but in order to reach to next element we will have to spend 3 units of gas. So now when we reach to this index position number 2, our gas is going to be 6 plus 1 minus 3, so 7 minus 3, so basically this is going to be 4. Once again from this position number 2, we need to reach to position number 3, so 4 plus 2 minus, we will have to spend 4 units of gas, so basically this is going to become 2. And at this position once again we get 3 units of gas, so 2 plus 3 minus, if we have to reach to next, which is from where we started, then basically it's going to be 5. So 2 plus 3 minus 5 is going to become 0. So basically we would be able to reach to unit number 4, and this is going to be the starting point if we were to complete the whole circuit. So we'll need to return the index position, so we can return 3 as the answer over here. And I know the explanation took a lot of time to understand what this problem statement is, but basically this is actually the whole solution as well. Because in order to solve this problem, we don't need to use any special data structure or any special architecture. Basically, if we just follow the most simple basic rule, that we are going to start our iteration from the very first index, and from this very first index position we are going to check that are we going in a scenario where our current tank goes negative. If the current tank goes negative, we can simply choose the starting point as the next element. And once again if it goes negative, we can choose the starting point as next element, and we will keep on repeating the same process. And the moment the tank goes into negative, we will just update the tank value to become 0, and that is the whole logic of this problem to solve this problem. Now let's talk about some of the critical possibilities. Number 1 scenario is the only way we are not able to complete the whole circuit is a very simple logic, that is that if the given gas is going to be less than the total number of cost. If that is the case, cost is higher, so we would not be able to complete the full circuit. And we can calculate this immediately, basically by summing up all the values that are currently present in both gas and cost arrays, and we can just compare those values. So if that is the case, we can simply return -1 immediately, saying that this problem cannot be solved. If that is not the case, then we will simply follow the most common, most logical thing that humans are really good at, and that is called greedy approach. That we are simply going to take the first value, try the solution. If solution works, great. If we at any given moment find the tank goes into negative, then we will just pick the next value. So over here, for the same problem, I have just presented it in a different manner. currently we have our index position stored inside. So 0, 1, 2, 3 and 4. Now this second circle defines that how much amount of gas can we get at any particular location, and the values located at these gates define that if we have to jump from gate number 1 to gate number 2, then we will have to spend 3 units of gas, and which we can subtract. So basically the solution is that we will start our greedy approach by iterating at value number 1 with initially the tank is going to be 0, and then we will just repeat the same exercise we did. So we will check, okay, over here we can add 1 unit of tank, but this is going to be 3 units of tank to reach to value number 2, so tank would go into negative. So basically we would choose our starting point over here by resetting the tank to be 0. Once again 2, and this is 4, so tank goes into negative. So once again we would choose our starting value to be index position number 2. Once again tank goes into negative, so once again we would choose our starting index to be this. The moment we find a starting index where the tank does not go negative, we would try to iterate over and see if we are able to complete the whole journey or whole transaction. And basically we should be able to do it in this case, because we know that we have a starting point where the tank does not go negative from to when we start iterating. And secondly, the total cost of basically total cost is basically not greater than the total number of gas. So that's why we know that the answer should not be -1, and just that's it. So in this case we would return 3 as the answer. If we have to calculate time and space complexity, it is quite straightforward. For time complexity, basically this can be done in big of n time if we apply the greedy approach and we do some slight tweaks with the code. So the tweaks with the code I'm going to explain you when we actually get to the coding portion. And for the space complexity, well, we are not using any additional space to solve this problem, so basically this is going to be big O of 1, so which is quite beautiful. Now let's just quickly see the coding solution. So the solution is quite straightforward. First, we are going to have a few variables. They are going to be initialized as 0. First one is total gas and total cost. Both are initialized at 0. Then we have tank, and then we have starting index. Then we are going to have a simple for loop that is going to iterate over every single starting point in the given input. We are going to have two variables, total gas and total cost, that is going to be continuously adding the total amount of gas and total amount of cost we have. For the current proportion of gas that can live inside the tank is going to be calculated by adding the current gas with the current tank value and reducing or removing the cost of the current ith position. Then we are checking for a simple condition that if the tank goes into negative, then the starting index that was originally at 0 now needs to be at I plus 1th position, because we identify that the current ith position does not work. And then the current value of the total amount of gas inside the tank is also going to be 0. Then we are going to check if at any given moment the total amount of gas becomes less than the total amount of cost after the running of whole for loop. Then if that is the case, we can simply return -1, and if that is not the case, we simply return the starting index. And this is the whole solution. Let's try to run the code. Okay, seems like our solution is working beautifully. Let's submit this code. And our code beats 99.29% of all the other solutions, which is exceptionally fast, so pretty good. And once again, I would be posting this solution in our GitHub repository, so feel free to go ahead and check it out from there. Thank you. Hello friends, hope you are having a fantastic day today. So now we are going to solve an awesome lead code problem called hand of straights. Now we can see that this one is a medium problem and also a very well-liked problem on lead code. Let's understand the problem statement. We have a girl named Alice who has some number of cards, and she wants to rearrange these cards into a groups such that each group of the group size consists of group size consecutive cards. So let's try to understand what this means. Basically, we are given an integer array called hand that defines bunch of different values inside a deck of cards, and at any given integer I is the value returned for that particular hand. Now we are also given another variable called group size. Now we need to check that whether we can divide all of these hands in a group sizes, like groups of these group sizes, such that all of the rearranged groups contains consecutive cards, and we can rearrange all the groups. So let's try to understand this with an example, and then it would make much more sense. Let's say that we are currently given the hand or deck of hands like this, and we are given the group size to be 3. So let's see that can we create the different 3 size groups. So first group we can create is going to be cards 1 2 3. Now notice that there is a condition when we are trying to create the groups, that every single card inside the group has to be consecutive. So we can create this one group. Second group we can create is using these 3 characters, and that is 2 3 and 4. And third group we can create is using 6 7 and 8. So now notice that in this case, we use all of the cards that were currently given to us, and we divided them into the size of 3, and each group contains the cards that were coming in consecutively. So in this case we can say that we can create the hand of straights using this, so we will return true in this case. Let's take one more example. Suppose the given hand is values 1 2 3 4 and 5, and in this case we are given the group size to be 4. So in this case we can create a group of size 4 with these 4 characters or with these 4 characters, both of which are going to have consecutive values. So values would be 1 2 3 and 4. The thing is, we would still have one more value left that is going to be left out, that we cannot use. So in this case we can return false, because we are not able to create or use every single card inside our hands array. Let's take just one more example. Let's say that currently the values given are 1 2 3 and 5 6 and 8, and in this case the group that we are trying to create is of size 3. So we can see that we can create a group 1 2 3 like this, no issues with this. We can also create a group of 3 cards using 5 6 and 8. But the thing is, this is not going to be a correct group, because we need to create a group that only contains consecutive elements, and 5 6 and 8 are not consecutive cards. If this were to be 5 6 and 7, then it would have worked. So because of that, for this particular example we will have to return false. So that's it. This completes my explanation on what the problem statement is actually asking us to solve. Let's see that what is going to be the optimal approach to solve this problem. Well, the idea is quite straightforward. What I'm suggesting is that we are given currently the hands, and we are also given group sizes. Now we know that for this particular given group sizes we will have to create groups. The values inside the group has to be consecutive. So first thing that comes to our mind is that if we are dealing with consecutive or subsequent values, why don't we just simply sort the given input of hands and then try to start creating groups according to that? Do you think that approach would work? Let's try to see that approach in action. Let's say that this is the current hand that we are given. Now we are trying to use our first approach, where we are going to sort every single value inside our hand array and try to create groups of size 3. So the sorted hand is going to look something like this. Now notice in this problem, if we try to create groups of 3, we would not be able to make consecutive groups. We would run into this issue. If we create a group of 3, we would have a group that looks like 1 2 and 2, and based on this we can just say that this is a false group and we cannot make sense of it. But this would not be the correct assumption. Correct assumption would be that if we identify two values that are same in frequency, then we only need to consider the first value for the partition of first group. So the idea in this case would be that we would create a group that is going to be 1 2, then we found a repeated character, so we would ignore this one and add value number 3 into a group. After creating this group, we will check that whether there has been any values that are currently left. So yes, this 2 has been left. So let's use the same operation. So now we are going to create one more group using this 2. Now notice that we have already used this 3 in the first group, so we are going to be eliminating that, and then we will have values 3 and 4 in this case. So we can also repeat the same operation, and then after all the values that we have currently used, we will keep on trying to make partition and trying to check that whether they follow the property of them being consecutive or not. So in this case, based on this approach, we can actually find the solution, which means number one, there are few assumptions we can make based on this. Number one, sorting is going to be greatly helpful. Second thing is, we come into the issue of duplicated numbers. So we will need to know that what is the frequency of every single character. And if we can combine these two values, store that information that have the sorted values of all the unique values that are present, and have the frequency that how many times they are currently present, it would be easy for us to make these groups. And if we are able to make subsequent groups that follow the all the property, and we are able to use every single value inside the hand, we can return true or we can return false. So using this, what I'm suggesting is that we actually use something smartly. We use a hash map, and we use a sorting approach. Now the thing is, why am I suggesting to use the hash map? Because we are dealing with unique entries, and for each of the unique entry we have different frequency, and this is what I'm suggesting that we store as part of the hash map, where as a key we are going to store that what is the current value of the hand, and as its subsequent value we are going to store that how many times that hand has been repeated in any particular iteration. Next, after storing this information, we will have to sort all of these given keys, because we are trying to generate consecutive values one by one. So logically, why don't we just combine hash map and sorting at the same time, where we can simply use a tree map that is going to have best of both worlds, that can access and fetch all the elements in big O of one time, and it can insert all the elements in big O of log n time for the frequency and stuff like that, because based on the key value. So this is going to be an efficient approach. So now what I'm suggesting is that we are currently given our hand that we are going to be dealing with. For this particular hand, what we are going to do is we are going to create a tree map. This tree map is going to contain the unique value plus their frequencies, and for these two, using these two values, we will start creating groups of bunch of different numbers, and we will need to make sure that the starting, if the starting value of group is, let's say, 5, and the group has to be of size 3, then next value has to be 6 and next value has to be 7. If we can find 6 over here, that's great. If we cannot find 6 at any given moment, we can directly return false, saying that this group is not being able to make. So let's try to see my solution in action. So now based on the hand, we have our tree map ready. Notice in the tree map, we have every single key or the hand value is currently sorted, and we also have the frequency that how many times this is present. Now we need to create the group size 3 for every single value. So the idea would be that for very first group, we are going to take the smallest value out, and we are going to reduce its frequency, and this is going to give us the starting point for that particular group. So starting point is going to be 1, which means this has to be a group of size 3. So next subsequent element that should be in the group has to be value number 2. But thing is, we are not sure if 2 is present or not, and lucky for us, we can check that immediately, that whether 2 is present or not. By the way, when we took this one out, we would have reduced its frequency, so we can reduce the frequency to 0. The moment frequency becomes 0, it would make sense to completely eliminate that element rather than just storing it. So we can eliminate 3. Now we are looking for 2, we found 2, and which means we can also reduce the frequency of 2. So now the frequency is going to be 1. Next thing should be 3. So we are trying to find a 3, and we also found a 3 over here. We are also going to reduce its frequency from 2 to 1. So now this is also going to be 1, and we created our first group. Now for the second group, once again we will check inside our hash map or tree map that what is the smallest element, and this is going to be the very first value inside our tree map, that is starting point is value number 2. So now we are going to use value number 2 over here, which means its frequency is going to become 0. If the frequency becomes 0, we can mark it as 0, and then next element should be 3. So we will check that whether 3 is present. Yes, 3 is present. So we are also going to mark its frequency to 0. Once this becomes 0, we can also eliminate this value, and we can also now we are looking for next element to be 4. 4 is also present, and we can mark 4 as counted, so we can remove that element and close this group. Now after closing this group, we have basically deleted all the elements before that. Now once again we will have to create a new group, then that group starting point has to be 6. So we will going to mark 6 over here, and then which means now we are looking for 7 and 8, and lucky for us 7 and 8 are also present, so we can just mark these as visited. And then in the end, notice that now we currently don't have any value inside our tree map, and because we did not find any place where we could not find an element, so in this case we can return true. Now let's say that in the same example, instead of this being 7, let's say that this value would have been 9. So in this case, what would have happened? That we would have values such as 6, and the frequency of the value is going to be that 6 is present one time, 8 is present one time, and 9 is going to be present one time. Over here we find that the starting point has to be 6. Now for this group to exist, we will have to find value number 7, but 7 would not have been present over here. The moment we identify such thing like this, we could have written false immediately. So this is just for you to understand that under which scenario we would return false, and basically this is the whole solution. Now you can see how beautiful we are doing things. If we calculate time and space complexity, in this case the time complexity is going to be big of n log n. Why n log n? Because it takes us log n time to add all the entries inside our tree map. In terms of space complexity, because we are using an additional tree map, it is going to be big of n, but we can manage that. Now on top of it, we can also do one more optimization, that if let's say the given number of hands is currently 10, and if the given group is equal to 3, so if the total cards are 10, do we even need to check that can we make all the groups of size 3? No. Why? Because 3, we can only create like the group for 9 cards, and there is still going to be one more left out card. So initially we can always check that whatever the size of the given currently h is, if that is going to be divisible by the given group size or not, and this value the remainder has to be 0. If that is the case, then only we will move forward. So this would be a way for us to eliminate few like bad and edge cases. And now let's see the coding approach. Now for the coding solution, first thing we are going to check is to see that whether the given length of all the hands, so all the cards that we currently have, if that is divisible by group of 0. If that is not the case, then we can directly return false, because for sure we would not be able to make the group of that particular group sizes if this is not divisible by 0. If that is not the case, we are going to initialize a tree map where we are using hash map in combination with tree map, because we want to access the keys in a particular order. And now we are going to be counting every single card. So we are going to iterate over each of the card that is currently present inside our hand array, and we are going to be adding that to our tree map, where we are going to define that if that card is present as the key, then we simply update its frequency. If that is not the case, we create a new entry. Then we attempt to form groups, where we are first of all in the outer loop checking that while we still have present cards inside our key tree map, we are going to do the following, where first we are going to initialize the first key or the first starting point of the first group with the smallest key. And notice that because we are using tree map, we can actually just keep on accessing the keys directly, because they would be stored in a sorted manner. Then we are going to iterate over the for loop, focusing on each particular group sizes, where we are checking that what is the current card, that is going to be first plus I. Then we are going to check if we have that current card inside our tree map or not. If we do not have that value inside the tree map, we can simply return false immediately, because we cannot make consecutive groups. If that is not the case, we are simply going to add that value. Then we are going to reduce the value or the decrease the count, because we are removing the card. And then we are checking that if the given count is equal to 1, then we can simply remove that card completely from our tree map. If that is not the case, we simply reduce its frequency and repeat the same operation. If we do get out of this loop, which means we are able to get out of every single card and use every single card to create the appropriate group sizes, and which means we need to return true in the end. So this is the whole solution. Let's try to run our approach. Seems like our solution works beautifully. Let's submit this code. And our code beats good chunk of solutions. It is not the best, and there are still improvements can be made, but given the time frame, this is a good approach. And the solution is present inside our GitHub repository, so feel free to go ahead and check it out from there. Thank you. So the lead code problem we are going to solve now is called valid parenthesis string. We can see that this one is a lead code medium problem and also a very well-liked problem. Basically, we are given a string S that contains only 3 types of characters: open parentheses, closed parentheses, and a star. Now we need to return true if the given string is valid, and there are some definitions given on what is valid. Basically, any left parentheses must have a corresponding right parentheses. That's fair. Same way, any right parentheses must have a corresponding left parentheses. Next point is that left parentheses means opening parentheses must go before the corresponding closing parentheses. So this is valid, but if we have like this, then this is not valid. Okay. And last one is that if we are given star at any moment, then we can consider star to be whatever we want. So we can treat it as a right parentheses or a closing parentheses or an open parentheses, or we can also consider it as an empty string, so that makes no difference. So let's try to see some examples. Suppose we are given a parentheses like this one is a valid. If we are given a parentheses like this, once again this is a valid. If we are given a parentheses that contains star, once again this is a valid. In this case we are treating the star to be an empty string, which means we are basically left with this. We can also say that this is also a valid string, and so on and so forth. So the only scenarios where it is not valid is if we are dealing with number of like out of order parentheses, or we are dealing with multiple parentheses of being like this and only one parentheses like this. So this is also not valid. So let's try to understand the most common logic on how we can pursue solving this problem. Now we know that if we are only dealing with working with problems that only contains parentheses, we can simply use a stack and solve this problem very easily, very efficiently. There are like a lot of different examples of that. I would not go in depth in this case, because the important thing for this problem is this asterisk. So whenever we are dealing with an asterisk, we have three possibilities. We can either consider it to be an open parentheses, we can consider it to be an empty string, or we can consider it to be a closed parentheses. So in each of the cases, let's say that if we are dealing with multiple stars, there can be many possible combinations and permutations that we should be able to make. But that adds more and more complexity to our problem, because let's say that we are given a string like this. Now in this case we need to basically have option over here to choose three different entries for each three different options we have another way to choose three more different options, and so on and so forth. So we can make many different possible combinations. So we'll have to do things smartly. So one solution I'm suggesting in this case is that we use greedy approach, and basically we iterate over the given input in just a single fashion, and we keep track of the number of open parentheses, and we also define that what is the maximum number of open parentheses that we currently can have depending on the star value, and what is going to be the minimum number of open parentheses we can have depending on the given star value. Now there are two possibilities. One possibility is that for any particular star, if we treat it as an open parentheses, which means there is one more open parentheses left for us to deal with. So in that case, we can add basically that value to the max pair character, or we can treat this star as an empty string or a closed parentheses. In this case, we have one less open parentheses that we need to deal with. So in this case, we would update the value for the minimum character. So let me just walk you through the solution I'm suggesting. Let's say that we are currently given an input like this. So in this case, we are going to simply have a few rules for two variables that I'm suggesting. First variable, the variable's name is maximum open, okay, and second one is minimum open. Now for each of this, we are keeping track that what are the maximum number of untouched open parentheses we have, and what is the minimum number of untouched open parentheses we have. The logic is quite straightforward. We are simply going to follow few rules. If the given input character is an open parentheses, then we will have to increment at both the places. So we are going to increment at max and min. If it is a closed parentheses, which means there is one less open parentheses for us to deal with. So in this case, we would decrement at both minimum open and maximum open variables. And we are going to initialize these with value 0. And if the given value is star, in this case, we have two possibilities. So there is one possibility, we treat this as an open parentheses, or we treat this as an closed parentheses or an empty string. So if we are treating it as an open parentheses, which means there is one more open parentheses left for us to check. So we are going to increment at our max open. So for max open, we are going to update the value whenever we encounter a star. And whenever we encounter a star, we can also treat it as a closing bracket. So we will decrement the value at the minimum variable that we have stored. And these are the rules that we are going to follow. Now there are a couple of conditions that would allow us to solve this problem, basically find the loose cases. So first case is that if at any given point we identify that given number of maximum open parentheses go into negative, which means that there are too few open parentheses and too many unopened parentheses. Because remember, when this can go into negative, whenever we have a closed parentheses, then we decrement the value. So let's say that if for the given example, if the first character in itself is a closed parentheses, then we would have decremented the value for maximum open and minimum open. So in this case, the maximum open would have become negative. So we can say that now, even if this is like the most valid string, this is always going to be not valid because it has an open parentheses where we don't have a corresponding closed parentheses. So this is one scenario that we can keep track of. Second scenario is that at the end, our goal is to ensure that there are no untouched or there are no left open parentheses. So let's say that we iterate over the entire given input using these three rules, and we find that there are no open parentheses, which means the min open is 0, then we can simply return 0 as the answer. Now next thing is we have a possibility where if we are encountering a star, we are basically reducing the value of the min parameter. So min parameter can still go into negative, but the thing is this would not directly say that we are dealing with an invalid string. So in this case, if for some reason the minimum variable goes negative, then we are simply going to just start it back to 0, treating that there are no open parentheses left for us to check. And I know that there are a lot of rules that I just talked about, but the thing is, if you just understood what we are trying to do with the example, then it would make perfect sense. So let's say that this is our minimum variable, this is going to be our maximum variable, and we are going to start iterating in this fashion. So first we identify an open parentheses, which means we are going to increment the value for both in min and max. So currently both values are going to be 1. Once again open parentheses, so both values are going to be 2, and once again open parentheses, both values are going to be 3. Now notice what these values define is that what is the minimum number of open parentheses that we will have to deal with, and what is the maximum number of open parentheses that we have to deal with. So far we haven't encountered any star, so that's why the numbers are same amongst both of them. Now we encountered a star, so we can treat the star as either an open parentheses or a dot or a close parentheses. If it's a one more open parentheses, then we would have 4 open parentheses that we will need to deal with. And if we treat this as a closed parentheses, then we will only have to basically deal with one less open parentheses, because we can basically close these two parentheses. So in this case, this value would become 2. And let's try to see this by different examples. So first 3 values we have as open, then we have a star over here. So what are the two possibilities? First possibility is that we create a close parentheses. So in this case, this becomes a close parentheses. So how many number of open parentheses that we are left to deal with? 2, which we are representing over here. If we treat this as an open parentheses, in this case, how many number of maximum open parentheses that we will have to deal with? 4, and that we are capturing over here. And this is the whole logic of the entire solution. So now let's continue moving forward. So once again, we identified one more star. So once again, the minimum variable is going to be decreased by 1. So this would become 1, and maximum variable would be increased by 1. So this would become 5. And now we encounter a closing parenthesis. So whenever we encounter a closing parenthesis, basically we are reducing the values at both minimum and maximum values. So this would become 0 and this would become 4. Now, because we reach to the end of the loop, we don't care about this maximum variable. This maximum variable is only there to keep track of if this goes into negative or not. If it does goes into the negative, which means we can stop immediately and return false. If that is not the case, we check the value of this minimum variable, and if because this is 0, so in this case we can return true for this one, and that this is a valid string. So this is the whole idea behind the solution. Now if we see time and space complexity, time complexity is going to be big O of n because it's quite straightforward. Space complexity is going to be big O of 1 because apart from using couple of variables, we are not using any extra space. So this is a wonderful solution, and now let's quickly see the coding solution for this one. So the coding solution is quite straightforward. First, we are going to initialize a couple of variables called minimum open and maximum open. This is to keep track of the minimum possible open parentheses and maximum possible open parentheses. Now we are going to start iterating over character by character inside our given input string s, and for every single character we are going to check that if there is an open parenthesis, then we need to increment both min open and max open. Otherwise, if it is an closing parenthesis, then we need to decrement both min open and max open. And if that is not the case, which means we have identified a star value, in this case we will need to decrement the minimum open because we are treating it as a closing bracket or an empty string, or we need to increment the maximum open because we are treating it as open left parentheses. Now at any given moment we realize that the max open is less than 0, which means we can return false immediately because there are just way too many closing parentheses compared to the subsequent open parentheses. Now if that is not the case, then we are going to check that at any given point if the min open becomes negative, then we are simply going to initialize the value starting from 0. So min open can go into negative, but we don't care about that. Now in the end we simply need to check that if the given min open is equal to 0, which means that there are no minimum possible left open parentheses. So in this case we can return true, saying that the given parentheses string is valid. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And code beats 100% of all the other solutions, which is exceptional. So once again, I would be posting this solution in the GitHub repository that we have created, so you can find it from there.
So now we are going to talk about a very important topic called intervals. It has a lot of real life practical applications because you can imagine a scenario if you are trying to design like Microsoft Teams or Zoom or any sort of calendar like application. You need to be able to find slots where people can book availability. If you are given bunch of different slots, you should be able to find appropriate intervals that follow certain property. So it is a very popular topic, and I'm going to solve 7 questions. This 7 question will comprise all the topics that interval has to offer. So I'm not going deeper into the introduction part. We will start jumping into the actual interval lead code problems that would cover all the topics. So I hope you find it useful.
Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do meeting rooms lead code problem, and this is actually a lead code premium problem. So if you want to know that what are the list of companies that have asked this question in their interviews, that comes later in the video, and I have provided the timestamp for that, so you can directly go and check it out. Let's understand the problem statement. Essentially, we are given an array of meetings called intervals, and we are given start time and an end time for every single meetings inside this given array. Now we need to determine that if one person can attend all the meetings or not. So let's try to understand this given problem by an example. So over here we are given 3 different meeting times, and let's try to plot them on this number sequence that we have created. So first meeting starts from 0 time and it lasts until 30 minutes. Second meeting starts at 5 minutes and ends at 10 minutes, and third meeting starts at 15 minutes and ends at 20 minutes. So over here we can clearly see that there is no way possible for one person to attend all the meetings, because there exists a conflict between this meeting and this meeting, and there also exists a conflict between this meeting and this meeting and this meeting. So because there is an overlap between intervals, and essentially that's what we will have to determine in this problem. So over here we can clearly return false, that there does not exist any way possible for one person to attend all the different meetings that are given in this interval. Now if we take a look at the second example, and let's try to plot it in on a number sequence. So over here we can imagine a number sequence like this, and over here we are given one meeting that starts at 7 and ends at value number 10, and second meeting starts at 2 and ends at value number 4. So over here we can clearly see that it's possible for one person to attend this meeting, and after that he or she can attend this meeting. So in this case we will return true, and basically that's what we will need to determine. Now the tricky part over here is that we will have to determine that how do we identify that there exists overlap between any two values. So suppose over here in this example, if we are given another meeting that starts at 3 and ends at 5, something like that. Now in this case, can we say that can one person attend all the meetings or not? Well, we can clearly see that because there is an overlap between these two meetings, one person won't be able to attend all 3 meetings, and over here we will have to return false. The thing is, why we were able to determine that over here there exists an overlap. So because over here we see that the starting point for this meeting and ending point for this meeting is from 2 to 4, so that is one interval. And if we look at this one, the starting point from this for this one and this ending point for this one is 3 to 5, so this is 3 to 5. So over here, if we consider this particular interval, we can see that the starting point of this interval actually falls somewhere between any other interval that already exists. So at any moment, if we determine that the starting point of some interval, if it falls between any interval and this condition is satisfied, that 2 is actually less than 3 and 3 is actually less than 4, which means 3 falls in between this interval. So that's why we can determine that there exists an overlap, and the moment we identify that there is an overlap over here, we will immediately return false, and this is how we are going to approach. Suppose we are given an input like this, the different intervals are given, and this is the number sequence that we are going to use. Now over here, essentially, if we want to determine that can one person attend all the meetings, we will have to check that whether there exists a conflict or not. So if we look at this first scenario, previously we determined that how to identify an overlap. So if we look at the starting value of this 20, we will have to check that whether this 20 exists in between some intervals. So over here, this is 10 to 15. So 20 does not exist over here. This is 35 to 45. So 20 does not exist over here. And this is 10 to 20. Now this meeting ends at 20 and this meeting starts at 20. So this is also a legitimate scenario because 20 is not part of this interval. So that is why we can determine that, okay, this meeting is good, like the starting point does not have a conflict with any other meetings. Now let's see about this one. So this meeting is from 0 to 15, right? So does there exist any conflict between these two, between this 0? So 0 does not exist between this one. 0 also does not exist over here, and 0 does not exist over here. So we are good. Same goes for this 35, that 35 does not exist between these two, this one or this one. So we are good. But when we come to this value number 10, we can clearly see that this 10 actually falls between this 0 to 15 because this condition is satisfied. 0 is less than 10 and 10 is less than 15. So over here we can clearly see that there exists an overlap between these two elements, and we can immediately return false. So this approach would work perfectly fine. But what is the issue with this approach? The issue is that this takes big O of n square time. Why big O of n square time? Because remember, for every single element, we will have to check all the remaining elements based on the starting point. Same goes for this one, same goes for this one. So that's why we are doing n square work. So this work can greatly reduce if we just sort the given input based on the meeting start times. And let me show you how. So let me clean this up and let me sort this given input. So now we have the sorted input. Now in the sorted input, if you take a look at it, we are actually able to determine that whether there exists an overlap immediately. How? All we need to do is we'll need to compare the starting point with the ending point of the previous interval. If the starting point is actually less than the ending point of previous interval, we can determine that this meeting actually starts before the previous meeting ends, and immediately we can identify that whether there exists an overlap or not. So this is basically our solution. Like in this scenario, we can clearly see that the moment we are in the meeting from 0 to 15, so there is a meeting going on from 0 to 15, and before this meeting ends, there is another meeting that starts at 10 and lasts up until 20-minute mark. So there is an overlap over here, and immediately we will return false in this case. So this approach actually works, and it is more efficient than the previous approach we suggested. Why it is more efficient? Because if we calculate the time complexity in this case is going to be big O of n log n for the sorting operation, because from this given input, first of all, we'll have to create a sorted input. And once we are done with that, if we want to identify the overlap, we only need to check any two adjacent values at any given moment. And the moment we reach to the endpoint and we don't find any issues, we can return true, or if we find any issue, we can return false before that. So this takes big O of n time. So total time complexity can be considered as big O of n log n. And in terms of space complexity, we are not using any additional space, so we can say that we are only using constant time to run this problem. And this is the final approach. Now let me show you the list of companies that have asked this problem. And if you are not interested, you can directly go to coding. So essentially, companies like Amazon, Google, Facebook, they have all asked this problem recently. And Microsoft and Wayfair, they are also really popular, well-paying companies that have asked this problem. Also companies like Bloomberg, Adobe, and eBay, that one of my dream companies that I want to join in, apart from the original, these tech giants. So first of all, we are going to sort the given input based on the start times of the given intervals. After sorting, we will have to iterate over all the sorted intervals, and we are going to check that whether there exists an overlap or not. We are going to check that whether the end point of any meeting is greater than the starting point of next meeting. If that is the case, we are going to return false immediately. And if this loop ends and we are able to reach to the last element, we are going to return true, that there does not exist an overlap. And now let's try to run this code. Okay, seems like our code is working. Let's try to submit the code. Okay, our submission works, and the code is actually pretty efficient, and I would be posting this in the comments. It is not too many lines of code, and this problem is very similar to the previous 3 interval problems that we have done. So I would be posting them in the comments. You can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. If there is any question that can get you in the FAANG, it's this one that we are going to solve today. Because if you just see that the number of companies that have asked this question, it's just out of this world. This question has been asked by hundreds of companies, literally hundreds of times. You can see over here that like Facebook and Amazon, they both have asked this question recently over 100 times in their interviews. So you can imagine the severity and the importance of this problem that we are going to solve. So apart from Facebook and Amazon, if we look at the number of companies that have asked this question, there are companies like Google, Salesforce, Microsoft, Bloomberg, Apple, Uber, LinkedIn, IBM, VMware, Walmart, TikTok, Adobe, Twitter, ByteDance, and then there are companies like Yahoo, PayPal, Wish, Goldman Sachs, Robinhood, and also Palantir, Square, and Netflix. So these are all one of my dream companies where I want to get a job. That's why I'm making these videos, and that's why I made this channel. So I would be paying my utmost attention. I hope you also enjoy the video. This is a LeetCode medium problem, and it is one of the most liked problems on LeetCode, and that's why a lot of companies likes to ask this problem. So essentially, we are given an array of intervals where every single entry inside the interval mentions that there exists a start point and an end point of that particular interval. Now we need to iterate over all of the intervals, and then we will need to merge all the overlapping intervals. And we need to return an array of non-overlapping intervals from this given input, and that would be our solution. So if we try to understand this with an example, suppose we are given some set of intervals like this. Now let's try to mention them on this number sequence that we have drawn out. Now over here, our aim is to return all the non-overlapping intervals, and if there exists an overlap, we will need to merge those two intervals. So first of all, we will have to identify that what are those two intervals where we can see an overlap. So essentially, if we look at the start values of this interval, so the start value over here is 1 and 3. And if we look at the start value of this second interval, the start value is actually 2 and 6. And over here, we can clearly see that there exists an interval amongst these values. And these are the two intervals that are causing an overlap, and we will have to merge them. Now the question is, first of all, we need to know that why we were able to calculate that there exists an overlap over here based on the given input. Like this is a pictorial representation. We can clearly see that why there is an overlap. But in terms of computer, we will need to dictate some sort of mechanism. So essentially, we can say over here is that at any point, if we start iterating over any number of intervals, and if we identify that for those particular intervals, if the starting value, so in this case the starting value is actually 2, if this starting value falls between any interval, so because this 2 currently falls in between this 1 2 3, this first interval is 1 2 3, and over here the starting value of this new interval actually falls between those places. And the moment we identify that okay, this 2 falls between this 1 and 3 interval, so we know that okay, this interval that starts at 2, so this 2 to 6 is also causing an overlap between this given input interval, and we'll need to merge them. So this would be our condition to identify that at any moment, at any interval, we are trying to see that whether it intersects with some other interval or not. What we are going to check is we are going to see that suppose this value is the start value. So we are going to see that this start value, if that meets, if that is less, if that is greater than whatever the interval start we are checking and whatever the interval end we are checking for. If this condition is true, we can determine that there exists an overlap. And now since we have already identified that there is an overlap, we'll need to resolve that. So in order to resolve that, how we will resolve that is we will create an interval from this value number 1 to value number 6. So essentially we are merging both of these intervals. And what is the condition we are using to merge these two intervals is that we are going to check that okay, for the starting point of the new interval, what is the minimum value amongst both the start values. So in this case over here, the first start value is 1 and second start value is 2, so the minimum value is actually 1. So we create an interval that starts at position number 1, and for the end value there is this 3 and 6. So we compare this value 3 and we compare the value 6, and we identify that okay, 6 is greater in this case. So for the end value we are going to pick the maximum value amongst two values. So we are going to create a new interval like this, that is from 1 to 6, and then essentially we have taken care of these two overlapping intervals. And for this one, this 8 to 10 and this 15 to 18, these two intervals, they are not causing any kind of overlap, so we can just directly put them as it is inside our answer. So in this case, if we try to calculate that what would be our answer, the answer is actually quite simple. Our answer in this case is going to be an interval from 1 to 6, and this is the merge interval. Second interval is going to be 8 to 10, and the third interval is going to be 15 to 18. So this would be our solution, and we can simply return this one. Let's try to understand the same problem with another example that is given over here. So in the second example, we are only given two intervals, 1 to 4. So this is one interval, 1 to 4. So the question comes that are they overlapping integers? And the answer is yes. Why? Because if we see at this value number 4, actually 4 is connecting point for both the intervals. So 4 is the ending point for the interval 1, and it is the starting point for the interval number 2. So in this case, we actually need to merge these two intervals, and we will have to create an interval like this, that is from value number 1 to 5. And again, we are going to use the same logic. The logic is going to be that over here the values were 1 to 4, and over here the values were 4 to 5. So for the starting values, we are going to choose the lesser value, and for the ending values, we are going to pick the maximum value. So maximum value in the lesser value in this case is going to be 1, and maximum value is going to be 5. So this would be our intervals, and these are all the scenarios that we need to take care of. So suppose we are given a custom example like this. Let's see that what should be the solution. And always remember that it is really important for any programming interview that you come up with your own custom examples. It shows that you have the ability to think about all the different kinds of test cases, and you can come up with some unit test on your own. So over here our aim is to find that all the non-overlapping integers. Now for to find all the non-overlapping integers, we already know that what is the condition, that how can we determine that any particular value is actually causing an overlap. And the way we can do it is that by checking the start value and comparing it with that whether it exists somewhere in between any given interval. The question is, previous two examples we saw, they were already sorted, so they were, all the starting values were already in a sorted manner, so that's why it was really easy for us to identify that whether there exists an overlap or not. But nowhere in the sequence we are told that all the input should be sorted, so that's why that makes things a little bit more complicated, and let's see that how it does so. So over here, suppose we are given an input 4 to 6. So we can create a line over here that, okay, there exists an interval like this from 4 to 6. Now second one is 11 to 15. So again, there is an input like this 11 to 15. Next one is 7 to 9. So there exists an input from 7 to 9. And this next input is 2 to 5. So we know that there is an overlap, but we are going to just draw it over here. And the next one is 13 to 16. So over here we can clearly see that there are two places where there exists an in overlap, but we don't know that yet, right? Because the input is not sorted and we will have to identify it by ourselves. So how we are going to actually identify? Well, essentially we are going to use the same logic. We are going to check that whether the start value falls in between any of the interval. If it does, we are going to determine that, okay, that part so if it does, so we know that this particular interval is in conflict with that interval, and then we are going to have to merge it. So let's try to do that. So over here we are comparing this value number 4, that is the starting value. First of all, we are going to check that whether 4 falls between 11 to 15. Well, it does not, so we are good with this. Whether 4 falls between 7 to 9, it does not, so we are good. But over here 4 actually falls between 2 to 5, because 2 is actually less than 4 and 4 is actually less than the 5. So we know that 4 actually exists over here, which means there exists a conflict between this and these two intervals. So we will have to resolve this conflict. How we are going to resolve this conflict? Well, of course, we are going to create a new interval. So starting value is going to be the lesser of both of them. So we are going to have a starting value that is at 2, and for the ending value it's going to be greater of both of them. So the ending value is going to be 6. So we are going to create a new interval like this, that is from this value number 2 to value number 6, and we are good with this one. So essentially we have merged these two intervals, so we can just simply mention that, okay, these two are merged or these two are taken care of, so we don't have to worry about them anymore. And now we are done with essentially these two intervals, right? And we have, in our answer we already have this this new interval stored. Now let's see that how can we move forward. So again, for this 11 to 15, again we will have to repeat the same process. So we check that whether this 11 falls in between some interval. So first of all, we compare this 11 with this 4 and 6. So it does not fall in between. And also remember that because we are done over here doesn't mean that there could not be any more overlaps that we cannot take care of. So we might have to do it. So that's why we are going to compare again all the values. So 11 does not fall between 4 to 6, 11 does not fall between 7 to 9, 11 does not fall between this 2 to 5, and 11 does not fall between 13 to 16. So far we are good that, okay, this 11 to 15, that is okay, we don't have any issue with that. Now we again check for the 7 to 9. So we check that whether the 7 falls in between somewhere. So 7 does not fall over here, it does not fall over here, it does not fall over here, and it does not fall over here. So this 7 to 9 is also good. 2 to 5 we have already checked. Okay, so this value number 2 does not fall anywhere, so we are good with this interval as well. Now again we are at this interval number 13. So for this interval number 13, it does not fall here, but it falls in this place. So we again have a conflict between this these two intervals. So 13 to 16, that is one interval, and second one interval is 11 to 15, there exists a conflict. So because there exists a conflict, we will have to resolve that, and we can mark these two as done. So we are going to create a new interval that is 11 and 16, which means lesser values of the starting values and greater values of the ending values, and this would be our new interval. So we can add this to our answer as well. So this would be 11 and 16. This is also our answer. And now we need to check that amongst these intervals, which were the ones that were not part of any overlapping series. So we know that this particular value 4 and 6 was part of an overlap, 2 and 5 was also part of an overlap, 11 15 and 13 16, they all were part of overlap, which we have taken care of with these two values. So this 7 and 9 was not part of any overlap, so we will have to add that to our answer as well, and we will add the 7 and 9 to our answer, and this would be our final answer in this case. Now the thing is, we are able to resolve this quite easily, right? We are able to generate the answer, we know all the logic and blah blah blah, we are able to identify the overlapping condition. If we calculate the time and space complexity in this case, the time complexity is actually big O of n square. Why n square? Because remember that for every single entity we are going to have to check all the remaining elements. Same goes for this one, that for every single entities we are going to have to check for all the other remaining values, so that causes n square work. The question is, can we do something better over here, and that rather than using this n square, can we bring down the time complexity? And the answer is yes. Okay, let's sort this given input. So the sorted result would be, now this is the sorted result. Now we need to identify that whether there exists a conflict or not. So it becomes really simple. What we are going to do is we are always going to check the first value, and we are going to compare that whether the starting point of any value, if that is actually less than the ending point of the previous element. If that is the case, we would be able to identify that there exists a conflict. And always we are going to start checking from the second value, because for the first value we know that the first element is already the smallest value. So even if there exists a conflict between first two entities, this first one would always act as a starting point of the new merged variable, or the new merged interval. So let's try to do that, and over here we will start with the second position. We know that okay, this one is 4, we compare it with the last element of the previous interval. So last element of previous interval is 5, so we know that actually 4 is less than 5. In this case we know that there exists an overlap between these two values. Because there is an overlap, we can see that we need to take the minimum value amongst these two. So minimum value is actually 2, so we create a new interval starting at 2, and for the ending values we will have to check the last values. So the ending value in this case would be 6, so we will have a new interval like this. So let's draw a new interval like this on this number system. Now we are already done with these two values. Now we take a look at this value number 7. So again for the 7 we compare with the last element in this case. So 7 is actually greater than 6, which means there does not exist a conflict between these two values. So we can start creating a new interval from 7. And now again for this 11 we are going to compare it with the last element. So over here this value is 9, so 9 is actually less than 11, which means in this case there does not exist a conflict. So 7 to 9 is an interval in its own. We are good with this one. Now we have calculated this one. Now again over here this is 13 and this is 15, so we know that 13 is actually less than 15. So in this case there exists a conflict between these two values. So because there exists a conflict, we are going to do the same conflict resolution technique. We are amongst this 11 and 13 we are going to pick the smaller value. So smaller value is going to be 11, so we pick this one. And for this 15 and 16 we are going to pick the greater value. So 16 is the greater value. So again we are going to create an interval like this, that is from 11 to 16. So essentially we have taken care of two overlaps that existed between these two values and these two values, but we were able to identify them immediately. Why? Because all we have to do is at any point we just have to compare one value that was in the previous interval at any given moment. And now over here we can just simply start iterating over whatever the answer we have found so far. So in this case we can simply return the answer as 2 to 6, 7 to 9, and 11 to 16, and this would be our solution. Now if you look at the solution over here, essentially all we had to do is just iterate over the sorted input once. So basically to generate this answer we are only doing big O of n work, but the total time complexity in this case is actually going to be big O of n log n. And why n log n? Because we will have to generate the sorted input from this given original input, and that takes n log n time. First of all we are going to sort the given input. Okay, after sorting the given input based on this, based on their starting values, we are going to create a linked list, and we are going to store answer in this linked list. Now we are going to iterate every single interval inside the given input. So now we are going to check that whether we are at the first position, or whether the given interval, if that is in conflict or not. So if that is not in conflict, or there does not exist an overlap, we are simply going to add it to our answer. Okay, if that's not the case, we have detected a conflict, and the moment we detect a conflict, we will have to resolve the conflict. So essentially we are going to add the new interval that is merged. Okay, and after this loop ends, essentially our answer should be in the answer linked list, so we can return that. But in this case, we need to return a two-dimensional array, so we will convert our answer list to a 2D array. Okay, let's try to run this code. Seems like our solution is working. Let's try to submit this code. Okay, our solution works pretty efficiently. I would be posting this solution in the comments. You can check it out from there. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very interesting lead code problem, interest interval. And if you see the number of companies that have asked this question, it's really amazing. The companies like Google, LinkedIn, Amazon, Robinhood, Facebook, Uber, Apple, Twitter, Microsoft, ServiceNow, Bloomberg, and Goldman Sachs. Like, these are, if you see the description of my channel, these are my dream companies that I want to get a job of. So that's why I'm doing these questions and I'm paying my utmost attention. I hope you also enjoy the video. So this is a lead code medium problem, and essentially we are given an array of non-overlapping intervals. This is a multi-dimensional array. It's a 2D array, and at any given cell, essentially we are given the value like start and end, which indicates that there exists an interval between those times. Now our aim is that we need to insert a new interval into the list, into the array of intervals that we are already given, and we need to maintain this non-overlapping quality of the intervals. So if we try to understand this with an example, suppose over here we are given a set of intervals like 1, 3, 6, 9. So we are given an interval like this 1, 2, 3. This is already given, and we are also given another interval like 6 to 9, and we need to insert a new interval called 2 to 5. So if I draw it on paper, it would be something like this. So 2 would fall over here and 5 would fall over here, and this is the new interval that we are trying to insert in this original existing interval. So how can we insert this new interval? Well, the answer is actually simple. Essentially what we are going to create a new interval is that we will start an interval at position number 1. Then from 1 we will have an interval all the way up until the position number 5, and then we will have another interval from position number 6 and all the way to position number 9, and this would be the two intervals that we will have to take care of. Now the thing is, in this problem we can clearly identify that why did we come up with this approach, because we wanted to make sure that we do not have any overlapping intervals. So that is why when we found out that this is the existing interval and this is the new interval that we are trying to achieve, if we wanted to insert this one, there exists an overlap between these positions, between this 2 and 3. So that's why, because there was an overlap, we actually chose to merge these two intervals, and we created a new interval like this. And for this one, this had no concern with the existing with the coming of new interval, so that's why we left it as it is. So let's see that what could be the different approaches we can take, what could be the different scenarios, and how we need to behave in any single scenario of them. And essentially that would be our solution. So first of all, if suppose we are given a number series like this, and we are given a list of intervals like this, that there exists an interval between this value 2 to 4, there exists another interval between this value 8 to 10, and 13 to 15. Now let's see that where different set of intervals can be entered. So suppose first of all we are given an interval like this that is not overlapping with, or that is not in conflict with any existing interval. So let's see that what would be the scenario in that case. Suppose we are given an interval like this, that from 0 to 1 we are given an interval like this. Now if we see this new interval, it has no sort of conflict with any of the existing intervals. If we wanted to add this to our array of intervals, it would be just pretty simple. We simply create a new interval like this, 0 to 1, and then return whatever all these values are, and this would be our answer. So we would be done in this case. There won't be any issue. But suppose if this is not at the first or at the beginning of the intervals, if this is at the end of an intervals, so suppose this particular new interval that we are trying to enter, suppose we are given some interval like this, that from 16 to 17 we are given an interval. So suppose we are given an interval from 16 to 17, something like this. Now in this case, what would be the approach? Essentially we would be doing the same thing. What we would be doing is we would be transferring this interval on top of whatever the existing intervals we got. And how we are going to do it, basically we are going to start traversing towards the original given input. We are going to see that, okay, where is the starting point of this new interval, and where this new interval can fit inside the existing set of intervals that we have. Now in order to check that, essentially what would be helpful? It would be helpful if we had a sorted set of intervals, and in this scenario all the intervals that we are given, they are already sorted. So that is why which works in our favor. So which means it becomes really easy for understand that where this new interval we wanted to shift into. And in this case, so we will start traversing. We will first see that, okay, this is the value 2, this is 16, we don't care, so we move forward. Again we are done with this interval. Now what is the next start point of this interval? This is 8, and this is 10, and this is 16. So again it doesn't matter, there is no overlap, so we can put this in the answer. Again this is 15, this is 13, this is 15, and this is 16. So again there is no overlap, so we can put this in the answer as well. And then we find out that after 15 there are no intervals, and we need to enter this new interval 16 and 17. So we simply add it over here from 16 to 17, and we add this to our array of answers as well, and we return these 4 as a new set of intervals. Now suppose somewhere in the rather than this one, these are like easy scenarios where we are given at the beginning or at the end. Suppose we are given something somewhere in the middle. So suppose we are given a new interval that we have to take care of, something like this, that it is from 5 to 7. This is the new interval that we are trying to insert. What should be the approach in this case? Again we are going to repeat the same case over here. This is the value 5 and 7. And now what we are going to do is we will start iterating over this given input. We will see that, okay, first value is 2, and the end of this interval is at 4. So this is 2 and 4, and the new interval starting point is 5, which means there is no conflict so far. So we would add this to our set of answers. Now from this 4 we reach at this 5, and at this 5 is the starting point of this new interval. So we check in our original set of intervals that from 5 to 7, does there exist any conflict? So from 5 to 7, actually there is no conflict in our original interval. So if there is no conflict, we simply add a new interval over here from 5 to 7, add it to our list of answers. And because we have reached the end of our new interval, right? We have reached the end of our new interval, which means what this dictates is that from this point forward, there cannot be any existing interval that could be causing any sort of overlap with this with the arrival of this new interval. So whatever the answer or whatever the list of intervals we are given beyond this point, once we have already entered this new interval, we can simply add these to our answer array, and this would be our solution. So this would make our lives very easy, and that is how we would be able to handle this scenario as well, right? Now so far all the three scenarios we saw, we entered the value at the beginning, at the end, or somewhere in the middle, but in all the cases there was no conflict between existing intervals with the arrival of new intervals. Now suppose the new interval that we are trying to enter, that new interval is something like 3 to 8. Suppose it's something like this, that now we need to take care of this scenario where we are handling this new interval, and which is from 3 to 8. So what should be the approach in this case? Well, the approach is actually quite simple. We will start iterating over our input. We will find all the intervals. So first we find that what is the start point of this interval. So the start point of this interval is 2. And what is the end point of this interval? The end point of this interval is 4. Now what is and every time with the end interval, we are going to compare the start interval of the new interval that we are trying to insert. So the start interval of this one is 3 and this one is 4, which means that we know that we will have to enter this 3 over here, and there exists a conflict. Now since we have identified a conflicting scenario, what should be our approach? Well, our approach should be simple, that we are going to take a look at this particular interval, and we are going to take a look at this particular interval. Now there exists a conflict. Because there exists a conflict, we are going to check the starting points of both the intervals. Now in terms of starting points of both intervals, this one is smaller than this one. So whatever is the smaller, we are going to treat this as the starting point of this new interval that we are trying to enter, because there exists an overlap amongst these values. So we are taking care of the overlap. So that's why this would be our starting point. This would be the start of this new interval, and we are going to drag this new interval up until the end of this point. So up until the end of this point, when we come, we find out that it comes up until all the way to value number 8. Now in this scenario, we did not had anything in the middle, but if we did had anything in the middle, that would have been merged by this new interval, right? But the thing is, even when we come at this position number 8, we see that actually the position number 8 is start of another interval. So which is this one. So if it is start of this interval, we cannot just treat this as a separate interval. I mean, what I'm trying to say is we cannot have an interval like from 2 to 8 is one interval, and from 8 to 10 another interval, because this 8 is actually a conflicting point, and it is because it is a connecting point, these two intervals also needs to be merged. So because this 8 is a connecting point, we are going to merge this interval with this new interval that we are trying to create, and essentially this interval from 8 to 10 will also be dissolved by this new interval, and we would have an answer like this in this scenario, that we would have a newly created interval from 2 to 10. This would be for one interval where we have, and this would be another interval, because remember, now we have already entered this one, which means all the values beyond this point are not part of our concern. We can simply add it to our list. And in this scenario, the second interval would be from 13 to 15, and this would be our answer that we are going to return. So this is one conflicting scenario, and I mentioned that how we are going to tackle it. So essentially the different test cases in this case we can have is that we can either have a scenario where the item lies somewhere between beginning or at the end, where it is not conflicting with anyone, or it can be existing somewhere in the middle where it is not overlapping with any other interval, or it can be a case where it conflicts with some intervals, with one interval or more than one intervals. In either scenario, what we are going to do is, the moment we find that there exists a conflict, we are going to see that what is the start point, what is the lower value amongst these two. So because the lower value is 2, we are going to start this new interval starting from the position number 2. Okay, now for the end position, again we are going to do the same thing. We are going to check that what is the end position of this existing interval and what is the end position of this new interval, and in the end position we will have to check the maximum value, because the interval we are trying to create should be the size of biggest interval that we could create, which is not overlapping with any other interval. So that's why we would have an interval that is maximum amongst these two ending values. So these two ending values, the value is 8. So we would have an interval from 2 to 8 so far. But the thing is, this is not the end yet, because when we come at this 8, we will still have to check for the conflicting scenario. So over here we would have the starting, we would have two intervals like this, and in the two intervals we have the 8 value as the value number 8 as common. So we are going to merge these two as well, and in this case we are going to choose the biggest value we can find as 10, and we are actually, rather than having an interval from 2 to 8, we would actually have an interval from 2 to 10. And this is the critical part to understand, and this is basically our solution. Essentially we are using the greedy approach, but this is all. We don't need to do anything else. And if we calculate the time and space complexity, the time complexity in this case would be actually big O of n, because at any point for this new interval we would need to find that what should be the entry point of this new interval, and then we will check for the conflicting scenario. If there exists a conflict scenario, we will find a way to put it there. If there does not exist any conflicting scenario, well, good for us. In terms of space complexity, well, for the space complexity it would also be big O of n, because we will have to create a new array of list of intervals that we are going to return. So we will have to create a new two-dimensional array, something like this in this scenario, from where the answer would be 2 to 10 and 13 to 15. So this would be our new array that we are creating, and we would be returning that. So that's why that explains the space complexity. And yeah, this would be the solution. Now the question is, where can you use these kinds of approaches? Like, what is the point of having this question at the first place? And actually this is a very interesting question. It has a lot of practical applications. Practical applications is like, suppose you are trying to design an app where you need to maintain some sort of calendar, or you need to maintain scheduling. So these are very practical, very real life applications. Google Mail, Outlook, all the companies, they all use this mechanism. So if we know that where we need to insert an interval where we are not creating any conflict, it could be a conflict between shifts of two employees working for a factory, or it could be the interval between two trains going through a station. So like, yeah, these are real life practical examples, and that's why that justifies the number of companies that are asking this question. So first of all, we are going to initialize some variables, and we are going to create a new start and new end for the given new interval. We are also going to create two pointers, left and right, and left would be at the 0th position inside the given intervals, and right would be the size of the given intervals. We are also going to create a linked list to store all the output, and then we are going to convert it into the array. So now first of all, we are going to add all the non-overlapping intervals that come before the new start. So we are going to create a while loop. Okay, now inside our given list, we will need to add the new interval. So in order to add the new interval, we will have to check two conditions. There could be two possibilities. There might be an overlap, or there could not be an overlap. So we'll have to take care of both of them. So first we are going to create a parameter called interval, and we are going to store all the value inside this parameter. Now we are going to check the condition that if the current position where we need to insert the new interval, does there exist an overlap or not. So if there is no overlap, we can just simply add the new interval. So if that's the case, we can just simply add the new interval. If that is not the case, which means there exists an overlap. So if there is an overlap, we will have to first of all check that what entry what should be the starting point and ending point of the overlapping character, and that we can define by choosing the minimum out of the starting values or the maximum out of ending values. So first of all, we are going to add the last value we have in our linked list inside this new interval variable that we created. And now we are going to check that what should be the endpoint, and we would add the new entry to our linked list. Okay, now we might have to merge all the elements that are after that came because we added this new interval. So we will take care of the merge scenario. And if there exists an interval, we will do the same thing that we did before. So essentially we can just repeat this process. Yeah, after this loop runs, we should have everything stored inside the linked list, so we can return the linked list, but we will have to convert the linked list to an array. This should be our answer. Let's try to run the code. It seems like our solution is working. Let's try to submit this code. Oh, we will have to check for this end variable here, so that's why. Okay, looks like our solution is working, and it's actually pretty fast compared to a lot of other solutions. And even in terms of space complexity, we are also saving a lot of time, a lot of space as well. So I would be posting this in the comments. You can check it out from there. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do non-overlapping intervals problem, and this problem is actually very similar to merge interval problems and insert interval problems. I have solved both of these problems, and I will be posting their links in the description so you can check it out from there. Like, though this problem seems like it has not been asked by many companies, actually this can be a very interesting post question after these two interview questions. So usually, like all the interval problems, they are done in sync. And even for this particular problem, if we see, it has been asked by tech giants like Facebook, Amazon, Microsoft, Bloomberg, Apple, Oracle, Google, ByteDance, which is TikTok, and Snapchat. And these are my dream companies, so I'm paying my utmost attention. I hope you also enjoy the video. This is a lead code medium problem, and we are basically given an array of intervals where every single entry has a starting point and an ending point that represents that particular interval. Now our aim is in this problem is that we need to return that how many minimum numbers of intervals that if we remove from this given original input, if we remove those, then the remaining result should be such that all the intervals becomes non-overlapping. So we need to return the number of intervals that we need to remove. So let's try to understand this problem with an example that is given over here. And over here we are given some set of intervals, and let's try to plot them on this given number series and see that what would be the answer. Okay, so after plotting all of these, our aim is to see that, okay, if there exists an overlap inside this given interval, we need to return the minimum number of intervals such that all the remaining intervals becomes non-overlapping. So over here we can clearly see that, okay, there exists an overlap between these points, and the overlap is actually mainly caused by because of this particular interval and these two intervals. So our aim is to remove the minimum number of intervals that that basically allows all the remaining intervals to become non-overlapping. So in this case, if we simply remove this particular interval that starts at position number 1 and ends at position number 3, this big one. So if we get rid of this particular big interval, we will have a result where all the intervals, they are actually not in collision with each other and they are not overlapping with each other. Over here we can see that they actually connect at some point, but that is not an overlap. Like, I know that in previous questions we used to consider this as an overlap, but you can confirm this with your interviewer that with what approach they want to go. So in this case, we only get rid of this one interval that was existing, and because we get rid of one, we will return one. That in this given input, if we simply remove one interval, we can determine that, okay, there exists one interval such that if we remove that, then all the other intervals becomes non-overlapping. Now to generate the optimal solution, the main thing is that we will have to determine that whether there exists an overlap inside the given interval or not. Now in the previous examples we saw, the input was already sorted, but in the problem statement it is nowhere written that the input should be sorted. So input could be something like this where everything is different value. Now the thing is, first of all, over here we need to determine that what are the intervals that are actually causing the overlap, and then we can determine that which one should be removed and what not, blah blah blah, what should be the strategy for that. Now the thing is, if we plot these this given input on side on a number system, we will get a result like this. Over here we can clearly see that there exists a conflict between these two intervals, which is represented over here. The thing is, how we were able to identify that there exists a conflict? We were able to identify it because the starting point of this particular interval was actually falling between the two values of some already existing interval. So that is the condition we will have to determine if we want to find that whether there exists an overlap or not. So over here, suppose we get at value number 5 and we want to check that whether 5 has an overlap anywhere. So 5, we will have to check all the other intervals. So 5 does not exist between this 2 to 4, so there is no overlap with this one. It also does not exist between 8 to 9, so there is no overlap, and it does not exist between 1 and 3, so that's why there is no overlap. So now we are say that okay, this 5 7 has no overlap with any other interval. Now we check for this value number 2 to 4. So again we check the starting point for the value number 2. So value number 2 does not fall between 8 to 9, so there is no overlap. But 2 actually falls between this 1 to 3, because 1 is actually less than the value 2 and 2 is actually less than the value number 3. So which means 2 falls between this interval. So that's why the interval 2 to 4 and 1 to 3 are in between an overlap, and then we will have to take care of that scenario. Now, do you see a problem with this one? And the problem is that I can see is that for every single value, we will have to check all the other remaining values, that whether there exists an overlap or not. And that actually causes big O of n square time. And this is unnecessary work. Like even just to determine that whether there exists an overlap or not, we are actually doing big O of n square work, which is like pointless. There exists a better approach, and the better approach is that if we sort the given input and then we sort them based on their starting values, things becomes a lot easier. So let's see that what should be the sorted array. Now we have sorted this given original set of intervals, and now we have all the values sorted. So now if we want to identify that whether there exists an overlap, all we need to do is we just need to compare any two adjacent values, and the moment we compare any two adjacent values, we can directly tell that whether there exists a conflict between them or not. How can we tell them is that we only need to check that whether the starting point of any second interval compared to its previous interval, if that is smaller, then we know that there exists a conflict. So in this case, we can say that between this 1 and 3 and 2 and 4, there exists a conflict because this particular interval ends at value number 3 and this particular interval starts at value number 2. So that's why there is a conflict. Meanwhile, if we see over here, this particular interval ends at value number 4 and this one starts at value number 5. So that's why there is no conflict. So this is a very easy way for us to determine that whether there exists a conflict or not. And if we see in terms of time complexity, the time complexity for the sorted operation takes only big O of n log n, which is a big improvement compared to the previous time complexity for this one, which was big O of n square. Okay, now we have determined that how to identify overlap. The question is that how to find that what should be the most number of nodes that we will have to remove, and what should be the strategy for it. So essentially there can be three different scenarios at any given moment. The first scenario is that between two intervals there does not exist an overlap. So if there does not exist an overlap, there is no need for removal. So we don't need to remove at anything. So we are good in this case. This is like the most beautiful thing. The second scenario is that we are given one interval that is clearly bigger compared to the second interval. So essentially we can say that this second interval is actually subset of this given bigger interval. So in this case, things actually becomes pretty easy for us. All we need to do is that we simply need to remove the bigger interval, because there is a conflict between these two intervals right now, which we can see, but there could be possibility that there might exist some other interval, something like this. So say in this scenario, if we got rid of this interval, we still have to we will still find ourselves to be having conflict between these two intervals, and again in order to resolve that we will have to remove this one as well. But rather doing this, suppose in this scenario we only had two intervals like this, and originally if we just got rid of this bigger interval, then immediately, even though there exists another interval somewhere down which was actually causing an overlap between this original interval, still we will have to perform less remove operations. So that is why the strategy should be that always remove the bigger interval. Now the question comes in scenario like this, where the starting point of one interval is actually falling before and the starting point of second interval actually falls somewhere in between. So what should be our approach in this scenario? And in this scenario as well, what I'm suggesting is that we remove the interval that has the longer end point. Essentially, if we at any point identifies ourselves in this kind of scenario, our strategy should be to remove the interval with the end point that is greater. So suppose we consider that the starting point for this interval is actually 1 2 3, and suppose we consider that starting point for this interval is 2 to 4. So in this scenario, the strategy we are going to use is that we are always going to remove the interval 2 to 4. Why? Because we are going to compare the end values, and whichever interval has the greater end value, we will decide to remove that particular interval. So essentially we are using a greedy approach. But by using this greedy approach, what we are going to do is that over here we know that for this particular case, for this particular interval, we only had an interval that was causing an overlap over here. But again, the same thing could happen, that we might have another interval like this, where this particular interval was causing an overlap between this and also this. So immediately remember, our input is sorted, so we are coming from left to right inside the number sequence. So the moment we identify that whatever has the greater end point, if we decide to remove that, so even over here we already got rid of this one. So even over here, if there exists another interval that comes after this 1 2 3, still it would not be in overlap with this 1 2 3, and we will have to do less remove operation. And this would be our ideal approach. If we calculate the time and space complexity, basically the time complexity in this case is going to be big O of n log n. And why n log n? Essentially, doing this interval, converting this interval from normal input to sorted input takes n log n time. And then after that, once we have this input given, essentially all we need to do is just we have to iterate over the given input once, because it is already sorted, and then we can perform the remove operation and we can count the number of times we removed any interval. So that this second part takes big O of n time. So total work we are doing is actually big O of n log n plus big O of n, but in general we can write this as big O of n log n. And in terms of space complexity, we are not using anything extra, so we can just say that it's a constant time space complexity. At most we are just going to use couple of extra variables. So first of all, we are going to check that if the given intervals is empty, so we are going to return 0. Okay, if that's not the case, we will have to sort the given input, and we are going to sort the given input based on the starting values. Okay, after the sorting, we are going to initialize couple of variables. So we are going to keep a variable called previous to keep track of the previous element, and we will initialize it to 0. We are also going to have a variable called count to keep track of the number of elements that we will have to remove. So we are also going to initialize it to 0. And now we are going to run a for loop that runs over the given sorted input. And over here we are going to start it as int I is equal to 1, because we already have the previous value as 0 for the comparison. And remember that because the input is sorted, at any given moment we are only comparing two adjacent elements inside the given interval. So first of all, we are going to check that if there exists an overlap between two adjacent elements, and if there exists an overlap, we are going to check that which element is having the greater end value. So we will update the previous counter based on that, and if there exists an overlap, we are going to increase our count. this second if condition dictates that if the previous interval is actually greater than the current interval we are at, we will have to update the previous counter to next element, and in any case we are going to increment our count variable. And if this is not the case, essentially we have found that between two adjacent intervals there does not exist any overlap, so we are going to increase our value of our previous previous variable to the current I, so that we can use it for further implementation. And once we are done with this loop, essentially this count variable should have our answer, so we can simply return the count variable, and this should be our solution. Let's try to run the code. Okay, seems like our solution is working. Let's try to submit the code. Okay, our solution is working as expected, and it's actually pretty efficient in terms of memory usage, and even in terms of time complexity it's not that bad compared to other solutions. I would be posting this in the comments and you can check it out from there. We are not gonna stop till we get into FAANG, and see you next time.
Okay, now let's just quickly go through this remove interval problem. This is a LeetCode 1272 number problem, and this is actually a LeetCode premium problem. So that is why I decided to solve this problem, because I know not many people can afford the LeetCode premium subscription, and since I already have it, I want to make the most use out of it. This is a LeetCode medium problem, and in this problem, basically if you want you can read this whole statement, but I'm just going to explain you that what it is asking us to solve. We are simply given an array of intervals that defines some intervals that we are already given, and these are already non-overlapping intervals. That is good in our favor. We are also given a new interval that we need to remove, which means if we remove this new interval, all the intervals that it overlaps, they needs to be removed from this original input list, and then we only need to return a new list of arrays or new array list that contains all the intervals that are not part of this to be removed part, and that is the answer we need to return. So let's just try to understand this with an example. Suppose again, just like this, we are given an interval that looks like this, and let's just give values 1 3 and then 5 7 and then 9 11. Okay, and then we are being asked to remove an interval that looks like this. This one, the value is 2 2, let's just say 6. Okay, this is what we need to remove, which means we can still keep this portion, but we cannot keep this portion. This we will have to get rid of, and even until this portion everything needs to be getting rid of, but this portion we can still keep. So the answer in this case is going to be that first we will have an interval bit that is 1 to 2, then we won't have any interval until the value 6, but after the value 6 there exists an interval between values 6 and 7. So again, between 6 to 7 there is going to be a new interval, and then this 9 to 11 is going to left untouched because it was not part of this 6 to 11. So what the simplest solution we can do is, and in my opinion this should have been a LeetCode easy problem, not medium problem, but anyways, LeetCode has their own ways to decide. What we can simply do is, whenever we are given an input and we are also given the interval we are trying to remove, so if we just take a look at the same example again, basically what we can do is that simply we can check for every single interval that we iterate over to see whether it conflicts with this new interval that we are trying to get rid of. So in the first place we check, okay, this value is 1 2 3, and the value that we are trying to get rid of starts at value number 3, which means that there exists an overlap between these two intervals. So because there exists an overlap, we will have to do something, and what we are going to do is we are only going to pick the values between this 1 and 2. So between these two starting values we are going to create a new interval and store it in our answer. So 1 to 2 is going to be the new interval. Then this part we don't care. Okay, now we are on the next interval. Again, for the next interval we are going to check that does its ending value is greater than the ending value of the part we are trying to remove. If that is the case, which means there is a possibility that this interval will have some value that we can add in the answer. Suppose over here, if we had one more interval that looks like this, okay, I'm just giving you an example, then this interval has to be removed completely because both of their starting and ending value falls between these two portions. So then we can't do anything in this case, which means that this interval is no use for us, so we will simply skip to the next one. But in this case, since this interval already has a value that is greater than the ending value of the part we are trying to get rid of, so then the value difference between the part we are trying to get rid of and the ending of this current variable, so that is 6 to 7, that would be stored in our answer. So 6 and 7 would be stored, and then all the other values, so in this case 9 and 11, will be left untouched and we can add it to the answer. And this is the whole solution. Now if we see time complexity, in this case the time complexity is simply going to be big O of n, because we might have to iterate over every single value inside the given input. And in terms of space complexity, well, this is debatable. You can argue with your interviewer, since in this case we are explicitly told to create a new list and return that. We are just simply creating a new array list and then we are adding all the solutions to that. So in this case we can mark the space complexity as constant. But if we are not being asked and still you are using a new array list, then it could be considered as big O of n. So you can discuss with your interviewer on how you want to treat the space complexity as. And this is the whole solution. Now let's move. I'll just show you the coding part for this remove interval problem. Okay, so for the coding solution for this remove interval part, this is the input we are given. Basically we are given the set of intervals and we are also given a new interval that needs to be removed. First we are going to initialize a new list where we are going to store the result that does not contain any interval that is to be removed. Then we are going to iterate over the given input of intervals. First, we are going to check that if we find all the intervals that does not have any sort of overlap before this to be removed and after this to be removed, we can simply add it to our this new result list we created as it is. No issues with that. However, if we find that there exists an overlap, in that case, we will have to pick the smaller portion. So between the starting values, we are going to pick we are going to create a new interval that is made out of the beginning values of these two interval values. And even for the ending portion, we are again going to repeat the same process that to find the interval that is made out of the two ending values difference, nothing more than that. And after that, after this loop ends, basically we would have our result populated inside this new list we have created, and we can simply return that. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty efficiently in terms of time and space complexity. So you can see how interval problems are behaving. I just showed you this solution because I haven't solved this before, and I just thought that you at least get some idea on how these interval items are being done.
Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do a lead code premium problem, and you can clearly see that this has been one of the most popular lead code premium problems. This has been asked in companies like Amazon, Facebook, Google, Bloomberg, Microsoft, Oracle, Walmart, Uber, Twitter, Apple, Goldman Sachs, TikTok, and ByteDance, and also some other companies like eBay, Adobe, Swiggy. They all have also asked this question fairly recently. So my aim, you all know that I want to get a job at any top tier FAANG company, and that's why I'm making these videos. So I'm paying my utmost attention, and I hope you also enjoy the video. Lead code medium problem, and it is one of the most popular problems on lead code if you see the like to dislike ratio. Also, the name is meeting rooms 2, so basically it is the next version of the original problem meeting rooms that I have already solved over here, so you can check it out from there. Now in this given problem, we are basically given an array of meeting times called intervals, and we are given a start value and an end value, and obviously start value is always going to come before the end value, like as it should be. Now we need to say that based on the given number of meetings, how many number of minimum conference rooms we are required so that all the meetings can be accommodated. And we know that for any single meeting we need at least one conference room, and when that meeting ends, that conference room can be used for some other meeting. So suppose say for example we have a meeting that starts at 5 and ends at 15 minutes, and we have another meeting that starts at, let's say, 17 minutes and ends at 27 minutes, something like that. So in this case, if we only have one conference room, we are still good. Why? Because first of all, this meeting will take place, all the attendees will attend this meeting at 15, this meeting is going to end, and then they are going to leave away from this meeting, and then these new people are going to attend the meeting in the same conference room. So in this case, we can clearly determine that, okay, with one conference room, we are sufficient to complete all the meetings. Now, but problem comes when, say for example, we have a meeting that starts at 0 and ends at 30 minutes. I'm using this original example that is given. So suppose we have a meeting that starts at 0 minute and ends at 30 minutes. We have another meeting that, let's say, starts at 5 minutes and ends at 10 minutes. And we have another meeting that, let's say, starts at 15 minutes and end at 20 minutes. So something like that. So essentially over here, we are having 3 different meetings. And now for these 3 meetings, how many minimum number of rooms we need to accommodate all the meetings? So clearly we can see that essentially there exists an overlap between this meeting and this meeting. There also exists an overlap between this meeting and this meeting. So because there exists an overlap, that is causing us to have more than one rooms, because at any given moment, two meetings are happening at the same time, but they cannot be placed in one conference rooms. So now we will have to determine that how many number of conference room we need. Well, we will need, in this case, we will need 2 conference rooms. Why 2 conference rooms? If we look at this start time and end time for all the meetings, initially, let's say we have a conference room like this. So initially this first meeting takes place, which starts at this 0 minute, right? So let's say that, okay, this meeting is being taken place over here. Now, when we reach at this time number 5, we know that another meeting also needs to be started. But this conference room is also already occupied, so we cannot use this conference room. So what we will have to do is we will have to use another conference room, and let me draw it over here. So we will have to use another conference room to accommodate this meeting over here. Now at this time number 5, we started the meeting, but we noticed that at value number 10, we also finished this meeting, which means that now all the folks that attended this meeting, they are actually coming out of the conference room, and now this conference room is empty. But this conference room is still occupied with this original ongoing meeting. So that we will have to take care of. So at value number 10, we already emptied this conference room. But again, we start seeing in this order. So we can find that at time number 15, we still need one more conference room to attend the meeting. So we check, okay, this conference room is already occupied, so we can't do anything. But this conference room is empty because this meeting has already been completed, which means we don't have to worry about it. So this meeting that starts at time number 15 needs to be placed on this second conference room again, and then it ends at minute number 20. So at 20 minutes, all the folks, they empty this conference room. So again, this conference room is now empty. Now there is no one, but this meeting is still going on. And when the clock hits 30 minutes, we can see that, okay, now this particular conference room, the first conference room, is also going to be empty, and folks are going to leave it at time number 30. And this is basically the approach. So at any given moment, the maximum number of conference rooms we were using to accommodate all the meetings were actually 2. So in this case, we will need to return 2 as our answer. The question comes that why we were able to generate this 2, why not some other value, and how do we programmatically solve this problem? Well, the approach is actually quite simple. That over here, what we needed is only 2 things. The first thing we needed is that at any point, what was the start point, what is the end point, and based on the start and end points, we can actually come up with some very interesting results. So if we see over here in this example, what we were doing is that at any given moment, we are iterating over this time sequence, and based on the starting point of the meeting and ending point of the meeting, we are either occupying the room or we are emptying the room. And just by keeping track of those two activities, we can determine that what is the minimum number of rooms that we need in order for us to accommodate all the meetings. Let me show you how. So over here, again keeping up with the same example, so let's say that in this example we already have the start and end times of all of them. So what we can do is we can have two arrays. So first array would be for starting values and second array would be for ending values, and we are going to sort both the arrays based on the timing. So over here the sorting values would be that what are the starting points. Starting points we have over here is 0, 5 and 15. So we have 3 starting points originally, and over here you can see that they are in sorted order, but if you look at the original input we can't see them in sorted order. Like they can be jumbled up or the values can be given in any order, right? So first of all we will sort everything, and then that sorting is going to take big O of n log n time. So that is some activity that we will discuss when we come to the time and space complexity. So initially the sorting position, currently this value is 0, 5 and 15. Okay, let me get rid of this extra space. Okay, now for the ending values are 10, 20 and 30. So again let's sort based on the ending values. So 10, 20 and 30. And now what we are going to do is at any given moment we are going to check both of these arrays, and in amongst these two arrays we are going to see that what is the minimum value amongst either starting value or ending value, and we are going to keep a count or keep a variable called meetings, and we are going to increase the value based on whatever the results we find over here. So let's try to do that. So initially we compare these two values. We see that okay, 0 is minimum amongst these two. So because we are starting a new meeting, which means we will have to occupy a room, and because we have to occupy a room, what we are going to do is we are going to do meeting plus plus. So essentially the value of meeting was originally 0, so we are going to keep the value as 1. Now we are keeping the value as 1. What we are going to do is we are going to iterate over. So this we are keeping at this because this has not been updated in the ending value, but in the starting value the 0 has already been taken care of, so we ignore this case. And now for the starting value we compare this value number 5. So again we compare this value number 5 with this value number 10. We see that okay, the smaller value amongst these two is still the starting point in the starting array, and because we are starting a new meeting, which means that we haven't completed any meeting but we are starting a new meeting. So because we are starting a new meeting, we'll still have to add the value of meeting. So currently the number of conference rooms we will need, we are going to increase it to 2. And by the way, this you can consider as meeting rooms. I just named it meeting just for simplicity. Okay, now again we are done with this 5. So again for the start value we increment, and over here we are still at this position number 10. Again we compare this 15 and 10. So over here we realize that this 10 is actually smaller than 15, which means we are ending a meeting before. So now because we are ending the meeting, so we will jump on this ending array. Now we will come to this place, and because we ended a meeting, which means we will have to subtract the value over here. So what we are going to do is rather than having 2, we will reduce this value back to 1. So now we are at this 15 and 20. So we compare both the values and we realize that okay, this 15 comes first. So we are starting a meeting now. So because we are starting a meeting, will again do plus plus. So now this 1 becomes 2, and we compare this meeting with this answer. So both values are 2, so we don't need to update anything. And that's why over here we are done with this case. So now there is no more place to start the meetings. So actually we can end over here. Why? Because over here the moment we are going to like reach this and this value, all we are going to do is we are simply going to reduce the value of this meeting parameter back to 1 and then again back to 0. So there is no point in us for doing all this work if the starting array has already been dealt with, and this would be our solution. Like this is a very simple solution to understand and easy to come up with, and this is also very optimal and it solves the problem efficiently. So let's see that what would be the time and space complexity. The time complexity in this case is going to be big O of n log n. So this is initially for sorting, as I mentioned earlier, plus big O of n, and this big O of n is to iterate over the start and end array. In general we can write this as big O of n log n only, and now we are done with this one. In terms of space complexity, for the space complexity it would be big O of 2n, because we are storing two arrays, and in the both arrays we are storing some n values. So but in general we can write this as big O of n as well, and this would be the optimal time and space complexity. First of all, we are going to check that if the given array of intervals is empty or not. If it is empty, we are going to return 0. That is not the case. We are going to create two integer arrays, start and end, and for both the arrays we are actually going to fill out all the values in the start array and end array. Once that is done, we are going to iterate over the given input, and from the given intervals we are going to fill out the start and end array. Once this is done, we are going to sort the given start and end array, and once sorting is done, we are going to initialize a couple of pointers. So we are going to name them a start pointer and an end pointer, and we are going to initialize the values as 0, and these pointers are going to be used to iterate over this start and end array. And once these two are done, we are also going to have a variable called result to keep track of the number of meeting rooms that are needed, and we are also going to initialize it to 0. And now we are going to run a loop, but remember that we only need to run a loop until the start array has some values. So we are only going to iterate over the start array, because once start array is done, the result value is always gonna go down. And at any point we are going to check that whether the current start value is actually greater than or equal to the end value or not. If that is the case, we will have to update the end array. And the reason we are doing it is, suppose we are given a couple of arrays like this, that a meeting starts at 0 and ends at 10 minutes, and there is another meeting that starts at 10 and ends at 15. So in this case we can actually use just one room or one conference room to iterate over. Why? Because first meeting has to end first before the second meeting starts. This is a condition that is given, and we are going to use that. Hence, if this is the case, we are going to decrement the number of result that is, and we are going to increment the end pointer. And if that is not the case, so which means that we essentially have a meeting starting before the previous meeting ending, and in that case we will always have to increase the number of rooms needed. So we can simply increase the result, and we will also have to update the starting pointer. And at the end, once this loop is done, we can simply return whatever the result we found. Let's try to run this code. Seems like our solution is working. Let's try to submit this code. And we are actually solving this problem way faster than a lot of other Java solutions, and you can see it over here. So I would be posting this code in the solution in the comments. You can check it out from there.
Hello friends, hope you are having a fantastic day today. So in this section, we are going to do an entire course on backtracking. It is a very popular data structure and algorithm technique that can be used in all sorts of practical applications and tons of interview questions. In this section, we are going to learn that what is backtracking, when to use it, how to use it, what is the typical time and space complexity, what are the benefits, pros and cons of using and not using backtracking, and also how to identify backtracking kind of questions. My expectation is that by the end of this course, you should become a pro in all sorts of backtracking and recursive kind of questions. So without any delay, let's get started. Now let's try to understand that what backtracking is. This is not any particular data structure, but rather this is a very important and very popular technique that we can use in all sorts of different scenarios. Let's say that you are at a current scenario where you are in a new city, and in this new city you are currently located at your home, and you don't have Google Maps at the moment, but you do know that somewhere around your house or around the block there is an ice cream shop that you are trying to find. So what you would do is, you know that currently outside of your home there are two different ways that go in each directions, and amongst these two different ways there are also two different possibilities that you can take in order to find the ice cream shop. And ice cream shop, let's say it lies over here and where you can find the ice cream, but you currently have four different options that you can choose from, where three does not lead to the ice cream. So what would be the logical step you would take? You would first of all start your iteration from your home, and you will pick any random guess. You know that at most you will have to make four different check out four different shops on four different places. So let's say that you decide to go down this path. Now once again at this path, once again you encounter two different possibilities. So once again, let's say that you decide to go down this path. Now going down this path, you realize that this is not an ice cream shop. So if this is not the ice cream shop, what should be your most immediate measure? So logical step would be to just do a backtrack operation back to the very previous point where you encountered the last possibility of different items that you could have explored, and once again explore those items as well. Once again, after exploring this, you realize that this is also not an ice cream shop. So once again you will go back, and after going back you notice that at this juncture you explored all the possibilities. So now once again you will go back to a point where you had some possibilities left. Now let's say that you come back to this moment, and once again you go back over here. Once again you have two possibilities. You coincidentally chooses this one, and this one turns out to be the ice cream shop, and you just found your ice cream. So that is awesome. Now what we did in all of these different jumps that we were taking on, these were actually the backtracking operations that we were doing. And what was our logic? It was quite straightforward, that whenever we are heading out and whenever we have to make any particular decision, we would just mark that what decision we took and what decision we are yet to take. We will take one of the decisions. Once again, if we encounter multiple decisions in such manner, we will pick any particular decision, and then let's say we did not find what we are looking for, we will go back to the very previous place where we still had some unexplored items that we did not take a look at, try to explore those possibilities, and then if we still don't find it, once again go back and repeat the same process. So you understood one thing very clearly, that we are actually repeating the same process we did at this point, and once again we would have repeated the same process we did over here, what we did, or if we had some possibility like this on this place as well. So logically we are just playing around with the same procedure with different inputs, and that is a very clear case of recursion. And you understood very correctly that backtracking and recursion go hand in hand. Many times when you are trying to realize that, hey, this is the problem where I'm dealing with a lot of different possibilities and I need to do some stuff differently, in that case you can come up with a backtracking solution that explores all the possibilities and all the subsets, all the permutations, combinations, you name it, whatever you wants to say, all the different paths. And in that case, if you try to think of using recursion to solve the or implement that method, things would become much more sense. And this is the true power of backtracking, where it lies, because you can explore all sorts of different possibilities, no matter how many number of possibilities that you have to check, and you can find the answer you are looking for and keep on iterating with relatively slow amount or slow volume of code. And everything can be done using recursion because you are just repeating the same process for different inputs. So this is the core concept of backtracking. So this is all that is needed to be done. It is a very simple uh, and very popular type of practice that can be used with all sorts of data structures. You can use it with arrays, you can use it with trees, you can use it with graphs, you can use it with strings. You can essentially use backtracking with all the different kinds of data structures that are available, and it would work just perfectly fine. Now let's try to understand that what are the different benefits and what are the different cons of using or limitations of using backtracking. Number one benefit is that whenever you have to explore all the possibilities or all the subsets, all the permutations or everything, every single path that you have to take, backtracking is a really good and very profound tool in order to do this one. Next thing is it is relatively easy to understand and very simple to implement as well. And next thing is that it leads to solution no matter what. So you can guarantee to be finding the solution because you are essentially leaving no stone unturned. So there are some good benefits of using backtracking. The problem is with backtracking solution, typically notice that with at every single moment, let's say that you have two choices to make and you keep on making those two choices, very soon the number of choices you have to make becomes exponentially higher, because at every single location you are updating or increasing in 2 to the power of n type of time complexity. And this can be one of the major drawback of using backtracking solution, because many times you are working with factorial or 2 to the power of n, or maybe like n cube, n square, sometimes of like these kinds of expensive uh, time and space complexities. And that's why you need to be very sure that whenever you are using a backtracking solution, that is like the only way that you are trying to use it. So if you are sure about it, then it becomes a really good and powerful tool. Because many times if the given problem is structured in a different manner, you can also try to think about some greedy approach or maybe some like shortcuts or binary search approach in order to make your backtracking more efficient. So just try to understand this point, because this can come in handy in the future. And now I hope that my explanation made sense to you, that what backtracking is. You also understood that why we need to use backtracking with typically recursion. So the lead code problem we are going to do today is called subsets, and we can see that this one is a medium problem and also a very well-liked problem on lead code. The statement is quite straightforward, that we are given an integer array called nums and we need to return all the possible subsets of this given array. So possible subsets means every single possible values or combination of values you can make out of the given array. So let's say that we are given an input element like this, and we are trying to determine that what are all the possible subsets that we are going to be able to make. So we know that for any given n value we can make 2 to the power n subsets. So in this case we should be able to make 4 different subsets. Let's understand that what these subsets are going to be. So first subset is going to be quite obvious, that is going to be an empty array, nothing more than that. And because that is a subset of this by default, because if we remove both of these values, still we have an empty array which we are able to generate using this. Next way, we can also generate values just 1. Same way we can also generate value just 2, and same way we can also generate value 1 and 2. So logically, using this logic, we should be able to try to understand that what is the way we can approach this question. And what I am suggesting is that this is nothing more than a decision making algorithm, where at every given step you are making the decision on whether you are going to include that element in your answer or you are not going to include that element in your answer. And based on that, you should be able to come up with these 4 answers. So let me try to explain you my approach using this example, and then we will try to understand this for a bunch of different other examples. Let's say that currently we are given these two elements as part of the input. Now in order to generate the very first subset, we have two options. And let's say that we are also iterating over this given input array in this fashion. So the moment we iterate over this input array 1, the very first option we have is that we should we include this 1 in our answer, or should we not include 1 in our answer. So let's generate those subsets. So if we don't include 1, we come up with an empty list. If we decide to include 1, then also we are going to be able to generate a subset like this 1. Same way, next we have the option that after this 1, now the next element in the loop is 2. So once again we have the same option, that whether we should include this 2 in the answer or we should not include this 2 in the answer. So let's say that if we decide to include this 2 in the answer, then we are going to be dealing with values 1 and 2. then once again we still have one more option, that is because remember we are trying to build the subsets, so with every single value we iterate to the next, we are also going to calculate the possibility by removing the previous value. So let's say that we decide to remove this 1 completely, then also we still have one more option, that should we include this value number 2 inside the answer or not. So once again we will have one more subset like this, and then we have reached to the end of our loop, so we don't have any more options. So this logic gives us the correct answer of all the number of subsets that we can make, where what we did is at every given step we check that whether including that value or not including that value would result in some sort of subset, marking those subset in our answer array list we are going to create. And this answer array list is going to be list of list, because it's this array is also going to contain bunch of different array values, and where we are storing the value of every single result that we are calculating. So once again let me try to go and explain this for a broader scenario, the solution I'm proposing, and then it should make you absolutely clear on what is the approach we are suggesting. Basically at every single step we are going to make a decision to whether to include that element or not, and every single answer we generate, it is one of the subsets. So let's say at this very first position we have two options, whether to include one as the part of the answer or not to include one. So let's see both possibilities. If we don't include one, we have an empty list. If we include one, we have one value, that is value number 1. Let's say we decide to go down the path of including value 1. Once again we have two possibilities, whether to include value 2 or whether not to include value 2. If we decide to include value 2, we are going to have 1 and 2. If we don't include value 2 and go to the next element, we are going to have value 1 and 3. And that's it. Now these are all the elements we have, so we won't be able to go any further, but we still have a decision to make, which is over here, that after this 1 2, do we need to include 3 or not include 3. So let's include 3. So that is going to be this decision 1 2 3. If we don't include 3, then it is just 1 and 2. That's it. Now once again, now we took care of all the possibilities with value number 1. Now let's try to work on value number 2. So once again we have the possibility of including 2 or not including 2. We already calculated if we don't include 2, then it is going to be an empty list. So let's include 2 now. So by doing that we are going to have one decision tree like 2. Now at this 2, once again we have two possibilities, include 3 or not to include 3. So let's decide to include 3. Then we are going to have value 1 2 and 3, and that's it. If we don't include 3, we already calculated that possibility over here. And last one is value number 3. So once again for this value number 3 we have two possibilities, whether to include this 1 and 2. We already calculated all of these by including 1 and including 2. If we don't include 1 and 2, then we only have one possibility, that is to have value number 3, and that's it. So these are at every single decision that we are able to generate, we are able to see that what are the values being generated by those decisions, and all of these are actually the answers or the subsets that we need to record, and that's it. This is the crux of the entire problem and the whole solution. So we can see that we are being able to generate in total these 8 values, and these 8 values are actually the answer we are looking for. Now let's try to think about that how did we generated this answer. The logic is quite simple. We do this recursively and using backtracking. And how do we do backtracking and recursively? Let's understand this with, first of all, what is the recursive pattern. So we know for recursion we need two items. First one is a base case and second one is a recursive function. So base case is quite obvious, that whether we have executed all the possibilities or we completed every single elements. So both of these base cases works perfectly fine, because at every step we would be able to generate an answer. So this is our recursive function, that whether we exhausted all the possibilities or we don't have any more elements that we need to traverse over. Now what is the recursive function? It is also quite obvious that as long as any particular elements exist, then once again record both possibilities of including that value and not including that value as part of the answer. After doing that, once again do a recursive call back to the same function in order to check that if you include that value, then also what are the remaining values persisted call back the recursive function with those values. Once again, if you don't include that value, what are all the remaining values persisted, once again do a callback operation, and if there are no other values left, then basically just do a return call. So this recursion would be able to generate the answer. Now why do we need to do a backtracking? And that is also quite obvious, because what we are doing is that we are building a decision tree. So let's say that we are given this values 1, 2 and 3. So once again, we first check all the possibilities for this value number 1. So we check the value number 1, then we check value for 1, 2 and 1, 3, and once again we check for value 1, 2 and 3. And after, at this moment, we will once again have to go back and see that did we miss out any particular element or any particular possibility that we did not check. So far we did not, we checked all the possibility over here, we checked all the possibility over here. Once again we do a rollback, once again we check, did we check all the possibilities? Yes, we did. So once again we do a backtracking and go to the next element and once again repeat the same operation. And that's why backtracking is the backbone of this problem that allows us to solve this problem flawlessly and pretty smoothly. So this is how we are going to be able to use solve this problem using backtracking and recursion, and these two typically go in hand. Whenever you try to solve some problem using backtracking, most likely doing it recursively would make much more sense. We already know what is going to be the time complexity in this case. That is going to be big O of n multiplied by 2 to the power of n, because that is all the possibilities we will have to check. Now let's quickly see the coding solution. So coding solution is quite straightforward. First of all, we have our subsets class where we are receiving a nums as part of the input. Then we are generating a list of array list to store our result, and then we are going to call our recursive method that we have created, that is called generate subsets. Now we are passing in the current index, the starting index, then we are passing in the nums array, and we are also passing in a variable to store our result, and also we are passing in a new array list or the current array list that we are going to be creating, that we would be adding at every single subset iteration. Now let's see our helper method. So first of all, the moment we enter inside our subset, we are first of all going to add whatever the current array list that we have been able to generate it so far as part of our result as a new instance of the array list. And then we are going to have a for loop that is going to simply iterate over every single index position inside our nums array, where we are going to check for the following. First of all, we are going to add the current value as part of the current iteration that we are building, which would be added into the array list or into the result in the next iteration of the recursive call. Then once again, after adding the current value, we are once again going to call the current value as part of the result, as part of the recursive call, and this is our recursive function. And after that, once that is done, we are going to be removing the current element in the next iteration. Why? Because let's say we are dealing with 5 elements, then at every given instance we need to remove one element after we are done iterating every single possibility at that value. So this is that step, and that's it. So by the end of this array, every single value should be populated inside our result array list that we have been able to create it. And at the end of this recursive call is done, we are simply going to return that value. So let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs 100% faster than all the other solutions, and also it is excellent in terms of memory utilization as well. So once again, the solution of this code is available on our GitHub repository, so you can go and check it out from there. Thank you. Now we are going to be solving the problem subsets 2. Now this is very similar to our original subsets problem, but there is a slight difference. Now we can see that this one is a medium problem and also a very well-like problem. The problem statement is that we are once again given an integer array nums that may contain duplicates. So we need to return all the possible subsets. Plus we are told that the set must not contain duplicate subsets. So there is only just one tiny bit of difference. Now let's first understand that what does a different subset means. So let's say that we are given an input array like this, then the number of subsets it can contain is going to be 2 to the power of n. So where n is the given number of elements. So in this case we have 2 elements, so we can expect that 2 to the power 2, which means 4 subsets we should be able to create. And these 4 subsets are going to be an empty list, a subset only containing value number 1, a subset only containing value number 2, and a subset containing value number 1 and 2. That's it. So this is the whole solution. But the thing is, I know we just solved this problem in like our subsets problem, so if you want you can check it out from there. The thing is, in this case, the only difference is that let's say that we are given a value like this, where the input may contain duplicates. Then this changes our equation a bit, because in this case, we need to only return the unique subsets. So in this case, if we want to create the number of subsets, definitely we can create 2 to the power of n subsets. The issue is that we can create a subset, we can create like an empty subset, then we can create a subset with just one. But once again, if we try to create a subset with this 2, let's say, then we can also create a subset like this 2. And if we were to put both of these in the answer, then there would be duplicated entries. So we only need to just pick one. So that is number one thing. There can be one more duplicate in this case, and that duplicate could be that we can create a subset like this, value 1 and 2, and we can also create a subset like this where value is 1 and 2. So if such kind of situation occurs, then we need to take care of that scenario. So basically making sure that whenever we have duplicated entries, we just have to keep them aside or not consider them for the current part of the subsets. Now we all know that what was the strategy we used in order to calculate the subsets. Let's say that we only have just 2 values given and we are trying to generate the subsets. Logic is quite straightforward. We are going to be using the backtracking. On top of it, we are going to be using recursion. Now what is going to be logic for our backtracking? That while after calculating every single path for every possible subset, then we are going to be doing a backtracking and once again repeating the same operation. What do I mean by that? Let me just explain. So first of all, we are at the empty list position. Now over here we have the possibility to include this value 1 or not to include this value 1. Same way we have the possibility to include this value 2 or not to include this value 2. Let's say that we decide that we are not going to include both of these 1 and 2. So in this case, we can create a subset like this, like an empty list, and we will mark this as part of the answer. So let's say that this blue line indicates that we already marked it as the answer. Now, once again, after marking this answer, we still somehow needs to go back and revert our operation. So in the previous choice, we decided that we are not going to select this value number 1, but now let's say that we do decide to go ahead to select this value number 1. So once again, we can create a subset where we are only selecting the value number 1. So once again, this is also part of the answer. So I'm marking it with a blue line. But after doing this, once again, we will have to do a backtrack and see all the possibility. So we already exhausted all the possibility of selecting one and not selecting one. But the thing is, we haven't exhausted all the possibility of selecting 2 and not selecting 2 along with this one. So let's say that along with this one, we have the possibility that whether we select 2 or not select 2. So we not selecting 2, we already calculated. But now we are calculating one more possibility where we are selecting 2. So we have values like 1 and 2. Okay. After doing this, we can do a backtrack. We check all the possibility at 1. Once again, we check everything so far. The thing is, we haven't checked the possibility of only considering 2. So once again, we are simply going to be considering 2, and this is going to be our backtracking mechanism. On top of it, this is also going to be our recursive function that I just explained, where for the recursion we need 2 items. We need a base case and we need a recursive function. So for the base case, it's quite straightforward that whenever we create or we make any single decision, we simply add it to the answer, and this is our base case. After this, for the recursion, we go back to the next recursive call with that selected value or not selected value, and once again repeat the same process for the next upcoming remaining elements inside the array. So this already makes sense. We already do this. But the only issue in this case is that we simply don't want to consider, let's say that we are given values 1, 2 and 2. So now in this case, once I'm making the decision, let's say I put down the empty array, then I put down a list with 1, right? Now at this 1, I have two possibilities. First possibility is that I'm going to be considering this 2, and second possibility is I'm not going to be considering this 2. So let's say I decide to consider this 2, then I should be able to create an input array like this, or like a new subset like this. Once again, let's say that I go to and let's, for a simplicity, let's assume that this value is currently 3, okay, not 2. So if this value is 3, then I create one possibility where I'm considering 2. I can also create one more possibility where I'm not considering 2, which means there can be a subset like this 1, 3. But in this case, rather than this value being 3, this value is also 2. So it's the same value. So if I try to do this possibility in this case, then I'm just stuck. I'm left with only this value. So what I can simply do is that I can take the given input. Let's say the given input array is like this, but it right now it is already sorted, but it is possible that this may not be sorted. We could have given values like this. So once again, if we want to do the solution, what I'm suggesting is that whatever values we are given, we simply sort those values. So let's say we get a nice looking values like this. After sorting, all we simply do is we check that at any given moment, whenever we calculated a possibility with this 2, now we are trying to calculate another possibility. We just check that the current element we are considering for the possibility, if that element is same as the previous element, then we just don't consider that possibility. That's it. This is the whole solution. So now what would happen in this case? We will have an empty list. We will have value with 1. Now we will have one more subset with 1, 2. Now after this 1, 2, we still have two possibility whether to include this 2 or not to include 2. So let's say that we decide to include 2. So then we still have one more subset like this. So we also consider that. After this one, we are doing our backtracking by removing the last element added. We do the backtrack. We don't need to calculate this one because we already know that it's the same element. We go back to 1. We check all the possibilities with this 1. So now we are at this position number 2. So we decide to include 2 only. This is a new subset. We add it to the answer. Now after at this 2, we have the option that whether do we need to add this value or not to add this value. So this value is quite straightforward. It's 2, 2. It's a new subset. So we haven't calculated that. So we can simply add this one. Now after calculating this, once again we do a backtrack. Now at this backtracking location, now our time is to move to the next element and not consider this one. But once again, while making a decision for this one, we check that whether it matches the previous element. Yes, it matches the previous element. If it matches the previous element, what is the point of considering this for the subset? So we are not going to do that. And that's it. This is the whole solution. And if you see the coded approach, it would make much more sense. Plus you already know that how does the calculating subsets work, because we already saw that in the past, that the whole explanation and the whole 9 yards. I just re-explained the whole thing, and I also explained that why we are adding this tiny logic to our already beautiful solution. Now let's quickly see the coding approach. So very first thing we are doing is creating a new array list where we are going to be storing the results. Then we are simply sorting the given input array. And then we are calling our backtrack recursive helper method where we are passing in the new result where we are going to be storing the array list of lists, and we are passing in the new instance of the array list to store the current list that we are iterating over. Then we are going to be passing in the given input nums, and we are also going to be passing in the starting index where we are looking at. So initially we are starting from the index 0. So we are just going to pass in 0. Now let's see our helper recursive method. First thing we are doing is whatever value we have in the current list, we are adding it into the answer. So during the very first call, we are adding just an empty list into the answer as well. Next, we are running a for loop from the start to the end of the given array. Plus, we are just checking for a very simple condition that if the given input I is greater than start and the current element is equal to the previous element, if this is the case, we simply continue. If this is not the case, then we simply add the value to our current array list, Then once again we call our recursive function. After the call comes back from the recursive function, we remove the very last element added inside the current array list, and then we repeat the same process until we are done with the entire for loop. And this should populate our results completely. So now let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs beautifully, faster than all the other solutions, and also best in terms of space complexity. So once again, the solution is present at our GitHub repository, so feel free to go ahead and check it out. Till then, thank you. Now the lead code problem we are going to solve is called permutations, and we can see that this one is a medium problem and also an extremely well-liked problem. The statement is quite straightforward, that we are given an integer array called nums of distinct integers, and we need to return all the possible permutations that we can make. And for good thing for us is that we can return answer in any order. So first let's try to understand this with few examples. Let's say that in the input we are only given one element, then we can only generate just one permutation. So this is what we need to return. But if we are given more than one element, let's say 1 and 2, then we can actually generate two permutations in this case. First permutation is going to be the same value as it is. In the second permutation, we are going to have the values being flipped around between 2 and 1. So these two are the permutations that we need to return. Let's take one more example. Suppose in the input we are given the values 1, 2 and 3. Then we can basically calculate that we should be able to make 6 permutations in this case. Why? Because for any particular given numbers, you can make n factorial permutation. So in this case we are given 3 elements, so 3 elements is going to be 1 multiplied by 2 multiplied by 3, as in 3 factorial. So in this case the answer is going to be 6. Now let's see that what are all these 6 elements are going to be. Well, so these are all the 6 permutations we can make. Now logically this is nothing more than a decision making element or decision making algorithm, because over here we can see that if we have to make permutation of this element, let's say that I have 3 blocks where I can fill in values. Now let's say for some reason I decide to put 3 in the first block. Then I know that I still have 2 values where I need to fill out something, but the thing is I can only fill out between this value 1 and 2, not this value 3. So once again I can repeat the same process, and let's say randomly I decide to pick value number 1. So now for this last element I only have just one possibility, and that is to fill in this value number 2. And this, the moment it reaches to the length of this previous one, we can determine that this is one of the permutation that we can store as part of the answer. Now after storing this, we need to check that whether keeping this 3 over here at the beginning, are we leaving out or being done with all the permutations? No, there are still possibility of permutations left. Let's say that we decide to eliminate this value number 2 over here and this value number 1 over here. Now once again, keeping this 3 on this place, once again we have the option that instead of selecting 1, we can actually select 2 over here, then we will have 1 over here, and this would be a new permutation. So visually this is very simple to understand that how does this function, but the thing is implementing this is slightly tricky. So what I'm suggesting is that we actually use the same algorithm that we just saw, but we apply it using the logic and possibility and concept of backtracking. Plus on top of it, after using the backtracking, I also suggest that we use a recursive approach to recursively recall the same function with different inputs. And why am I suggesting this is because number one, we already know that we are repeating the same process. All we are doing it is that the input we are given, we are picking one value in, we are marking that particular value with one of the values, and for that let's say that over here we have 1. So once again now we have two possibilities. First possibility is that on this place, for the second place, we can fill in the value 2 or we can fill in the value 3. Once again, let's say if we decide to fill in value number 2, then we are only left with just one possibility for this last element, that is this value number 3. And this whole path defines one of the permutations. So this we will be able to mark as the answer, and then if we decide to go down this path, once again the values are going to be 1, 3 and 2. So this is going to be our second permutations, and once again we can mark this answer as well. So now let's say that what are the things we need to solve this problem and how we are actually going to be doing that. I just explained that we are going to be using backtracking plus recursion. So let's say that what do we need for our backtracking function? The idea is quite straightforward, that we will keep on going in one direction until we reach to the length of the given input. Once we reach to the length of the given input, we will mark that entire path in as part of the one of the answers, and we would put it into our list of lists that we have created to store our answers or results. Once doing that, the idea is to once again do a backtrack, and after doing the backtrack, once again see that what is the potentially different path that we could have taken, and once again once we reach to the answer, we basically store that answer. Now there are two critical parts in this case that we will have to consider. Number one thing is that we will need to know at some point that what are the values we have already calculated and what are the values we have not calculated so far. So what I'm suggesting is that let's say you decide to put 1 over here, then I would need some sort of way for my computer to tell me that this 1 is already part of the function. So for that I'm suggesting to use a used array, or like array named use, and the moment we add any particular value inside the current consideration for our recursive function, we are going to mark this used function as true or false. So this would be my used array of boolean values, and currently I would mark that this is true, which means I'm currently considering 1. Then once again, let's say that now I know that through my used array I only have 2 more possibilities left because this 1 has already been filled. So for the next element, I'm going to consider this value number 2, and once again I'm going to mark this value 2 as being used as one of the decisions. After doing that, once again I'm going to mark this value 3, and then I'm going to mark this 3 as being used. But the thing is, because I reached to the end of the list, so the moment I reach to the end of the list, I can mark this answer 1, 2 and 3. And after marking this answer, I can actually go back, and I can go back in time with my recursive function and say that over here, instead of using 2, now I have decided to take another path where I'm going to be considering 3 as part of the input. And in order to do this one, I will need to constantly update this used array. That is number one thing. Second thing is, in order to calculate this path, I will also need to have a current array or array list to store this path as well, that these are the values we are currently iterating. And the moment we identify that we have reached a new answer, then for the next iteration of the recursive call, I simply need to regenerate the entirely new array. So I know my solution might confuse you a bit, but let me just give you this with like using 2 examples. So let's first quickly take the example of simple 1 and 2 values. Okay, the logic is that we are going to have a recursive function that is going to store. So for the recursive function, I did not explain, but basically for the recursive function, we need 2 items. So we need a base case, and we need that what is going to be our recursive call. Base case is quite straightforward, that the moment we identify that our given current n or the current length of the given input is equal to the original n of nums, then we have found the correct path. In this case, we would mark the current path inside the answer, and after marking that, we would basically return. So this is going to be our base case. Now for our recursive function, the idea is quite straightforward, that we are going to pick one element right now, and through that one element we are going to be marking the used array for that particular element to be true, and then we are going to call the recursive function once again with the remaining portion, because we still haven't identified all the values. Once we identify all the possibilities and we receive an answer back, then we are going to eliminate the last element we had inside our recursive function to be turned out to be false, and keep on repeating that in order to calculate other possibilities. So let's first see for this example. The idea is that first of all over here I have 2 possibility. Let's say I mark number 1 element as being used, and I have a current list where I'm going to store that what is the current path I'm taking. Okay, I took 1. Now I'm once again going to call for the next element. So now I call for the next element, that is obvious choice 2. So I mark 2, and now I know that my length of this current has reached to the n. So I'm going to mark this as part of the answer 1 and 2. After doing this, once again I'm going to do a backtrack call. During the backtrack call, I'm going to mark this 1 as not being used and 2 as not being used, and then I'm going to be iterating over this given input in this fashion. So I already took care of this element, and now I'm going to start taking care of this element. So now I have my 2 as being used. Now I have my new current instance being created where I'm starting the path from 2, and I'm going to go down to the next path. So I only have one possibility, that is to add value number 1. So I'm going to add value number 1 over here, mark 1 as being used, and because this n is correct, so once again mark the another answer as 2 1, and now I have my answer that I was looking for. So after this, I realized that in my existing loop, I already be done through all the elements inside the given input. So which means now whatever I have in the answer, I can simply return that. So now if you want, you can directly go to the coding approach if you already understood what I meant. If you didn't understood, then let me also do the same iteration for this path as well, and once again repeat the same procedure. So logic is we are going to be iterating over every single element one by one. That is number one thing. Next thing is we are going to have our current list or the current values we are iterating over, and we are going to have our used array where we are going to be storing that which are the elements we have already used so far in the current iteration, and we are going to be updating the values one by one. So let's say that in the current path I add value number 1, so I'm starting the path from value number 1. After 1, I decide to add value number 2 as an input. So once again I do that, and after this 2, I add value number 3. So the moment I add value number 3, my length is equivalent to so I'm going to store the answer 1 2 3. After storing this, now once again I do a recursive call. So I basically break out, so which means I will have to remove the last element I added. Still keeping 1, I still have one more possibility that I haven't tested. So once again I'm going to mark 3 as being visited. So now I'm going to take one more path, and by the way, this is going to be a new instance where currently the nodes I have visited are 1 and 3, and next time I'm going to be visiting the value 2 because that element is left over here. So once again I'm going to be marking 2, and I'm going to have one more possibility 1 3 and 2. Once again now I do a backtrack. So backtracking would make sure that I took care of 3 over here, I took care of 2 over here, and all of these things are done. So now my used array is being backtracked to all the way to the beginning. So now once again I'm going to repeating the same process, but now this time with value number 2, and keep on doing this recursively until we reach to this very last element 3, where we have all of the 6 possibilities calculated, and this is the whole solution. So now let's quickly see the coding solution, and that would make much more sense. Now first thing we are going to do is that we are going to create a new array list which is going to store our results. So now you can see that this one is an array list that stores different array list inside. Then we are going to initialize our used boolean array in order to keep track of that what are the current elements we have already used. And then we are going to have a helper method called backtrack, where as an input we are providing our result that we have calculated so far. Then we are going to have a new instance of an array list where we are going to be storing the current elements we are iterating over. Next, we are going to be passing in the given input nums, and lastly we are going to be passing in the new used array that we have created. Now first we are going to be checking for the base case, that if the current size is equal to the length of the original given array, then we are going to add the results of the current array list inside the new instance of a new array list, and we are going to be doing a simple return. If that is not the case, then we have our for loop that we need to iterate over. So very first thing we are doing is that we are starting from the 0 and iterating I until we reach to the end of the array. Then we are first of all checking that if the given I value is not used, then we are going to be adding that value inside the current path that we are iterating over. So we added that. Then we are going to be marking that particular element as true inside our used array. And after that, we are going to be calling our backtrack method recursively, where once again, we are simply providing the results that we have calculated so far, the current path, which now contains a newly added element, and the nums input, and the used array that now contains that the current element is being used. And that's it. Basically, this should ensure that all the work gets through, and the moment the list size is correct, then we would start adding those values inside the result. But the thing is, after the backtrack call, we will also have to remove the lastly used elements. So we are going to be doing that, and we are also going to be removing that value, the very last value that we had in our current list. So we are always updating that in order to calculate new possibilities. And this is the whole solution. Now I know it's hard to visualize, but coding is very small, and also you can understand that how to generate it on a pen and paper. So you can just work around with different examples and it would make sense to you. Now let me quickly run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs super fast compared to all the other solutions, which means this is an excellent approach. Now I know using an extra used array might hamper with our space complexity, but this is still a much faster result. So now I will be posting the solution in our GitHub repository, so you can check it out from there. Thank you. Hello friends, hope you are having a fantastic day today. So in this video, we are going to do a very popular lead code problem that is going to be pretty nostalgic for a lot of people. So without any delay, let's get started. The title of this problem is called letter combination of a phone number, and now many of the iPhone users won't know it, but in the past phone actually did used to look like this, where if you have to type any messages, you will need to do it according to the keys that are present over here with the corresponding numbers. And people were so good that they were able to do it without even looking at it. But anyways, now coming back to the question, this is a lead code medium problem and also an extremely well-liked problem on lead code. Also has been asked at tons of popular companies. So let's see that what does the problem statement ask us to do. Basically, we are given a string containing digits from 2 to 9, because notice that in this problem, we are only given the characters from A to Z present between the letters 2 to 9. Now, inclusive. Now we need to return all the possible letter combinations based on the given digit numbers, and that it can be represented. For our convenience, we can return them in any order. So let's try to understand this with a couple of examples. Suppose we are given as an input just character number 4. So how many characters does this character number 4 can represent? Well, only 3 characters. So if we have to return this, the answer is going to be G, H and I as the answer that we need to return. But let's assume that instead of that, we are given the input as like 4 and 6. Then what should be the answer? So we know that 4 can represent G, H and I, and 6 can represent M, N and O. So the answer is going to be the combination of both of this GHI and MNO. So the answer would look something like, where you can see that currently we have 9 entries and they are combination of all the characters from these two entities, and that's what we need to return. So this is the whole problem statement. So let's try to see that what is the approach we can take to solve this problem. Now, number one thing is that currently we are only given characters between 2 to 9 as an input and nothing else. So first thing we need to do is that we will have to create a mapping, so that based on any given input location, we can actually identify that if the character 2 is given, we know that it can only have the possibility of storing ABC. Same way, if character number 9 is given, then it only has the possibility to store 4 characters W, X, Y and Z. And same way, we can store this in any such fashion so that this lookup needs to happen in big O of one time. So we actually have two options to do that. Number one option is that we can actually create a hash map, and inside the hash map we can store all the entities, and based on the key we can mark as the digits, and their subsequent values we can mark all of the entries. So that is option number one. This will yield in big O of one time complexity whenever we have to do the lookup. Second option is, since we know for sure that we are only dealing with characters between 2 to 9, nothing more, we can also create an array, and inside the array, based on the index positions, we can store the values. So let's assume that because in the array we have values like 0, 1 and then 2 and all, or so on and so forth. So for 0 and 1 we can store as an empty strings, because anyways they are not going to be part of our inputs, and starting from position number 2 we can start storing values as A, B, C and stuff like that. Now this is only for our convenience purposes, so that we can quickly look up what element we are trying to find. Now this is the pre-work that needs to be done in the solution so that we can do it in the efficient manner. Now let's see that what is going to be the optimal approach to solve this problem. Suppose as an input we are given the characters 2 and 3 that we need to return. Now we know that 2 is represented by A, B, C and 3 has been represented by D, E, F. That we actually take this given input 2 and 3, then we break this input based on all the digits it currently has. So first we get the digit 2. For digit 2, whatever the characters that it can represent, we create 3 decisions trees based on that. So currently it can represent A, B and C. So we create 3 separate decisions tree. And now, since this is not the answer, because we need to return the combination or the potential combinations that can be there. So this is just a part of the answer that we have created so far. But now we will have to complete the combination portion. So in order to do that, the number one thing we will need to do is to keep track that how many number of characters are currently present, or how many number of digits are present and how many are pending. So now 3 is pending. So we will append 3 with each of these decisions trees, and we know that 3 is currently represented by these 3 values. So once again, for each one of them, we are going to have 3 separate decisions tree being made. Notice that currently at this very first location 2, we only had 1 entry per character inside our representation. But the thing is, in the input we were given 2, 3, 23, which means we were dealing with 2 character letter. But in the problem, we are only at half of the step, where we only have just 2, which means after creating this possibility, we still have to wait to add the values to the answer until we find this path where now the index position matches the total number of inputs that we are given. The moment this condition matches, we will need to add it to our answer list. So because over here we only had 1 characters, but now we had 2 characters, and even in the input we were dealing with 2 characters, we are going to add DA or AD in the answer. Same way AE is going to be part of the answer. Same way AF is going to be part of the answer. And the good thing about this is, because this is same operation being done multiple times, so we can actually keep on doing this. The moment we find out that this is one of the potential pair that we have already added to our answer, we can actually backtrack to see if A still has any more values that it needs to add to the answer. And yes, AE still needs to be added. So we will add AE. Once again, we will backtrack to A, and once again this AF needs to be added. So we will do that. Once again, we would backtrack to 2. Now we have completed all the path with A. So we will repeat the same process with B. And this is the whole answer we need to return. Now I know what I just explained might have confused you a bit. So that's why when we do go into the coding section, I will explain the whole thing in much more clarity. But this is the whole approach. Basically, we are simply using recursion and backtracking to solve this problem, because repeatedly we are doing the same operation. And we know that for this, we need to have an terminating case. So terminating case would be that the moment we identify that one path or one combination contains the same number of characters as the number of input that is given or the index values, then we need to add it to the answer and once again do the backtrack, keep on repeating the same process until we have exhausted all the possibility, and whatever the answer we found, we need to return that. Okay, so what is going to be the time and space complexity in this case? The time complexity is only going to be the number of potential combinations that can be made, which means the number of characters that are given. So let's assume that this currently has 3 times 3, 6 characters. So whatever the value is, so we need to do square of the number of given input for every single digit. So in total, it is going to be the number of combinations that are currently present. That is going to be the time complexity. For the space complexity, because we will have to create another array that contains all the mapping from the characters 2 to 9, we will have to store that. but that is going to be limited in scope. So instead of calling this as big O of n, we can actually treat it as big O of 1 because the space complexity is not going to change. So now let's see the coding solution. Okay, so first of all, we are going to initialize our string array where we are going to mark first couple of entries as blank, and then we are going to mark all the values. So this is going to allow us to iterate over all the digits to the letters. And then let's start our code actually for the problem statement for this method letter combination, where we need to return a list of strings as the answer. So first we are going to initialize a combination string that we are going to return as the answer, and this is going to be the blank array list so far. Now first we are going to check for an edge case that if the given number of digits is equal to null or digit.length is equal to 0, then we simply need to return combinations. If that is not the case, we are going to call our backtrack method, and we are number one thing, we are passing this list that we have created. We are also passing the input digits that we have received. We are passing an empty string that is going to be considered as the current combination that we have so far, and we are passing in 0 as the current index values that we have processed so far. Okay, now let's see this backtrack method. How does it work? So number one thing we are checking is that if this given current index location, if that is equal to the digit length, which means we have an answer that we need to add to our current combination. So we are going to add all the answer that we have found in the current combination to our combinations array list that we have created. If that is not the case, we are first of all going to differentiate the letters for every single index position. So let's say in the input we are given value number 2, then we would have ABC as the letters passed on, and then we are going to run a for loop across every single letter. But now this time we are recursively going to call back the method backtrack. We are passing in the same combination, same digits, but for the current combination, we have added the current combination plus the current letter we are working on. On top of it, we have also updated the number of increased value, index value. So if in the previous iteration, if we would have passed in value number 2, in the next iteration, we would have passed in value number 3. And that's how we will be able to start storing all the combinations in the current combination array string that we have created. And this is it. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty efficiently compared to a lot of other solutions, which is awesome. By the way, you can always find this coding solution in the GitHub repository we have, and the link is in the description, so you can check it out from there. Thank you.
Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code problem, and I have provided the introduction of what are the things to expect from this video. We are going to solve the combination sum problem, and first of all I'll be showing that what are the top companies that have recently asked this question from Lead Code Premium. We'll understand the problem statement. We'll also find the optimal solution, and we will also determine that what would be the intuition behind it. We will create an example and we'll walk through it, and at the end I'm going to write a Java code. I'm going to explain it thoroughly, that how we come up to it, and also we would be explaining the time and space complexity. So first of all, these are the top companies that have asked this problem recently, and if we see from past 6 months to a year, it's eBay, Google, Goldman Sachs, and these companies. And pretty recently, Amazon has asked this question 20 times in its interviews. Facebook has asked this question 18 times in its interviews. So I highly suggest you to take a look at this problem, understand it completely, and then practice it as much as you can. This is a medium problem, and we are given a distinct integer called candidates, and we are also given a target integer, and we need to return all the unique combinations of candidates where we can reach up to the target value. Now this is a little bit tricky part to find all the unique combinations for this target candidate, because let's try to understand this with an example. So over here we are given the candidates as 2, 3, 6 and 7, and we need to reach the value number 7. So we can clearly see that 7 is already present over here, so we can return this one. The thing is, we need to return all the unique combinations. So one unique combination is 7, second unique combination, and also one more thing, we can use the same number from the candidate unlimited times. So if we apply this theory, then we can find another value that can reach to the sum of 7, and that would be 2 plus 2 plus 3. If we do that, this also sums up to 7. So we need to return a list where the two values are 2, 2 and 3, and the second element is just 7. And this would be our solution for this given problem. Okay, let's try to understand this problem with a custom example. And it is really important to create your own custom examples because it shows that you have the ability to think outside of the box, and you can create test cases on your own. It is a really important skill to have for any engineer, and especially FAANG engineers. So we are given 3 candidates, 2, 5 and 6, and we need to see that what are all the combinations we can get out of these candidates to achieve the target value 8. Now just by looking at it, we know that the two combinations we can create is 2, 2, 2, 2. This is one combination, and the second combination we can create is 2, 6, and this would be our answer. The thing is, let's see that what would be the most basic solution we can come up with, and what would be the intuition behind it. And based on that, we would be able to create an algorithm that would solve this problem. So initially we are at this position 0. Now at this position 0, we have 3 possibilities from which direction we can go. We can either go to this value number 2, we can go to the value number 5, or we can go to the value number 6, because these are the 3 candidates that we are given. And also we should not forget that the target value we want to achieve is 8. Okay, so keeping this in mind, we need to go and pick a side where we need to go further and keep going. So again, let's just go on one direction for all the cases we can. So over here we are at 2. Now remember that we can use same element infinite times, which means that there can be one possibility as 2, 2. Of course, there can also be one possibility as 2, 2, 2. Of course, the thing is, notice that we need to put a constraint for the number of decisions we are making, and the constraint is that if at any point the direction where we are fetching all the candidates, if the sum of those can either be less than target, they can either be equal to target, or they can be greater than target. These are the 3 possibilities we can have. If it is less than target, which means that there is still room for us to find the potential combination, which means we can keep further going on that direction. If we are already at value number 8 or whatever target we are, we can directly put this value in the result. But if we and which means that we have found the combination, so there is no point in going further after we have already found the combination, because all the elements, they are only going to add up to whatever combination we have, which means that we won't be able to find another combination with the same numbers that were used to achieve this equal to. And the third option is that the value could be greater than 8. If it is greater than 8, why are we keep on going or to do more iterations and putting more strain in our computer? There is no point in doing it, because we could have infinite options, and if we do it, this would be like the best way to deplete the resources of our company. So we don't want to do that. So now, since we have kept these things in our mind, now let's see that how can we use them over here. So far the sum we have found up until this point is only 2. But the thing is, over here we have 2 candidates, and the sum we have found so far is 4, which is still less than 8. This is 6, again still less than 8. Now over here we can have one more possibility as 2, 2, 2 and 2. And if we do the sum of this is 8, which means that this is actually equal to whatever the target value we had. So we can add this to our result combination. We would have that we have already find one value in our result, and we will just add it as 2, 2, 2, 2. This is one combination that we have found so far. The thing is, we are not done yet, because we still have other candidates that we need to look at, and we need to check the possibilities. But the thing is, we have concluded at least one thing so far, and that thing is we can't go further down on this path because all the values would be greater than 8, and which is not what we want. So the only way we can go is actually we can go back and see that have we missed out on any combination. So over here, the next possibility we can get is we have already used 2 as our candidate for this value 2 2 2. So the next possibility we can have over here is it could be 2 2 2 and 5, or it can be 2 2 2 and 6. So let's do sum of all the combinations. So some of these combinations would be 11, and some of these combinations would be 12. Notice that both are actually greater than the value of our target, which means that we can't go further down at any of these positions, and we have exhausted all the possibilities up until this point. So since we have already exhausted the possibilities up until this point, the only way we can go is we can go back. At this position 2, we have exhausted all the possibilities there can have. One, we found the answer, and the other two we found that it cannot be part of the combination, which means that we have already exhausted all the possibilities for this value 2 to 2 as well, which means that we can't go down, but we can go up. So over here, have we exhausted all the possibilities so far? No, there are still room, there are still other possibilities that we can check. So let's do that. So one possibility we can have over here is 2 2 2, which we already checked. The next possibility could be 2 2 5, and the next possibility would be 2 2 6. So sum of these values is actually 9, and sum of these values is actually 10. Again, both are greater than whatever the target value we had, which means that we cannot go down. So we will go back. We went back. Over here we check that we went through all the possibilities, which means that we are done over here. So we can't go down any further on this path, but we can go up. So if we go up, we ask ourselves a question that have we explored all the possibilities at this position? No. The possibilities we could have is 2 5 2 6. So let's take this value first. So at 2 5, the current sum we have is 7. 7 is less than whatever value we have as our target, which means that we still have possibilities. The possibilities we can have is 2 5 5 or 2 5 6. Notice that over here we only had two possibilities where we can calculate it from. We did not had the possibility of 2 2 5. Why? Because we already calculated it for this portion over here. Remember, in the previous iteration we already calculated for this scenario, which also shows one very important property, and their property is that out of our candidates, whatever the candidates we are given, if we are at any particular position or any combination of positions, so whatever value we have as last, we can only use that multiple times, or we can use the values that come after it. We cannot go backwards because we have already exhausted those possibilities in an iteration before this, as I showed you earlier, that this we have already explored over here, and this 2 to the 2 5 we are exploring at this position 2, which means that the only combinations we can make up after this point is either 2 5 5 5 something blah blah blah, or 2 5 6 6 6 something like this, but we can't make like 2 2 2 5 because we already checked that over here. So, and this is a very important property that we are going to use. Okay, at this point the sum we can have is 12, which is greater than 8, so we can terminate over here. We can't go down any further, and over here the sum would be 13. Again, we can terminate over here. We can't go down, which means we have to go back. So we come back at 2 5. We say that okay, we have explored all the possibilities over here. We go back to value number 2. Now the thing is, at value number 2, have we explored all the possibilities? No, there is still one possibility pending, which is 2 6. So at 2 6, this value, the sum would be 8. Again, this is really critical because we have found a pair that equals to whatever target value we had, which means that we will add this combination to our result list. So over here we will add another entry 2 6, and after adding this we have explored all the possibilities after this point, which means that we would go back. Now at this position 2 we have explored all the possibilities it could have, and because we have explored it, we will again go back to our 0th position. The thing is, we are still at 0th position, so can we stop now? No, we can't stop because we still have a whole lot of possibilities that we haven't touched so far. Because remember, over here we still have this 5 and 6 pending. So let's see that what could be the possibilities over here. Now at 5, again we can only have two possibilities. As explained earlier, we could have either 5 5 or we could have 5 6. So let's do the sum of these values. So 5 5, the sum is actually 10, and 5 6, the sum is 11. Both are greater than 8, which means that we can terminate over here. So that concludes that at this position 5 we ran out of the possibilities. We went up. At this position we are done. So again we go back. We go back at 0th position. We check that do we have any other options where we can explore, and yes, currently we are at value number 6. So 6 is again less than our target 8, so we can go further from 6. The thing is, at 6 we can only do 6 6. We can't do any other combination because those we have already checked so far, which means that 6 6, the value is 12. So 12 is already greater than 8, which means that we can't go further from this, which means we can't go further. We go back. At 6 we see that have we explored all the possibilities? Yes, we have explored all the possibilities, which means again we go back to this position 0. So at this position 0 we check that now have we explored all the possibilities? Yes, initially we check all the possibilities for the value 2, again we check for value 5, and again we check for value number 6, which means that even at 0th position we are done. So our base case has satisfied. Now whatever we have stored in our result result list so far, we can simply return this, and this would be our final solution. And this is actually the optimal solution that we can achieve. Notice over here that we are doing lot of repetitive work. At any position we were calculating the different possibilities we can have. We are picking a possibility, we are exploring in that direction, depth first search. We kept on exploring. Once we found a terminating case, we would go back to a point where we can still explore for more possibilities. Over here again we would further go down to additional possibilities. We would find a terminating case, again we would come back, and eventually we would come back to the 0th position from where we started, and after the calculation we will return our result. So this, where at any point we are coming back from where we originally started. This is actually called backtracking. This is a really important concept in computer programming, and I just showed you that how can we use it, and that is why, because this concept is really important, it has lot of very practical applications, and that's why you see that why all those big companies like Google, Facebook, Amazon, Goldman Sachs, they were interested in asking this question to their candidates, because they want to know that are you familiarized with very important things that are really critical, and can you go down that path. And yeah, so since we have found our optimal solution, I did not mention explicitly that I was showing you the optimal solution, but the thing is, I told you that this is the intuition behind it, and once we knew the intuition, we just need to find a way to implement it in computer programming. The way to implement this, you must have guessed it correctly, that we were doing so much repetitive work again and again, and we were using it somewhere, and we had some terminating conditions that either if the value is equal to or greater than our target, we would terminate. which means that we were using recursion at its best over here. So yeah, this is basically our solution. So let's calculate the time and space complexity. That time complexity for this one would be big O of n to the power t. Now first let's determine that what this n and t means. N is actually the number of candidates and the least value for this one, and t is actually the total amount. Because imagine that what could be the longest sequence we can have at any given position. Well, suppose our target value is 8 and our candidate is 1, which means that we would do 1 plus 1 plus 1 up until 8 times till we get the value 8, which means that we need to go in one direction 8 times, and at any position we can have multiple options or we can make multiple decisions, and from further down we can go ahead, which means that we need to do this work n to the power t times until we find the solution. So that's why this is the time complexity. So first of all, we'll create our result list, and now we'll create a list to store the current combination. Okay, now we'll create a backtrack method, and in this would be our recursive method. So initially we are going to provide the target result combination 0 as the starting point and the candidates array, and after whatever the result we get back from that recursive call, we simply need to return whatever we find in this result list. So let's create the recursion method. Okay, so first of all we are going to create the terminating cases. So if target is equal to 0, which means that we have find a combination that sums up to the target value, so we can just simply return it to we can simply add the combination to our result. If this is not the case, we need to return we need to check that whether the target is less than 0, which means that we have already surpassed our target and we need to break, so we can just return null. If both cases are not true, which means we still need to look for our combination. So we'll start by checking in our combination from the position start, and we'll go until we still have candidates. Now inside the loop, first of all we will add whatever candidate we are currently looking for in our combination list. Okay, after that we can do our recursive call, and as a target we will have target minus whatever candidate value we found. And start would be ith position, and I think that would be it. Yeah, one more thing, we will have to remove the entry from our combination list because we will be doing backtracking when we move towards the next value. And I think this would be it. Let's try to run the code. This should have worked, but I don't know why it's not working. So we'll just enter the value manually. Oh, it should be candidates. Okay, our solution seems to be working. Let's try to submit the code. And yeah, our solution works perfectly fine. And I would be posting this code in the comments. You can check it out from there.
Now we are going to be doing an awesome lead code problem that is called combination sum 2. This is the subsequent question to our original combination sum problem with some slight tweaks. Now we can see that this one is a lead code medium problem, but in my opinion this can be categorized as hard problem sometimes as well, because combination sum in itself is slightly tricky to understand. And we can see that this one is a very popular lead code problem, also being asked at tons of companies. Basically we are given a collection of numbers called candidates and we are given a target number. Now we need to find all the unique combinations in the given input array such that the sum of those values is equivalent to the target value. There can be more than one results, so we need to consider all of them. Now we are told that each number in candidates may only be used once in the combination, and we need to make sure that the given solution set must not contain any duplicate combinations. Okay, so now let's first try to understand this with an example. We are given this candidate array and we are given the target value to be 5. Now next thing is that we need to generate the unique sets. Now let's see that what are all the combinations that can generate this value 5. We can see that we have value 4 and we have value 1. So 4 and 1 is a combination that can sum up to value number 5. So that this can be one of the potential answers. Next one is we have value 2, 1 and 2. So once again we can generate value like this, and this can also be an answer. Next value is that we can do 3 to 2. This is also one of the subset that can generate the answer. But now there is one problem over here. We also have this 3 that we can utilize with this 2 to once again generate the target value 5. The thing is that value is also going to be 3 2, which we have already entered in our result. So we should not be reusing the same set in our results, because we need to make sure that this answer becomes unique. So if we, by considering these elements, we can only generate these 3 values or these 3 sets that combination to the total value 5. So we need to understand that this is how we need to solve the problem. So now let's try to see that what could be the potential solution over here. Now the logically, the very first thing that it would make sense for us to do is that instead of treating all of these weird values side by side randomly, it would make much more sense to, number one, sort the given input array. Why am I suggesting to sorting the given input array? That has two reasons. Number one reason is that let's say that we have some values like let's say 10 and 15 and then so on and so forth, like 100 other values, okay? And we are given the target value to be 5. So the moment we reach to a value 10, then why do we even have to check possibility for all of these 100 values if we have already sorted the results? We know that all the values sum is always going to be greater than 5, which means it is going to be shortening the reach we will have to search for. That is a good benefit. Second benefit is that it will allow us to handle the duplicates in a more elegant manner. So what I'm suggesting is that let's say that in this case we have the values 1, 2, 2, 3 and 4. This is the input we are given. Now what we are doing is that logically it's very simple. We are just simply making decisions. And what is the decision we are making? We are iterating over the very first element. Okay, so let's say that we are currently passing through value number 1. We know that the target has to be 5, but our current sum that we have made so far is just value number 1. So we will need to add some more subsequent values. So let's say we decide to add value number 2 down this current path. So now the sum is 3, still less than 5. So once again we decide to add value number 2. So after adding this value, our sum becomes 5. So the moment our sum becomes 5, whatever the values we were currently having as part of our path, this is one of the potential answers. So let's mark this as part of the answer. Okay, that we currently have found one of the combination 1 to 2 as part of the answer. After doing this, there is still more possibility that we could have some other value that we might have missed on. So we will have to backtrack and once again see for other possible answers. So let's say that we do a backtrack at this position number 2, and once again this now the problem comes because this next element is already 2 and we just did a backtrack. But the thing is, we already considered this 2, so now we will have to consider value number 3. Okay, so let's say if we try to do this one, this current sum becomes 6. So the moment current sum becomes 6, we know that this is no longer a viable solution, which means we will have to do a backtrack because this solution is leading to a value greater than 5, and once again we will have to repeat the operation for all the other remaining possibilities. So we remove value number 2. So once again, now with this value number 1, there might be some other solution with 1 and 3 that we could make. So we try to add value number 3. After this value number 3, the current value is 4. After 4, we add value number 4 over here. So doing this also brings our sum greater than 5, which means we will have to do a backtrack. We do a backtrack and we get rid of this value number 3. Now at this value number 1, we still have possibility to check for value number 4. There is still one more decision we haven't made. So let's say we do this one. The sum of this is actually 5, which means we found another set that corresponds to our correct result and our correct instinct. So we are going to mark this as part of the answer as well. Now once again, we know that we took care of all the things we could using this value number 1. So now we are simply going to go to the next element and not even consider 1 because we ran through all the possibilities we could with value number 1. So we don't have to worry about it. Now at this value number 2, let's say, let me just clean this up a bit. Now we are making a new decision tree, a new decision path where we have 2. Once again, we go to the next element, that is once again 2. After doing this, we go to the next element, that is 3. So now this sum in total becomes 7. So 7 is greater than 5. If 7 is greater than 5, going down this path 2 does not make sense. So we are going to ignore that. Ignoring this, we are going to be going with 3. So we are at this juncture and we found that current sum is 5, which means this is one more potential answer that we will have to record. So let's mark this one. Okay, marking this, we are not done yet because we may still find another results, we don't know. So we go to this next element 2 to 4, but this also leads to result number 6, which means we calculated all the possibility at this current 2 as being the very first element where we are calculating. Now the thing is, next element is also value number 2, and we can see that with previous element 2 we already calculated all the possibilities. So if we had a target value, let's say instead of over here instead of 5, if we had a target value 4, we would have a potential value 2 that is being generated by this 2 already. So we don't have to do anything over here. And also if we try to go down this path, let's say that we ignore my advice for now and we say that currently we took care of this one, we took care of this 2, this 2 is still valid and legitimate. So now we have this value number 2. Once again we go down to the path, so we find value number 3 as the next potential match, and this matches. So should I add it to the answer? No. Why should I add it? Because I already calculated this one. So what I'm suggesting is that once we have the sorted list, we simply check that for any particular element that we are trying to iterate over in the recursive manner using our backtrack function and recursive function, we first check that whether if it is the same element as the previous element. If that is the case, we already calculated all the possibilities and added to our answer, so we can simply ignore that. So now we are all going to be ignoring this 3 as well. Now we are left with this element number 3. So let's try to make possibilities with this 3, and we are just going in one direction. We are not going in the opposite direction because we calculated all the possibilities. So with this 3, the only possibility we have is to add value number 4. The sum is going to be 7, so greater than 4, which means this leads to no result. So we already calculated all the possibility as 3 as well. Next is the only element 4. Once again, if we calculate the possibility, there is only going to be just element number 4, which is not 5, so we cannot put it in the answer. After this, we are done with all the elements in our input, and this is the answer we need to return. So now let's do a quick recap. What we did, we calculated that what was the backtracking function, and we also calculated that what is going to be a recursive approach. For a recursive approach, we need two items. We need a base case and we need a a recursive call or recursive function. We know that what is going to be our backtracking logic, that at every possibility, the moment we either reach to the target value is equal to 5 or target being greater than 5, in either case we are if it is 5 we are going to be adding it to the answer. If it is greater than 5, then we are going to be going to the very previous element that we were iterating over and remove that from our current list and follow along with the remaining possibilities. That is option number 1. For our recursive, the logic is quite straightforward. Base case is going to be that the total sum of the current elements that we are iterating over, it's either 5 or greater than 5. If it is equal to 5, we add it to the answer. If it is greater than 5, then we can simply just move forward or jump to the next element. And for the recursive function, we are simply going to go in a normal fashion by adding the current value and removing the current value from the given input array, and just making a recursive call by adding a new value that is next inside our given array. So if we see the coding solution, it would make much more sense, and this is, in my opinion, a very beautiful solution. So I hope you understood what I was trying to explain. Now let's quickly see the coding solution for this one. So here is the coding solution. First of all, we are generating our result where we are going to be storing the list of array list. Then we are sorting the given candidates array. Plus we are going to have our backtrack recursive method where we are going to be doing backtracking and also making recursive calls. And so now let's understand our backtrack method. So first we are passing in the result list that we just created. We are also maintaining a current list. We are also maintaining the candidates array that we are iterating over. On top of it, we have provided our target and we have provided our start values. Okay. Very first thing we are doing is checking that if the given target is equal to 0, then we are going to be adding the current list inside our result, and we are simply going to do a return from our current recursive call. If that is not the case, we will run our for loop where we are simply going to iterate over all the values that are currently present inside the candidate. Very first thing we are doing is skipping the duplicates. So we are checking that if the current candidate is same as the previous candidate, we can simply ignore that value. Next, we are also doing an early termination if the sum becomes negative, because at every given moment, the moment we see a new ith value, we subtract that ith value from the given current target element, and the moment we realize that this is going into the negative, we are simply doing a break operation. Now if that is not the case, we add the current value to our current array list that we are maintaining. Then we once again make a recursive call with the current value, which contains one more value right now, and we provide the target minus candidates I, because we are subtracting the value from the target that we need to achieve, and we update it with the next element inside our for loop, and that's it. Now once we get a result back from our backtrack, we simply remove the very last element, and we once again do the same operation for other possibilities that we are yet to calculate. So this approach should work. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty fast compared to a lot of other solutions, which is pretty good. So once again, I would be posting this solution in our GitHub repository, so you can go and check it out from there. Thank you. So the lead code problem we are going to solve now is called Palindrome Partitioning. We can see that this one is a medium problem, but in my opinion, this should have been a hard problem. We can see that this is a very well-liked problem. Now let's understand that what is being asked us to do. We are given a string S, and we need to partition this string S such that every single substring of that particular partition becomes a palindrome, and we need to return all possible palindrome partitionings of S. So it sounds a little bit awkward, but let's try to understand this with an example. First, let's understand that suppose we are given a string S such that the values are A, B, C. So we can see that in this case, if we have to partition string, there are a bunch of different options. We can have a partition that is completely like this, or we can do a partition like A, B, and C, or we can do a partition like A and B, C, something like this one, right? There are a bunch of different ways for us to partition any given string. But the thing is, In this case, we need to find partitions such that every single partition becomes a palindrome. Now we all know that what is the definition of a palindrome. Suppose we are given a value like this ABA. In this case, this ABA is a complete palindrome. Why? Because if we write it from left to right or right to left, in both the cases, the answer is just going to be ABA. So same way, this let's say if this is the input we are given, and if we have to partition it in such a manner that every single substring of that partition becomes a palindrome, we only have one possibility. That possibility is if we partition it by using just individual characters, because an individual character in itself is a palindrome. Because let's say if we only have one value, you can read it from left to right or right to left. In both the cases, we are going to be left with the same value. So this is the only answer we need to return in this case. But let's say that we may have been given some other options. Let's say that our given string s is equal to values such as a, then a and b. Okay. Let's say our given string s is equal to values a and b. So now in this case, we will have two options in order to generate the partition. First partition is going to be quite straightforward, that is taking on individual characters because they are palindrome and their own, and combination of these characters actually form in such a manner that every single character is a palindrome in itself. But we can make one more distinction or one more answer in this case, where if we create a partition of these two values a as one partition and we create another partition of this individual character b, then also this becomes a valid partition of the substring such that every single portion of the partition actually forms a palindrome, because this a is a palindrome and this b is a palindrome in itself. So this is what the problem statement is actually asking us to solve. Now let's try to understand some logic on how we can actually solve this problem. Well, if we just have to solve it using pen and paper, what is going to be the first logic you are going to apply? Well, the very first logic is that we will start iterating over this given string character by character, comparing every single character with the previous characters that we have been able to find so far, to determine that whether using the combination of previous characters are we able to generate palindrome or not. If we are able to generate a palindrome, we would mark it as one of the partition and then we will keep on moving forward. So let's try to understand the approach I'm suggesting. Let's say over here we start iterating over at this very first element a. Now for this very first element a, the moment we come to this element a, we have two choices. One choice is that a in itself could be a palindrome, so we mark a as a palindrome. And same way, there could be another possibility that we may find some value where this a could be potentially part of some future palindrome that we are yet to discover. So let's leave this possibility open for us for the moment. Okay. Now, if we decide to create a partition based on a, then once again we have the option to move forward with a single a or the next element. So let's say that once again we decide to move in with a single a and create another partition, which this is the first partition and this is the second partition. Okay. And once again we move to the another value, and for this next value we encounter value b. So once again we create a partition in its own. Now the thing is, when we reach to this b, we realize that now we have reached to the end of our array. So far all the values we find inside or all the partitions we did for our given string s, all of these values are palindromes, because let's say that in order to determine that whether any particular string is a palindrome or not, we are actually going to create a method that checks that if the given string is a valid palindrome or not. Okay, and this string is quite straightforward. They are the values of itself, so we know that all of these values are correct palindromes. And we are also storing some current array list where we are keeping track of all the current values that we are iterating over one by one. So we realize that this is the correct sequence of the partition that generates a palindrome. So we are going to mark this option inside as part of our answer. After marking this, we are not done yet, because once again I mentioned that there could be some potential ways or some potential other paths that we are able to generate, which could lead us to more palindromes that we are yet to discover. So once again let's try to apply that same logic in this case. So now once again we already explored this path. Okay, now what we are going to do is we will do a backtrack operation once again to the very first character to make sure that maybe we did not miss out some palindromes that we could have found. So let's say that we, instead of just creating a single value partition, from this single value we actually decide to do a partition of two values. So creating a partition of two values would give us value AA. Once again we check that if is this a valid palindrome or not, and yes, this is a valid palindrome. So we are good to continue to the next element. For some reason, if we identified that this was not a correct palindrome, let's say for some reason that this value given is x, so then this AX is not a correct palindrome. If this is not a correct palindrome, then it does not make sense for us to continue down this path of partitioning. So then we would choose a different path where after this AX, we would actually include B in our decision making as well. But there is no need to do that. So let's leave it as it is right now. So after leaving it as it is, okay, so we created another partition at this moment AA. The answer is valid, legitimate. So we are keeping it as it is. After keeping this as it is, now we decide to go to make another partition, that is this value B. So once again we create a single partition of just one value B. This is also a palindrome. And with this B, we reach to the end of our list. So after reaching to the end of our list, we are also going to be marking this sequence that we found as part of the answer as well. Now let's try to clean this up a bit. And now once again we are yet to explore more possibilities that we haven't found. So we will also try to do this one. Now for the more, initially we took down a possibility where we are only partitioning the string based on just one value. Then we partitioned the string by using values A, and then also it worked out. Now we are going to partition the string based on considering all three values. So let's say that we just create a partition that is A, and B. This is definitely not a palindrome, plus we reach to the end of our list. So now we are done with our search with starting all the possibilities from this current value A. Now we are yet to identify more possible palindromes that we are yet to identify. So let's say that in the very first beginning when we made this partition, now we will continue down this path, but previously we went down this path that was this answer over here. Now we will try to choose a different path, and in this different path what we are going to do is, with this A, now we are going to pass the baton on to the next element, and now we will say that, hey, next element, if you want to do or try some partitions, let's check those. So once again from this A, we can create another partition like AB, but definitely this partition is not a palindrome. So if this is not a palindrome, then it does not make sense for us to continue down this path, and anyways we are running out of elements in this case. But let's say if we had some more elements over here, let's say some more element like say C. So do you think it would make sense for us to create a partition such that A, B and next element to C check like this? No, because we already know that this is not a palindromic substring. So why even bother checking? So then in that case, our logical step would be to include C as part of one of the possibilities as well. But once again, this is also not palindrome. So now we can be done with this. So this is the simplest approach we can take to solve this problem. Now we all know that what we did, we use the backtracking option to basically go through all the possibilities that we can in order to generate or find sufficient answer. Now let's try to understand that what has to be the logic of our backtracking function. This is going to be a simple function that takes the current partition that we are dealing with, and based on the partition from the input string, it is going to have a starting index for the next partition that we are going to check with. And with the starting index of the next value, we should be able to understand that are we at the end of our string or not, and whether we can conclude the current partition to be over or not. On top of it, with every single value, we are going to check for any particular substring that we are generating, that whether that is a palindrome or not. And in order to do that, in order to accomplish all of this, we will actually use recursion. Now for recursion, we know that we have two items that we need. First one is a base case and second one is a recursive function. Base case is quite straightforward, that if we I previously mentioned that we are going to have a variable called start to keep track of the next index. That would be the starting point of the next sequence of palindromes. Let's say that we created a subsequence like this, AA as one of the palindrome, then start index would be living over here with value number 2, as that is the logical starting position. So we are going to check that if for the current list we come to a place where the starting index is the length of the given string, then we are going to be marking that current index as part of the answer and returning or coming back through our recursion. So we identified our base case. For the recursive function, we will have to do two things. First thing is that for every single new partition we make, we will have to check that whether this one is a valid palindrome or not. If let's say that that is a valid palindrome, then it would make sense for us to call the recursive function once again with the next value in line and creating the current partition as it is. Now I know it sounds confusing, but if you just understand that or try to walk over the solution that I presented, then it would make absolutely beautiful sense to you that what I'm suggesting. And on top of it, for the recursive function, we are also going to be updating the current index value that we are iterating over. Let's say that we iterated over AA, so then we will have a recursive function starting with value number B, and once again we will try to repeat the same process. Combination of all of this should give us the answer, but thing is this is not just enough. Once we receive a call back, and we will have to check for other possibilities, where first we check for the possibility of A only, then we may have to check for the possibility of AA. So in order to do that, we will have to do a backtrack, and for the backtrack, the simplest thing is to remove the very last element we added inside our current array or current array list, and once again repeat the same operation. So basically combination of backtracking and recursion is the way to move forward in this case. Now let's try to calculate the time and space complexity. Well, time complexity is difficult and tricky to calculate in this case because we don't know that how many number of potential partitions we can make. So at the end of the day, this is simply a decision making algorithm, and in the decision making algorithm, at every given step, let's say that we created a partition like this A. Now we will have to check whether to include this A or not to include this A as part of the partition. So at every given step, we are checking for or to whether to make that decision or not to make that decision. So basically we have 2 to the power of n possibilities, where n is the number of characters given, and for every single character we will have to repeat the same operation. So it's going to be n multiplied by 2 to the power of n possibility, and that's why this is a very expensive operation. And if you go through the lead code problem, we are only given like up to from 1 to 16 as part of the range of n for the length of the string, because they also realize that they don't want to put much load on the lead code servers. So now let's try to quickly see the coding solution for this one. Okay, so the very first thing we are doing is that we are generating a new result array list that is going to store different array list inside it to store our answers. Then we are going to have our backtrack method, where we are passing in first of all the result array list we created. Then we are also passing in the current list we are iterating over, passing in the given string that we are given as the input, and we are passing in the starting value of the next pointer that we should consider for the partitioning. This is the starting pointer that I just mentioned. Okay, now first of all, let's see in our recursive function, we are going to have our base case, where we are first checking that if the starting value is the length of the given string, which means we are actually reached to the end of the string, so we can add the current result we are iterating over inside our result array list, and we can simply do a return call from the iterative stack. And now let's check our recursive case or recursive function. So for that, we are basically iterating over from the starting index till the end of this list, and we are updating the value. And here I mentioned starting and ending pointer. This is just simply so that we can check that the given palindrome or the given sequence of element partition we are iterating over, if that is a substring or not, we can simply make that call. So first thing we are going to check is that if the given current substring, is it a palindrome or not. For that, we have created is palindrome method, where we are doing nothing but we are simply iterating over from both ends, like starting pointer and ending pointer. If at any given moment we identify that there is a mismatch, we simply return false. If that is not the case and we complete the whole iteration, then we can simply return true, saying that this current substring is a palindrome. Okay. After determining that the current set of partition is a palindrome, we are going to add that substring to our current list that we are maintaining. And once again, we are going to recursively make call with the same values, except the next index position that we will have to iterate over, and that is going to be our end plus 1. You can also define this end instead of end to be I as well. I just put in end for it so that it becomes better readable for our is palindrome method. And once we get a result back from our backtrack method, we are simply eliminating the last value we inserted inside our current list, because we still have to explore more possibilities. And this is our backtrack function basically. So now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty fast compared to 98% of all the other solutions, which is exceptionally good. Once again, the solution of this code is presented on our GitHub repository, so you can go and check it out from there. Thank you. Okay, so now we will attempt to do a very scary question that is called n queens. Now, in my opinion, this is one of the most toughest and most interesting problem I have seen. Basically, this one is a lead code hard problem, and very justifiably. It is also an extremely well-liked problem, and let's understand the statement. The n queen puzzle is a problem of placing n queens on an n cross n chessboard. So if we are given, let's say, 4x4 chessboard, we will have to place 4 different queens. Now we know that every single queen can iterate in 3 directions. Let's say that if I decide to place a queen over here, then this queen can control these squares, and these squares, because queens iterate in all 3 directions. So based on considering a formation such that I am able to place 4 different queens, and without these queens intersecting with each other on a given n cross n board, and I will have to make sure that I populate all the n queens. Now let's see that what else is being asked for this problem statement. That we are being told that we are given an integer n that defines that what is going to be the size of the board we are dealing with. Now we need to return all the distinct solutions to the n queens puzzles. And good thing for us that we can return the answer in any order. Now there is also one more, just a quick note, that each solution contains a distinct board configuration on a place where the queens can be placed. Let's say that if I decide to place a queen over here, then next queen might be placed somewhere over here, because I need to avoid hits by this queen. So there can be one solution or 2 solutions or 3 solutions, no matter how many solutions are there, where I can place all 4 queens on this 4x4 board. I will have to put all of those solutions inside the answer. Next thing is, we are being told that where we are placing the queen, we will mark it as cube, and where we are not placing a queen, we will just mark it with a dot. So let's first try to understand this problem with this given example of a 4x4 board. The idea is we are trying to place 4 different queens on this board, and we will have to explore all the possibilities we could in order to generate the answer. Now this is going to be a very long video, so I'm just warning you beforehand. I don't want to take any shortcuts, and I want to make sure that I understand this problem and you understand this problem. So now let's get started. Basically, let's start one by one. Let's say that I put the first queen naively on this very first location. If I do that, which means essentially I'm eliminating all of these squares for any other queen to pursue and use it as for their configuration. Let's say I put this queen. Now in order to put the second queen, I have 2 options. So let's say randomly I just pick this option. Okay, so once again, after picking this option, also these squares are now being controlled by this queen. Next thing is, if I want to put another queen, there is no place for me to put the third queen because this entire row has been covered because I put this queen over here. So let's try to revert that. Let me try to put this queen somewhere else. Okay, so let's say if I don't put this queen over here, then all of these squares would become empty. And once again, let me just try to put this queen on the second position and then try to see. So let's say if I put this queen over here, once again these squares gets controlled by this given queen, and now I only have one option in order to put the third queen, so I can put third queen over here, but that controls this option, which means once again I cannot put four queens over here. So once again I will have to go back, and I exhausted all the possibilities for the second row, which means I still have to exhaust more possibilities at the first row by changing the position of this queen. So let's try to do that operation. For that I will have to clear the board and basically do a backtrack operation. Let's do that, and now I'm trying to place queen over here. Now which are the squares being controlled? Let me just quickly mark each one of these to make sure that I don't create any confusions. Now for the second row I only have one possibility where I can place my queen, so let me do that, and let me also mark all the items that are being impacted by this queen. Okay, now for the third row I only have one option, so let me also place one queen over here and once again exhaust all the possibilities. And now for the fourth row I only have one choice where I can place the queen, and that is this empty square. So now we can see in this case that we are able to place all four queens on a 4x4 grid. So this is one of the potential solution. So we will actually have to mark this entire solution and place it inside our answer array. So the thing is, let's say that we create a list that is going to store all the answers. How we are going to take the snapshot of this is that we are actually going to create an array that is going to represent every single row for this given entire section, and for each of the row we are going to mark it as this, that we are going to store string values, where for the first two elements we don't have a queen, so we are going to mark them by dots, and then we do have a queen, so we are going to mark it by queen, and then we are once again going to mark it by dot. Once again we are going to do the same process, so queen and then dot dot dot. Once again for the next element repeat the same process, so basically three dots and then a queen, and for the last one we are going to dot queen and dot dot. So dot queen and dot dot. Okay, and so this becomes one of our answers. But the thing is, this is not the whole answer. We could still have more potential answers. So let's say we explored one possibility. Let's try to explore another possibility. And remember, once again, we are doing the backtrack operation. Going back to the very initial call, we already exhausted these two possibilities for the position of queen. So let's try to explore more paths. Let's say if queen is over here, then once again let's repeat the same operation. We are going to eliminate all the squares being controlled by this queen. The option is to place it over here. Once again eliminate all the options. Once again we can place a queen over here, and for the last one we can place a queen on this position. So once again this becomes another one of distinct answer, because notice the positioning of queens are different compared to our previous answer. So once again we are going to note this entire answer. Now don't worry, I will not put you through the painful process of going through the whole thing. Let's say that I just paste this answer over here as part of the next array list inside our answer, where we are going to return the list of array list. Okay, and now let's say we try to explore the very last option for the queens. Once again for the very last option we are going to be placing the queen over here. If we try to do this one, basically this solution would not work, because we would not be able to find appropriate queen positions in order to fill it out. So notice that in this case once again we filled out all these four possibilities because we placed a queen over here. If we don't do that, if we decide to place a queen over here, then once again we are eventually going to fill out all of these possibilities. So these are the only two distinct ways through which we can place all four queens on this 4x4 grid, and this is what we will have to return as part of the answer. So this is what is being asked us to solve. Now the thing is, let's see how we can actually solve this problem. So notice at the very beginning when I selected a queen over here, immediately I did not started rejecting this option. Basically what we can do is that at every single position we have two options to make, that whether we can place a queen over there or we can not place a queen over there. Now we will have to explore both the possibilities, and in this case we will proceed in column by column area. So we will try to put the queen on the first column. Based on that, we will it will determine the position of the second column, and then third column, and then fourth column. So initially the idea is going to be that for the very first column on the leftmost portion or the very first value, we will try to place queen. And let's say that after placing this queen, our logic would be that we will have to find an empty space in this particular section where the squares are not being hampered by this queen. We can completely ignore this entire column the moment we place queen at one of the position. So our jumping is going to be based on column by column level, and at every single column for all the n values, we will have to determine that whether it is a sufficient place to place a queen. And the moment we find the very first opportunistic moment where we can actually place the queen, once again we are going to repeat the same operation for the next subsequent column, and once again we will try to find an appropriate cell where we can actually place the queen. So there could be two options. One option is that let's say that we are able to identify some place where if we just take a look at this example, basically in this example, if I place a queen over here, we exhaust all the possibilities. Now there are no place for us to place a queen, which means immediately it should come to our brain and also in our program that placing queen over here is not a good idea. That is option number one. Option number two is that placing queen over here is not a good idea. So we are going to do the backtrack operation, and after backtracking we will first try to remediate our this mistake, and we would, instead of placing queen, we would place at the second possible place, and once again try to repeat the same operation. But eventually this will also not yield us the correct result, and eventually we would keep on backtracking to our very first decision. And through the very first decision, we would try to make sure that, okay, instead of placing the queen over here, let's try to explore other possibility, and then this would lead us to our correct result. So that is number one thing on we can understand that how we are actually able to find the answer. The logic is quite straightforward. We are simply going to do a recursive backtracking call in order to determine that whether the given path is a correct sensible path or not. But this is not as simple as it sounds, because there are a lot of computation and a lot of things we will have to understand and break down for our program to that how it is going to work. So let's quickly understand first that what is going to be the recursion we need to do in this case to complete the problem. Well, we know that for recursion we need two items. Number one item is that a base case, and second item is that we need a appropriate recursive function. Base case in this case is quite straightforward. The moment on the C4th column we find an appropriate location for the queen, we know that we already crossed all of these columns, and then we reach to the column 4 where we are able to find an empty slot for a queen to be put in. So which means this has to be the complete correct path that we are able to generate in order to fill the answer, and that is exactly what we are going to be storing as part of our base case. So what we will do is, number one, we will need some way to keep track of all the paths that we have taken so far, because by doing that we are doing two things. Number one thing is that when we do reach to that happy path scenario for our base case, we can actually add the path that we have stored for so long for the positions of queen as part of the one of the values for the answer. So that is number one thing. Number two thing is that using this path, let's say at some moment we decide that we cannot go further anyway, then once again we can just say that this path does not yield to the correct result. If it does not yield to the correct result, we can simply do a backtrack operation, and through the backtrack operation we will try to explore other paths. So just same way we saw over here that this Q location was not working out, so we tried to see for this Q location. Once again that didn't work out, so once again we updated from our Q location this one to this one, and then we try to identify that whether this is the correct path or not. So we made some judgment calls through our recursive function on what are the things we are trying to achieve. Basically, don't get confused. We are just doing exactly the same thing that I showed you on throughout the entire graph. The only difference is we are trying to do it recursively, and we are trying to follow both the things, that what is going to be the base case where we need to break out of the recursion and store the value to the answer. If we are not able to do that, then we will also have to do the recursion using the current path we are choosing in order to solve the problem. Now there are also few more things that we will have to understand. First thing is that at every given moment, whenever we are checking for potential candidates, we will have to understand that whether this path we are taking, if that is the correct path or not. Because let's say that in this case I place a queen over here, which means I am eliminating these elements that can ever be used for the potential queen. So now when I am at the column 2, I once again going to check all of these positions one by one, and in order to check that whether they are good candidates or bad candidates for my queen to be placed over here, I will need some method to basically do a validation that whether I can place my queen on this square or not. And the only way I can check is that is to check my current path that I have currently iterated over and see that this particular cell has it being impacted by any of the queens that I have previously placed. And by doing that, we can actually make sure and find the potentially good values for our queen. So let's say that we identified potentially good values for our queen. So we did this operation for this first column. Then once again we repeated the same operation for this next column. Once again we are going to repeat the same operation for this third column. So logically we are just redoing the same thing that we have done in the past, but for the different input. And that's where the second requirement for our recursion comes into the place, because remember recursion needs two items. First one is a base case and second one is a recursive function. So as part of the recursive function, whenever we are moving to the new column, we are simply updating the value of the column, plus we are also updating the value of where we have stored the queen in the previous value inside our current path. So this will allow us to do the backtrack and also allow us to move to the next value inside the logical iteration of our recursion. On top of it, that's why this is a hard problem, because there are a lot of on top of it that you will have to understand. At every given moment, once we reach to the very end, in the current path we are not keeping track of all the items of the board. We are just simply keeping track of the position of queen that we have placed so far in each of the columns. So once again we will have to have a method where we are actually generating the board based on the positioning of the queen. So remember that ugly board that we are seeing, like that contains dot q dot dot, then once again like dot 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 q, and this type of like Morse code type of structure. We will also need a method to generate this as well. And this is the solution. Basically this is the optimal solution in order to solve this problem. We are using backtracking, we are using recursion. For recursion we have a base case, we have a recursive function, we are keeping track of the current path we are at. We need to have a method to check that whether the given path is valid or not, to place the queen based on the previous queens we have placed. Plus we will need a method to generate the board that we need to generate in order to solve the problem. And in the end we need to store everything in an answer, where in the answer we are actually storing the bunch of different arrays as part of the array. So it's going to be an array list that contains multiple array lists. And if we try to calculate time and space complexity in this case, well, it's really difficult to calculate the time complexity, but let's try to understand the time complexity logic in this case. If you can understand this, then your logic to solve time complexity is going to be pretty beautiful. Logic is quite straightforward, that for every single column we are iterating over all of these values, and we are doing it for each of the columns, which means basically we are in the worst case scenario, we are iterating over each one of the elements. So basically and the number of elements we know are n to the power 2, and at every single element we have two choices to make, whether to include that element or not to include that element, which means we are actually doing 2 to the power of n multiplied by n, or 2 to the power of n square work. For this one, and we will have to repeat the same operation for each of the columns, because remember that in column 1 there are 4 possibilities that can lead us to different paths, which means we will have to calculate this for each one of them. So we will also have to do this operation n times. So time complexity is horrendously bad, and that's why if you read the problem statement on lead code, we are only being told that the value of n can only be between 1 and 9, nothing more than that. We are dealing with a very small number of finite solutions, because if you try to do this with million values, we need quantum computers in order to solve this problem. Okay, now let's quickly see the coding solution, and I hope my solution made sense to you. Okay, so the very first thing we are doing is that we only have value n that we need to return. So first of all, we are creating a blank board of n cross n size, and we are marking all the values as initially as dots, because we don't have any queens placed at the moment. We are also initializing a new array list of list called result, where we are going to be storing all the result, and then we are going to be calling our backtrack method. This backtrack method is going to do the backtracking and also recursive function for us. In the input, we are providing the new board that we just created, plus the starting index of the very first value that we need to iterate over, and the result array list that we have just created in order to store all the answers. Now let's understand our backtrack method. So very first thing we are doing is this is our base case, that if the current length of our column is equal to the length of the board, which means we have placed the queens correctly on all 4 columns or all n columns. So the correct current path or the current version of board is suitable enough for us to place it into the result. The thing is, we are not directly placing it into the result. We are actually calling a construct method to construct the board we want in the subsequent manner. And first, let's just see the construct method. Okay, so in the construct method, we are just passing in the board. On top of it, we are checking that what are all the current positions of the queen that we currently have, and we are just adding those values as part of the queue. Apart from that, we are not doing anything else, and we are simply returning that to the result. Okay, next thing is so let's say we add the appropriate result over here. Then we have our for loop, which allows us to iterate over all the values inside our given input, where we are starting the value from 0, we are going until the length of the board, and we are just doing I plus plus. Very beginning, for every single board position, we are checking that is it a valid place where I can place my queen, and this is valid method is doing nothing but checking that based on the previous paths that we have calculated, whether we have any particular queue or any particular queen placed before that is either in the row of that particular queue, in the column of that particular queue, or in the diagonal of that particular queue. If that is the case, we simply need to return false, that this is not a valid position where we can store our queen. If none of these cases are true, then only we will return true, saying that yes, this is a valid place where we can actually place our queen. So once we find a valid place, we update the position of our board to mark that value as q or queen, and then once again, so this is what we are updating the current path, and then once again we are going to be calling our current recursive method with the new recursive call, where we already updated the current path of the board, and we also call in with the next index position or the next column we will have to iterate over, and we will keep on repeating the same process. Once we receive a call back from our board, we will also have to explore other paths that we haven't explored so far, and that's where this recursive call comes in, where remember, first we are marking this current position as q, but next we are marking this current position as a dot, that this is no longer a cube, and we are exploring other paths. And this is the whole solution. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs 87% faster than all the other solutions, which is pretty good comparing that how difficult question this one has been. Also in terms of memory usage, our code is pretty good, and in terms of like much better than a lot of the other solutions. Once again, the solution of this code is present on our GitHub repository. I highly urge you to go and check it out and try to solve this problem. If you can solve this problem, I don't think any backtracking problem would be a cause of concern for you. Okay, thank you.